হুম,
হ্যাঁ, এটা তুই কি অ্যানিমেশন দিচ্ছিস না নেক্সট স্লাইড যাচ্ছিস? ওই তোর স্লাইড নম্বর 2 সম্ভবত আসছে এটা।
কি দেখছো স্লাইড 2 তে? ইন্ডিয়ান ইনস্টিটিউট অফ সায়েন্স এডুকেশন রিসার্চ এর একটা ভারতের ম্যাপ।
হ্যাঁ, ভারতের ম্যাপ, ভোপাল হাইলাইটেড।
হ্যাঁ ঠিক আছে, গুড। তারপর আমাদের অ্যাসেট ফল কিছু দেখতে পাচ্ছ?
নেক্সট স্লাইড যাচ্ছে না।
Shrikant, Akhilesh, should we start?
Yeah, of course.
Good morning, everyone. Welcome to the second day of the RAIC 2022. And we'll soon start the second session of the eWorkshop. Professor Akhilesh Singh will introduce the chair, Professor Pedretti, and then the session can start. Akhilesh, please take over.
Okay. So thank you, Samantha. So this second day of RAIC 2022, the morning session will be chaired by Professor Pedi Reddy. So as such, he doesn't need any introduction. He is a well-known chemist in the field of crystal engineering. He did his PhD from University of Hyderabad, and later on he worked at JNCSR, and then he worked as a senior scientist at NCL Pune for quite some time, and then he joined IIT Bhubaneswar in 2009. And he has more than 80 publications. He is recipient of CRSI bronze medal. So, Professor Pedi Reddy, please start introducing the speaker of this morning session. Professor Pedi Reddy. You are muted. Professor Pedi Reddy.
Yeah. Thank you, Dr. Akhilesh Singh. And also I thank the organizers of this meeting. Yeah. Are you able to hear me?
Yes, we can hear.
Yeah. Thank you, Dr. Akhilesh Singh, for the introduction. And also I thank the organizers for inviting me to chair the session, which is really a wonderful session with speakers. Yeah. Now, we start our session. We are having the three eminent speakers. First, we'll start with Professor Padhasarat Mukherjee, who is one of the very well-known chemists in the country in the inorganic chemistry and working at the Indian Institute of Science, Bangalore, in the Department of Inorganic and Physical Chemistry. And his research fields are been supramolecular nanomaterials, organic nanomaterials, molecular sensors, catalysis in nano cages. He is very well known, as I mentioned, with great distinctions. One of the major things that is been, he is the recipient of the Shanti Swarup Bhatnagar Prize in the year 2016. He also been recipient of Chemical Research Society of India Bronze Medal, and he has distinguished honors with the membership in various academies, particularly with the Fellow of Royal Society of Chemistry. And beyond that, he also been the recipient of Swarna Jayanti Fellowship, which has been the part of the Government of India in the Department of Science and Technology. Below the age of 40 years, I think he received it when he was at that age. And he was also Nasi Scopus Young Scientist Award. Apart from that, academically and research-wise, he's been very much well known with his credentials as in the form of editorial advisory board member and also the associate editor in various prominent premier journals of the chemistry, for example, Inorganic Chemistry and also Inorganic Chemistry Frontiers, published by Royal Society of Chemistry. And he is also a member of editorial board of Scientific Reports, a journal of the Nature Publishing Group. At the beginning of his career, he was the Alexander Humboldt Fellow, which has been one of the prestigious awards that we do consider in sciences. And he has a very accomplished teaching and research engagements at Indian Institute of Science, Bangalore. With all these distinctions and credentials, I would like to now invite Professor Padhasarat Mukherjee to deliver the lecture entitled Molecular Vessels. Professor Padhasarat, it's
Thank
for
you,
you.
Professor Reddy, for your kind words of introduction. Let me begin by thanking the organizers for the kind invitation to deliver this talk. So my group at Bangalore basically work involved in designing molecular architectures of defined shapes and sizes and use their confined space for catalysis, sensing, as well as for recognition and separation of chemicals from mixture. So my today's lecture will focus mainly on molecular vessels, particularly water-soluble molecular vessels. First part will be on molecular vessels that show different behavior of chemicals in compounds, particularly photochromic compounds in their confined space. And second part will be on chiral molecular cages or vessels and their chiral recognition. Now, we actually use mainly metal-ligand coordination as driving force to construct such discrete molecular architectures of defined shapes and sizes. Our design strategy is very simple, utilizing the general concept of geometry as well as coordination chemistry. From the general concept of coordination chemistry, we know that palladium and platinum in +2 state adopt square planar geometry. That means a naked palladium 2 ion has 4 dsp2 hybridized orbital, empty orbitals. Now, if we treat it with one equivalent ethylene diamine or any diamine, it will actually block 2 sites. So a tetratopic acceptor, that means initially it had 4 sites available to bind with donor, has become now ditopic acceptor because it has now 2 sites available to accept donors. And the angle between these 2 available empty sites is 90 degree. So we call it 90 degree acceptor. Now imagine a molecular square. Use your general concept of geometry. In case of a molecular square, you have 4 90 degree corners and 4 linear arms. So if we use it as a 90 degree corner and treat it with a linear arm, this is a ditopic acceptor. That means 2 sites are available to accept donors. So we have to treat it with a didented or bidented donor, which is having 2 donor sites to satisfy the coordination number. Now, this is a 180 degree donor because the angle between these 2 donor sites is 180 degree. Okay, now if we mix them together, they will assemble, self-assemble together to form a 4 + 4 self-assembled molecular square. That means 4 acceptors and 4 donors assembled together to form molecular square. As both the units are ditopic and didented, resulting assembly will be a 2-dimensional architecture. Square, or depending on the angle, if we make it 60 degree, we can get a triangle. If we make it 90 degree, we'll get a square. Like that. If we make it 110 degree, then we'll get a pentagon like this. Now, instead of ditopic or didented, if we take one of the building blocks, which is having 3 sides available to bind, or 4 sides, then we'll get a 3-dimensional architecture. So using this general strategy, we design many complex 3-dimensional structures. Okay, so in first part of my talk, I will show you design of water-soluble molecular barrel. We are very much fascinated using this coordination-driven self-assembly approach to design molecular barrel. Okay, our group is the only one working on molecular barrel or introduce the field of molecular barrel because barrels have wider window size. One window can actually allow entry of the reactants or substrates, and other window will allow the products to come out or even the guest molecule to come out. In first part of my talk, I will show you how different is the behavior of photochromic or thermochromic molecule inside molecular barrel compared to their traditional behavior in glass vessels. Now, photochromic compounds or thermochromic compounds are those compounds show different colors by changing temperature or by applying light. Now, Spirochylon compound is a well-known photochromic compound. This is the stable form, which is a non-planar molecule. So these two rings are like almost orthogonal. So this form is almost colorless or very light cream color. Now this is stable form. If you prepare or if you buy from commercial sources, it will be like this. Now, if you apply heat or if you irradiate with ultraviolet light, this ring will break to form this open conjugated form. Because of this conjugated form, it is colored either red or strong yellow or sometimes blue, etc. Now, this open form, which is deuterionic, is not stable. This is called merocyanin. This is called spiropyran. Merocyanin form is transient. Its lifetime is just a few seconds or minutes. So as soon as you remove from UV source, it will come back to its parent stable form. Or if you cool it down, it will come back to this one. But remember, this non-planar molecule becomes planar conjugated molecule upon irradiation with light or upon heating. Now, this non-planar molecule to planar molecule transformation needs some space available for this movement. Now, in solid state, molecules pack very closely. So, spiropyran does not store solid state such thermochromism or photochromism easily because of the non-ability of available space for this molecular motion. But in solution state, if you take solution of this spider compound, irradiate with UV light, it will become red. And these two forms can be easily distinguished by NMR as well as by UV. UV shows strong absorption between 500 to 600 nanometer for this highly colored form. Whereas for the closed form, there is no absorption in the visible range. Okay, because it is very light colored or almost colorless in many cases. So in solution state, particularly in organic solvent, this is very facile, but in solid state it is not. But for practical use in many cases, we need solid state thermochromism or photochromism. Suppose if you coat your glass with thermochromic or photochromic compound, if you go to daylight or outside under sunlight has UV rays, so that will actually convert this to color, so become dark. So it will act as goggles. As soon as you get into room in absence of sunlight or in the evening time when there is no sunlight, it will become transparent. So, but for this practical application, your compound or the spider compound thin film should show solid state thermochromism and photochromism. Now, the question that we ask ourselves is, what is the fate of such photochromic molecules in confined molecular space? They behave differently in glass vessel in organic solvent. First of all, such spider compounds are not soluble in water. What will be the behavior in aqueous medium? Second question is it possible to have such solid state photochromism? To understand this, we actually design molecular barrel. So first we design a tetratopic donor. This is a tetrapyridyl donor. This is one donor side, this is second, this is third, this is fourth. We have two more pyridyl units, but they are actually surrounded by bulky pyridyl units. So acceptor cannot easily approach here. Not only that, ortho position has electron withdrawing pyridyl groups. So its electron density for donation is less available. So only 4 pyridyl nitrogens will be available to donate to acceptors. Now, so this is represented by this panel. So it looks like a flat unit with 4 corners having 4 pyridyl lone pair of electron. Now, when we treated it with a 90-degree acceptor, this is a 90-degree acceptor because this nitrate and this nitrate can be easily replaced by pyridyl lone pair, and you can accommodate this. So now, when we treated, actually we got a complex mixture of two barrels. One is uniform barrel, another one was distorted barrel, okay, in DMSO. But when we heated this in water medium, then it converted to an uniform barrel like this. So you can consider that uniform barrel is formed, or this distorted barrel is formed by sliding two sides like this. We crystallized both the barrels by using two different solvents, and this is the crystal structure of the uniform barrel, and this is the crystal structure of this distorted barrel. Now, once we could actually convert this complex mixture to uniform barrel like this, we use this barrel as molecular vessel because it's a large window at the top as well as at the bottom. Now, this barrel is highly soluble in water, though the building unit tetrapyridyl is not at all soluble in water. Because of the highly charged nature, you see how many palladium you have, 8 palladium, so 16 counter nitrate anions as well as highly positive charge. This is actually highly soluble in water. So this is the aqueous solution of our barrel MB1. This is not soluble in water. This bromo-substituted spiropyran is not soluble in water. But if we add this to this, in a few minutes, it becomes green color. Okay, because it gives you blue solution, and this blue and yellow mixture gives you this green color. NMR showed that it is indeed in the form of merocyanin. You see, this is having merocyanin unit that is cleared from photon NMR. And then UV shows that this green colored solution shows strong absorption at 590, which indicates that this compound is now converted to merocyanin form. Remember, we just added it without applying UV light, without heating. Simple stirring at room temperature could convert this spiropyran form to merocyanin form. Okay, this is very unusual. Not only that, if you keep this green solution for months, it will remain green. That means merocyanin form is stable in this molecular vessel, and this is the stable form, not the spiroform is stable form. Why, I will explain later. And from the NMR integration, it was found that host gas stoichiometry, that means this barrel takes up 2 molecules of gas, this one, and it exists in this open form. Now, we have also checked whether this is only restricted to one spiro compound, or if you change the substituent, it will also show. So we replace bromo with nitro. And in this case also, when we added, it showed red coloration, and red coloration was also due to, again, spiroform that was fully evident from NMR as well as by UV study. And then you see, if you take it out, you add chloroform, take it out, shake for a few minutes, it becomes blue. And this is due to this merocyanin form. So merocyanin form immediately comes to organic part because it is highly soluble in organic form. But if you keep it for a few minutes, this blue becomes just colorless, because in organic medium, it converts to its usual stable form, that means spiroform. So inside confined pocket, it exists in open form, but outside confined pocket, in glass vessel or in organic medium, it becomes this stable spiroform. So we could stabilize the unusual or transient merocyanin form in confined pocket or molecular vessel. So to generalize whether this is only true for a particular barrel, or it can also show similar behavior in other aqueous molecular barrel. So we reported this barrel where instead of tetrapyridyl, we use tetraimidazole donor. So this is more wide. Previous ligand was actually more long. Here it is more wide. So we could actually generate a barrel which is having more wide open space, pocket or window side. This was used actually for stabilization of fluorescent compound, drug molecules, and then transported to life cell. Earlier, I'm not going to talk on this. I will show only behavior of photochromic molecule using this. So when you use this one and treat it with bromo as well as nitrospiropyran separately, in this case also we found similar behavior. Okay, color change and merocyanine form was stable in both the cases. Here there will be a double bond which is missing. So this barrel also stabilized the open form of merocyanine form. Okay, in both the cases. So what is the overall story? Overall story is the barrel. This is colorless almost. If you add Spiro compound, it stabilizes open form. NMR integration, so two molecules go inside, but DFT showed if we try to encapsulate only spiroform inside this pocket, as it is non-planar, it needs more space. So two molecules cannot be accommodated comfortably inside this pocket. So one molecule cannot have better fit or packing with the wall of these barrels, while two molecules, because of the flat nature, can orient in head to tail fashion. That means positive charge of this positive end of this molecule will come close to the negative end of other molecule, and that will have electrostatic interaction. Pi-pi interaction between these two molecules, as well as these molecules, pi cloud will have strong interaction with the backbone of this barrel. So this extensive pi-pi interaction, electrostatic interaction, stabilize merocyanine form so favorably that two molecules of merocyanine get stabilized instead of spiroform, because spiroform is not at all stable in confined pocket here. So we have shown that in molecular vessel or in confined space, behavior of spiro compound or photochromic spiro compound is completely opposite to what chemists have so far seen in organic solvent in glass vessel for last 50 years. Not only that, if you heat this solution, it comes out as solid particle at the bottom. If you keep it again under normal temperature in visible light, it again gets dissolved to form this. So as I mentioned, that spiro compound needs to be irradiated with UV light or to be heated to get merocyanine. But in presence of barrel, without heating, without UV light, you can convert it to merocyanine form. Now, if you heat this merocyanine form, it forms spiro compound, which is reverse photochromism and thermochromism. So in presence of barrel, we could see reverse photochromism and thermochromism. Now, the second question was, is it possible to have solid state photochromism? To address this question, we actually simply took solid spiro compound and then solid barrel. And if you grind them simply, you can see color change. That means something is happening. Okay, after some time, if you just keep under UV light, you can see the color change. Okay, so after 10 hours, this is the situation. And once you apply UV light, you see it converts to open form, and open form can easily go inside after grinding inside the molecular barrel and get stabilized. So it doesn't come back to the colorless form. So in this case, this is the solid state under UV light. You see, this is after grinding under UV light, it shows color change. So solid state photochromism was also seen in presence of barrel. But if you simply take spiro compound and grind under UV light, after irradiation also, you won't see this one. But in presence of barrel, grinding creates some heating as well as UV light actually converts this closed form to open merocyanine form, and this merocyanine form gets stabilized inside barrel, and this stability enhances the reactivity or conversion rate from closed form to open form high. And that's why it converts to methocyanin form. So we prepared a hexane solution of our Spiro compound, which is soluble in hexane. Barrel we made solution in aqueous medium, then dipped a filter paper into this barrel's aqueous solution and then took out and dry it with a heat gun. So your filter paper is now coated with solid molecular barrel, correct? Now you use this hexane solution of Spiro compound as an ink. Using a pen, you just write something on this. Nothing is visible because in solid state, you cannot easily convert Spiro compound colorless hexane solution to colored methocyanin form. So you have to irradiate with UV light. You keep under sunlight for 5 minutes. You can see this glow. And even if you take it out from UV light, you keep it room temperature, you can see this color. That means just for few minutes, if you keep under sunlight, that is good enough to convert this to open form, which is colored, will remain stable. Now dip this colored writing pad into chloroform or dichloromethane. This color compound, methocyanin, is an organic compound, is soluble in organic solvent. You can wash out, but your barrel is not soluble in chloroform. It will remain in filter paper. So you can use this pad as a rewritable pad and write again. So it was used as magic pad for writing several times. We have also used a different class of photochromic compound. I will not talk much on this, but I will just show the result. This is called donor acceptor stain house adduct. It was first reported in 2014, very new generation photochromic compound. In this case, stable form is this open form, which is highly colored. Now, if you take it in non-polar solvent like toluene dioxane, irradiate with green light or even visible light, it converts to its closed cyclic form. But remember, in non-polar medium, this cyclic form is not stable. So as soon as you remove this light in dark, it comes back to its stable open form. But in aqueous medium, polar aqueous medium, story is completely opposite. If you take it in aqueous medium and stir for some time, it will readily convert to this deuterionic closed form, which is highly soluble in water, stable in water. You can never return it back to this open form by any chance. That means in aqueous medium, it is a reversible process, but in dioxane or toluene, in non-polar medium, it is reversible process and light directed process. Now we designed this tetraimidazole and treated with 90-degree acceptor. We got barrel. It was structurally characterized by X-ray. This is highly soluble in water. And then now we added aqueous solution of this barrel. To this aqueous solution, we added solid, this stable form. As I mentioned, in aqueous medium, it converts to colorless cyclic deuterionic form. But if I have barrel, it does not go to deuterionic cyclic form. It will remain in this hydrophobic form inside this cavity. It is reflected from this color as well as from UV, which shows strong absorption at around 510, 512 nanometer. So barrel could actually stabilize this even in presence of aqueous medium. Not only that, even as I mentioned that this process is irreversible. That means you take this DASA, dissolve in water, that means you get this form, cyclic form. It cannot be transformed to this open form at all. But after getting this solution, if you add our barrel to this, barrel is soluble in water, after some time, it will become colored again. That means, and by UV and NMR we prove that this closed form now is converted to open form in presence of barrel. So an irreversible process was made reversible in presence of molecular barrel. So we have seen completely unusual behavior of another kind of new generation photochromic compounds inside molecular barrel. So we have also shown similar kind of behavior using a different molecular barrel, using different kind of substituted this DASA, which are very difficult to convert to the closed form to open form, but we could see in presence of a barrel which was reported last year. Now I move on to the second part, that means chiral cages. Now, you see, if we use a chiral building blocks, then resulting assemblies are always chiral generally, okay? But chiral cage or chiral assemblies are really challenging to design. Simply, this is a well-known cage reported by Fujita's group. This is a triangular donor. We have 3 pyridyl nitrogens with lone pair of electron. So these 3 corners represent 3 pyridyl nitrogen. If you treat it with a 90-degree donor acceptor, then you will get this octahedral cage. This is an octahedron with the corners having palladium, and each palladium is having ethylene diamine or tetramethyl ethylene diamine. Any chiral amine if you have, always you will get this one. Okay, so this cage is chiral. Now, one may imagine that if we simply substitute this amine with a chiral amine like cyclohexane diamine, chiral RR or SS12-diamine cyclohexane, then we can get an enantiomer pure cage. It is true. If you replace this amine with an enantiomer pure diamine, you will get enantiomer pure cage. True. But this such kind of enantiomer pure cages do not show chiral recognition. That means they don't show binding to a specific enantiomer of a chemical entity. Suppose if you take R-binol, it may not bind specifically R-binol or S-binol selectively. So it does not show chiral recognition. So only enantiomer purity of a cage is not good enough to show chiral recognition that we have established later on. So to show chiral recognition, your pocket need to have chirality. That means your pocket cannot be symmetrical in nature. So with this hope, we actually tried to design chiral cage with some building block that are not chiral, but still they have some kind of helicity kind of ligand. So we use this tetrajol, ditetrajol. If you remove hydrogen, one of the NH proton, then it will be tetrajolate. So this nitrogen can act as donor. So this will be bidentate donor. This unit also will be bidentate donor. So it is a tetratopic donor. Okay, that means tetradentate donor. 4 nitrogens can bind. So when we treated with a 90-degree acceptor, we got this unusual tetrahedral cage. Tetrahedral cage from square planar metal ion is not simple, very rare. So we got tetrahedral cage like this, where if you see the crystal structure, you have a helicity. You see, if you see this one, you see it is going like this. All the ligands are like this. So this is like anti-clockwise helicity. In this case, it is clockwise. So this is lambda. Okay, so both the cages were crystallized. Crystal structure showed the presence of both the forms. Okay, that is the problem. That's why it was not, even though the cage is chiral, we could not get enantiomer pure cage. Okay, but here pocket is chiral because you see this form has a particular helicity or orientation of the ligands. This form has exactly opposite. So if we can get one of them, then it should recognize a particular enantiomer in its pocket. So we use same approach. Instead of this, we use a hexadentate ligand. That means tritetrajol. So if you remove this one, this NH, then it will get tritetrajolate. ligand. So it will be a hexadentate ligand. In this case also we got a tetrahedral cage, palladium 12 cage. But in this case, remember, faces of tetrahedron are occupied by the ligand. Here edges of the cage, tetrahedron, are occupied by the ligand. That means your faces are free, empty. You have large window size. Your faces are occupied by the ligand. That means your window size for gas to go is very narrow. Now we determined X-ray for both of them. Both of them have same size, same shape, water solubility. Now we tested encapsulation using this hydrophobic compound. This in aqueous solution of this cage, it is soluble as is reflected from strong NMR peaks. This is not soluble in water, but in presence of cage, it is highly soluble. Integration ratio showed 1:2 host gas complex formation. But when we added this cage, face directed cage, it did not show any encapsulation of this molecule because of narrow window size. So one cage shows encapsulation, another one showed no encapsulation, and then both the cages were used as catalyst for performing Michael addition reaction using this dimethyl barbituric acid, which is having actually active methylene group. So in this case, Michael addition product was formed, which is chiral. This center is chiral, but no particular enantiomer was formed because our cage has both delta and lambda. No enantiopure cage was formed. That's why no enantio selectivity was formed. But remember, as T2 did not show any encapsulation, that means face directed cage, its activity or yield was almost identical to the yield that we obtained without using any cage, that means blank. That means it did not promote catalytic reaction. But in presence of T1, where encapsulation was possible, we found large or increase in product yields that indicated encapsulation enhanced catalytic activity. So it is cage catalyzed reaction in aqueous medium. Remember, we did not use any organic solvent that generally organic chemists use for performing such Michael addition reaction. Now, what was the problem? As I mentioned, though we got chiral cage, pocket was chiral, cage was not enantiopure. So we could not use for enantioselective catalysis or enantioselective recognition. Now you see the unit, this triangular unit, it has 4 triangular units in the tetrahedral cage. What did we have? We had actually this tetramethyl diamine unit. So this is not perfectly planar. You see the crystal structure in one way, this is like this, in another way this. So in one cage, all the units are like this. You have palladium N bound, and it is like this. And in other cage from crystal structure, all the ethylene diamine units, CC bond was like this. Okay. Now, as this is flexible, it can adapt in this form or in this form, E2 fashion or E1 fashion. E1 fashion gave lambda cage, E2 orientation gave delta cage, because we have both the cages in the crystal structure we found. Now the question is, can we freeze this orientation in a particular way, only E2 or E1? Then only we can freeze E1 conformation, then we'll get only lambda cage or delta cage if we can freeze E2. We use this simple concept. So instead of ethylene diamine, here you have hydrogen. If you use a rigid unit, then it will not allow 2 conformation like this. A particular orientation will be frozen, like this or this. So you use this enantiopure unit, this one, to freeze one particular orientation. Just by replacing this with this, we prepared this one. This synthesis was not simple. We struggled for almost 6 months to get this one, and then we use this. Same concept, same ligand was used to prepare this cage. We got clear solution, and then CD showed, yes, we got chiral cage. If we replace this with SS, we got enantiomer opposite one cage, and both were crystallized and characterized. Okay, so in this case we got only one, no counter cage was crystallized. So we got enantiomer pure cage and chiral pocket. Pocket is expected to be asymmetric because of different helicity of the ligand. In this case, one particular direction helicity is there for all the ligand. Now, to generalize this, we use different ligands, naphthyl, biphenyl, tetraimidazole. In all the cases, we could get enantiomer pure cages. Now, as this one is having larger pocket, we use this for host gas chemistry. Now, can it recognize host gas chemistry? To do that, initially we tried with simple binol. We found that a particular cage can bind with both R as well as S binol, but R binol was strongly bound. You see, R binol peak. Later on, this is not binol peak. Binol case peaks were quite broad because binol is smaller in size compared to the pocket size. So it was like moving inside the pocket. So peaks were not frozen. To get better peak, we substituted it with ethyl group so that tight packing is possible. After tight packing, we could see clear peak. When we took lambda cage treated with R binol, this is the peak for this methyl proton. But when we take same lambda cage treated with S binol, same methyl peak came here. R and S binol should come to the same place, but these two are diastereoisomer. That's why peak positions are different. Okay, but remember this peak is more uphill shifted, which indicated better packing or binding of this R binol. So R binol fits better, or this lambda cage binds strongly to R binol compared to S binol from NMR study. Similarly, opposite thing happened for this one, the delta cage also showed same, but it binds S binol stronger. Okay, and when we took R and S mixture, enhanced racemic mixture, and treated with the cage, suppose this one, delta lambda, then we found 70 to 75% is actually R, because R binds strongly. That's why majority of the binding cages, encapsulated cage, was R, and 25% was only S. That means the cage has recognition power to a particular enantiomer over the other. Okay, so we took racemic mixture of R binol derivative and S binol derivative. To that we added this cage. It recognizes encapsulated, or to a better extent or greater extent 75%, the R1. In S1 was only bound 25%. Reverse thing happened when delta was taken, and this was fully characterized by R and S. And this was the story. So you take one cage, okay, and then have mixture, it recognizes one particular enantiomer. Take the enantiomer more of this cage, that means delta cage, it will recognize the other one. So by preparing not only enantiomer pure cage with chiral pocket, we could actually show enantiomer selective recognition for a particular enantiomer. And this was appeared on the front cover of JAC's issue. Now, chiral compound or chiral cage will recognize a particular chiral enantiomer. It's not a new concept. We have shown that only enantiomer purity of cage is not good enough. Your pocket has to be asymmetric or chiral to induce chiral recognition. That is what we have shown and established here. But this is not known new concept. It is known in organic chemistry textbook. Now I will show you a new story. As I told you, Fujita used this ligand, which is symmetrical, and prepared this octahedral cage, which is achiral. It is highly symmetrical. Now, instead of this Fujita's ligand, if you design another symmetrical ligand, here no sigma plane is there. but it is having what is called like fan, a propeller type nature. You see this one, this one. It can also have in other way, anti-clockwise. Okay, so this propeller shaped ligand, if you use, then you can generate asymmetric pocket. So we actually treated this ligand with 90-degree acceptor. As expected, we got octahedral cage like this. But NMR was not so simple. This ligand is symmetrical. We have only one imine peak. But after formation of cage, I will show you, it showed 3 different imine peaks. That indicated, though we have a single octahedral cage, mass NMR showed, they have different isomers. Okay, and then what did you do? As I said, it can have delta, this kind of propeller arrangement, or in this way lambda. Now this delta and lambda form of this ligand can form different cages, all lambda or all delta in one cage. This cage is delta, this cage is lambda, they are enantiomer. So they cannot show different imine peaks. Enantiomer cannot distinguish NMR by NMR, okay? So they will have same imine peaks. But we can have another racemic mix, not racemic, mesomeric form, where 2 units have delta and 2 units have lambda. This is mesomeric. So this is also achiral, and this solution showed no CD signal. That means overall mixture is achiral. If we have 3 delta, 1 lambda in a cage, situation will be more complex, more imine peaks are expected, and the cage is expected to be chiral, or it should show CD signal. Now in this case, as I mentioned, we have 3 imine peaks, and that is because these 2 pair will show 1 imine peak because they are enantiomer. But here, because of 2 different forms attached to this, we can expect 2 imine peaks. So 3 imine peaks was justified from this. And CD also showed this one. You see, now you have a racemic mixture. Okay, now racemic mixture, how do we separate? We separate by forming diastereoisomer using an enantiopure compound or entity, anion or cation, whatever be. Form diastereoisomer. So one enantiomer will form diastereoisomer. They will have different physical or chemical properties, and then you separate them by means of any method, and that is called chiral resolution. So enantiomers need separation by diastereoisomer formation, which is chiral resolution, known in undergraduate textbook. But conversion of the racemic mixture to a single enantiomer by chiral seeding is unknown. So in this case, we got complex mixture of chiral cages, enantiomeric cages. Okay, but the cage mixture is overall achiral. When we added simple R-binol, because of the dynamic bonding between palladium and nitrogen, they can easily open up and fit a particular enantiomer to adopt a particular chiral environment inside cage and form a particular enantiomeric cage. Okay, and that was established by computational study and other method, that a particular enantiomer delta 1 stabilize R, and that's why we got compared to S1. That's why R1 was stabilized. So as soon as you add R-binol, you get a pure enantiopure cage, no mixture. So complete mixture is converted to one enantiopure cage. It is not that one of them form diastereoisomers and others to remain, and then you separate. No separation is needed. So this is a unique approach of converting racemic mixture to enantiopure cage. So it is reverse chiral recognition. Generally, an enantiopure cage recognizes an enantiopure entity But here, in presence of an enantiomer pure entity, a complex mixture of racemic mixture of cages formed enantiomer pure cage, reverse chiral recognition. Okay, this is what we found. When we use S-binol, we got lambda cage exclusively. When you use this one, we got delta cage exclusively. Both the cages were prepared and characterized, and these peaks are not originated from binol. They give peak here below 250. So these are due to this moiety as evident from UV absorption spectra. So NMR also now, you see NMR, it had 3 peaks here and it showed singlet. So one enantiomer pure cage was formed and it showed a single imine peak as expected. In next part, I have 10 or 12 minutes more, so I will speak on separation. Now, I have shown you in chiral recognition. Now, this is a very recent one where I will show you, discuss on separation of isomer. You see, anthracene crude oil is the major source of phenanthrene, and phenanthrene is widely used in industry. And for industrial use, we generally separate phenanthrene from anthracene crude oil. And this separation is very challenging in industry because anthracene and phenanthrene, they are isomer, they have very close physical and chemical behavior, and thus by simply distillation method or other method, it is very difficult to separate them, and that is very time consuming and expensive. So to see whether we can actually separate by any other method, to do that we use, as I showed you, that when we use rigid tetrapyridyl ligand with 90-degree acceptor, we got molecular barrel. So if you do not have this CH2, directly if you attach this dipyridyl amine here and here, you get a molecular barrel. But when we use this flexible CH2 group, we got an unusual molecular barrel, both. You see the conformation is like this ligand conformation. So these 2 pyridyl unit binds to one palladium, and this unit binds to another palladium, and this one binds to another unit. Similarly, another ligand shows similar binding and to form a boat. It is like boat surrounded by this aromatic building block, and this is highly soluble in water. Okay, now we checked its binding. First, this is the NMR of the ligand. But after formation in the ligand, all the pyridyl units are identical, so you have simple NMR. But once it forms this boat, you see 2 pyridyl units bind to one palladium, and other pyridyl, pink color pyridyl units are bound to 2 different palladiums. Okay, so that's why they have different complex NMR. All were assigned by 2-dimensional NMR. Okay, now this was also characterized by X-ray. X-ray showed the structure with almost 8.5 angstrom distance between these palladium units, so pocket is quite large. Interestingly, when we added gas like anthracene, naphthalene, pyrene, and phenanthrene, all polyaromatic hydrocarbons actually bind. This is the cage. If you add this one, B means phenanthrene. You see this one, anthracene shows slightly broad NMR. And then pyrene also showed peaks. These are all peaks due to guests. Guests are not soluble in water, but only in aqueous solution of cage. If you add these, they are soluble. And integration ratio also showed 1:1. This is for naphthalene. Okay. Now stoichiometry was determined from NMR integration, and in all the cases, it was evident that guests go inside. Now, competitive binding proved that this is the mass spectrum for this barrel. Crystal structure of phenanthrene as well as anthracene pyrene were determined, and in both the cases it was found that because of the flexible nature, it can actually expand though shrink. So it is very flexible. So it is adaptable cage. Okay, so it can adapt this one for perfect fitting and expand. You see, in this case, it is much wider distance. So in presence of gas, it can actually adapt the guest inside this one. So flexible cage. That's why it expanded in presence of gas. So the breathing nature of the cage was established by X-ray structure data. Sorry. Now, if you see, this is MB1, simple our boat. Treatment with phenanthrene, this is the NMR. And this is treatment of phenanthrene cage, encapsulated cage with anthracene. If you treat it with anthracene, no change. This is after treatment with anthracene, no change. That means anthracene cannot replace phenanthrene from the pocket. This is anthracene cage, anthracene encapsulated, which is broad. To that, if you add phenanthrene, again phenanthrene encapsulated cage is repeated, barrel boat is repeated. You see, these two are identical. That means it can easily kick out anthracene from the pocket. And this is not, again, phenanthrene encapsulated cage, pure phenanthrene encapsulated cage. If you take anthracene and phenanthrene and then add both, you see it only recognizes phenanthrene, not the anthracene. So competitive binding shows that phenanthrene binds strongly compared to anthracene. So in all the cases, we get phenanthrene encapsulated cages by competitive binding study. By UV titration method, we determined the binding constant and found that the phenanthrene case binding constant is almost 7 to 8 times more than the anthracene. Now, as phenanthrene binds strongly compared to anthracene, we use this to separate them from 1:1 mixture. So we took a mixture of phenanthrene and anthracene and then treated with aqueous solution of our barrel, both. You see, in this case, we are not using organic solvent. So aqueous extraction method to separate these water insoluble substrates from solid mixture. So now when we extracted this aqueous solution and then from that aqueous solution, whatever is encapsulated, we extracted by organic solvent and checked NMR, we found encapsulated entity was almost 99% pure phenanthrene and only close to 1% anthracene. So it is almost pure phenanthrene. So this aqueous extraction method, by using an extracting agent, which is a molecular boat, is an unusual method or entirely new concept. Okay, so it is like you have a mixture of phenanthrene and anthracene 1:1. Add aqueous solution of molecular boat, stir for some time. Phenanthrene will be encapsulated, anthracene will not be encapsulated. Simply you filter or decant, and then the decanted solution, you take aqueous solution, to that you add chloroform. Chloroform layer will have phenanthrene, separate it. Organic layer will have both. Again you reuse for this one. 5 cycles we used and so this purity of the phenanthrene remains same, almost 97% at the end. Okay, not less than that. So this is a unique and very new approach of aqueous extraction method using a molecular boat as an extracting agent to separate isomers which are having same physical and chemical behavior, to separate them from crude oil also can be used later on. But palladium is expensive. We need to use this concept to design more robust organic system so that for practical application we can use. This is under revision now. Last 3 to 4 minutes, I will talk on organic cage. Just one example, I'm not going to talk on details. In addition to inorganic or coordination cages, we do also work on organic cages using dynamic imine bond. So dynamic imine bond is also like reversible bond, like dynamic coordination bond. So you have bond forming, bond breaking process happens simultaneously, and finally thermodynamically most stable structure is actually formed. We know that for metal nanoparticle synthesis, top-down approach and bottom-up approach, both are actually logical approaches. Top-down approach means you start with 1 meter iron rod, divide into 10 equal parts, each one will be 0.1 meter. 0.1 meter, again you divide into 10 equal parts, each one will be 0.01. If you continue it 9 times, you will get 1 nanometer particle size, but it is very tedious method. Practically, it is almost impossible to get uniform size distribution and get exactly like that. So bottom-up approach is the most widely used approach. That means you start with metal salts where metal is present in metal plus oxidation state. Now reduce using reducing agent, it will form metal atoms. Metal atoms will agglomerate to form metal nanoparticle. But the question is how many metal atoms will combine to form a particle? 10, 1,000, million, billion, many numbers. If you have large number, then finally you will get precipitate non-nanoparticle. So generally chemists use a capping agent to cap this number of atoms so that it does not grow beyond a particular size. So you will get a particular nanoparticle of definite size. So many templates have been used by chemists like protein, peptide, micelles, polymer, dendrimers, etc. But it is very difficult to control the shape of such dendrimers, polymers, proteins, peptides. In many cases, their structures are also not properly known. But can we use discrete cages? Their shape, sizes are known. Inside them, if we can nucleate nanoparticle, we can control size. But metallo cages are highly sensitive to reducing agent, acid and bases, so it is very difficult to control their sizes. Now, what is possible? We thought we can actually design organic cage. So we use this trialdehyde with this diamine, we got this imine cage. We reduced it to amine cage, which is more robust, stable. Imine is not stable in presence of acid and bases. Now you have amine pocket. You can introduce metal ions to go. You have sulfur. You can actually bind soft metal ions like gold. So gold can bind this and this site. We check by NMR, and then gold ion can go inside and bind. Now you add reducing agent, gold ion will become gold atom. And if this process happens, gold atoms can combine to form particle. And if this process happens inside this pocket, then we can expect particle size will be close to the cage pocket size. And indeed, the cage size is 2.1 and our particle average particle size was 1.99. Okay, it is less than this. So synthesizing less than 2 nanometer gold nanoparticle was highly challenging, and in a very simple way we could achieve. We also designed many palladium, silver, other cages also using this approach. And then we use very old traditional reaction, nitro to azo. Nitro to azo, if you do this reduction using traditional method, using textbook approach, you will get azoxy, azo, hydrazo mixture. But selective formation of azo was achieved simply by using our cage supported nanoparticle as photocatalyst using 0.5 mole/% in just 2 hours time. In all the cases, these are isolated yield. Actually, yield was almost 100%. There was no byproduct, no side product or AB unreacted material. Okay, so we could get in most of the cases complete conversion and selective conversion of azo. So this is very brief study. We have also done mechanistic study and found that this is the actual route for this one. And then we have also reused it 5 cycles and there was almost no loss of catalytic activity. And the cage supported nanoparticle was stable even after 5 cycles and can be reused, as was evident from powder XRD. So in conclusion, I have shown you mainly on molecular barrel or cages as molecular vessels, and I have shown that such vessels can, chemistry of photochromic compounds in molecular vessel is entirely different from the traditional chemistry in glass vessel or inorganic solvent. In many cases, I have shown you that one can actually design cages, not only enantiopure cages are good enough to show chiral recognition. You need to have pocket which is asymmetric or chiral to have chiral recognition. That was established by designing asymmetric chiral tetrahedral cages to show chiral recognition. First time we have shown a reverse chiral recognition phenomena to convert enantiopure racemic mixture to enantiopure cages because of the dynamic nature in presence of a chiral compound as chiral seeding. And this approach has been already used by 2 groups in last 1 year after our approach was reported, and they have shown that in case of imine cages as well as in lanthanide cages, they could get enantiomer pure cages by applying our newly developed approach. We also do work on organic cages, and for nucleation of nanoparticles of control size inside the confined pocket, and then use them for photocatalysis and heterogeneous catalysis of organic transformation. I have not discussed much on this topic. And let me also acknowledge my students who have done this work. Pradeep Howladar work on first part of my talk, that means spiropyran encapsulation in molecular vessel. Bigganeshwar Mondal worked on nanoparticles in organic cage. Rupak Saha worked on DASA encapsulation in cage and chemistry of donor acceptor stain house adduct in cage. Arpita worked on the last part of my talk, that means separation of phenanthrene and anthracene. And Ennio Giangrande is a crystallographer who helped us in collecting synchrotron X-ray data for our molecular barrels and cages. ACRB for financial support, and thank you for your kind attention.
Yeah, thank you. The forum is open. Audience, any questions, please post on the YouTube link that has been provided to you, which I will transmit to the speaker. Anyone has questions, please? Yeah. There is a query from Samiranjan Mishra.
Yes.
Can we expect other side product while using mixture of both lambda and delta isomers?
Side product?
Yeah.
Lambda and delta isomer means? Okay, so lambda and delta isomer of the ligand or cage? In case of cage formation, we did not see any other geometry except an octahedral cage. So an octahedral cage one can expect from NMR. We found delta lambda and delta lambda, that means mesomeric form. All three were formed from NMR study we found. Other than that, there was no other byproduct, like no polymeric form or no other geometry. In fact, other geometries are not possible. If we use rigid tripyridyl ligand, then only geometry is this octahedral cage, and another geometry that we call double square is also possible, but in that case NMR nature will be different, not symmetrical. That can be easily distinguished by NMR. So in our case, we got only this symmetrical octahedral cage.
I think that makes him to get into that. There is another query from Paltan Laha, is one of our students from the institute. Is there your presentation and your work has been based on mostly on palladium? So is there any speciality for palladium?
Yes.
Yes,
Good question. Good question. Okay. So basically, we always use palladium, platinum. Some groups also use iron or ruthenium. Okay, you can use late transition metal, and the advantage of using palladium and platinum is the following. Palladium and platinum in +2 oxidation state will only exist in square planar geometry. It will never adopt tetrahedral geometry, it will never adopt octahedral geometry or pentacoordinated geometry. So we know its history, so it will automatically be square planar. So if you know the square planar geometry, you can block 2 sides, or you know only 4 sides are available, so designing is easy. Number 1, if the bonding between platinum and palladium with nitrogen is dynamic in nature because of soft hard interaction or moderately hard nitrogen donor bonding is dynamic. So self-assembly can be easily done. If you use donor like sulfur, then it will form strong bond. So you cannot get dynamic mixture. So you will get kinetically inert product. Okay. So because of the dynamic nature, we use platinum palladium with nitrogen donor ligand and its rigid geometry. If you use copper, nickel, and other metal ions, they have variable coordination number. So you can get mixture of product, difficult to control a particular geometry. So you may end up with coordination polymers.
I think, Professor Mukherjee, I think there are no more questions from the audience. So I take this opportunity to thank you for a wonderful presentation and giving a landscape of efficacy of confined medium for various applications, especially isolation of isomers, that is a separation of isomers, and also different properties like thermochromism in the solid state. Especially going through the spectroscopic techniques and also the crystallography techniques together. It's a wonderful presentation. It's eye-opener for many people to just have the systems, both solution state and solid state together, how a beautiful chemistry that can be evolved in the long run. Thank you once again, Professor Chatterjee, for your presentation.
Thank you.
So now we'll move on to the next presentation of the day. Again, another well-known personality of the chemists working in the research areas of CH functionalizations from IIT Bombay, Professor Devabrata Maiti. Probably I don't have to tell much about him, as name itself reverberates many young Indians in the chemistry, organic chemistry areas. He is one of the very young himself, young person pursuing research, particularly focusing on the CH functionalization. He has a very excellent academic career, with a PhD from the Department of Chemistry at Johns Hopkins University, and then did the postdoc under another stalwart professor. All of you have been aware, that's Stephen Buchwald. And then he started his independent career at IIT Bombay as an assistant professor. Today he has been the full professor at the same department at IIT Bombay. And he is the recipient of various awards, CRSI Bronze Medal, and Sun Pharma Science Foundation Research Award, Professor P.K. Bose Memorial Award. And apart from that, he has been Humboldt Research Fellowship for Experienced Researchers. It is slightly different from the postdoctoral research fellowship. And he is also the fellow of FRSC, fellow of Royal Society of Chemistry, NACI, Scopus Young Scientist Award, Innovation in Engineering and Physical Sciences. He is also visiting faculty at Tokyo Institute of Technology, Japan, and Federal University of Minas in Brazil, and also University of Pavia at Italy. And he has also been INSA Young Scientist, and he received also CRSI Young Scientist Award. Apart from that, A.V. Ramarao, who was again another stalwart of the country in chemical sciences, former director of IICT. He was the Young Scientist Award of AVRA. And he received also IIT Bombay IRCC Young Scientist Award, and most prominently NACI Young Scientist Platinum Jubilee Award. Coming to his accomplishments in the academics and research, highlighting his contributions. He has been the editor, having lot of editorial appointments. He is associate editor, the Journal of Organic Chemistry, the most premier journal in the organic chemistry. Editorial board member of the Chemistry European Journal, Academy Advisor Board of Advanced Synthesis, and also editorial board member for the Tetrahedron Chem, editorial advisory board of the Organometallics, International Advisory Board member of Chemistry and Asian Journal, International Advisory Board of Asian Journal of Organic Chemistry. Further, he is in the Advisory Board of Catalysis Science and Technology. I think at this level, the various membership associateships and then the memberships with various boards of these premier journals itself explains his serious research orientation. And now, with this introduction, I would like to invite Professor Maiti to speak on his topic, Enlightening CH Functionalization. And you all can see that his title, he nicely put it, Enlightening. I'm sure that is going to reflect in his presentation. Professor Maiti, please.
Hi, hello everyone.
Yes.
Can you hear me?
Yeah, please go ahead.
Yeah. So it's been a pleasure to be here. Thank you so much, Dr. Pedireddy, for your sweet and kind introduction. I hope all of you are enjoying this exciting conference. And although it is an e-workshop, I wish I could visit sometime soon, all of you. After the exciting talk by Padhasarat, I think it's time to take some of the palladium complexes and try to see if we can do some application of this method. Okay, let me start sharing my slide again. Can you see my slide? Can you see my slide?
Yes, yes.
Okay. Again, let me thank the organizers. Let me thank all of you. I mean, quite a lot of friends and close associates, well-wishers over the years, and I think over the decades. We have, all of the colleagues at IIT Bhubaneswar. It has been a pleasure to be, although online, but I wish to share some of the ongoing research work in our laboratory at IIT Bombay. Well, we work on quite different domain. Today, mainly I'll focus on the carbon-hydrogen bond functionalization, and that is one of the topics that we have been discussing for last several years. I think one of the biggest challenge that our society faces today is to provide simply the simplest possible solutions for complex molecules or for complex problems. As a chemist, as we know that we have our domain-specific problems. Each domain, as Padhasarat very nicely demonstrated through his work, the challenges in his domain. Now, we wish, or we hope, of course, collectively with the world's scientists, to promote synthetic transformations which will be useful in industrial setup. Again, what we would like to promote is the transformations or the organic reactions which will be useful to make molecules in tons of scale. That's the dream. The molecule must be important. Of course, let's say pharmaceuticals, agrochemicals, perfume industry, and for perfume industry and so on. Now, if you are looking at organic molecule synthesis, often you'd need, not always, I would say often, you'd need metal centers. That is where we come into the picture. So for synthesis of organic molecules or new organic molecules from simple starting materials, we use metal. Now, as you know, metal cannot just float around in your solution. It gets solvated or it gets associated with ligand. Completely free of coordination of metal center is very difficult to get. Usually it will conglomerate or aggregate to give you nanoparticle, and other problem will be associated with it. To keep the metal in the reaction media, you need ligand. In these cases, or in this domain, we are calling them as directing group. Again, the DG or template, whatever word I may be using throughout my discussion today, it is simply ligand. Often you will see that we are using even monodentate ligand, bidentate ligand, but what we may not be using way too much is the tridentate or tetradentate ligand. Simply because if you are using those bidentate and tridentate ligand, then metal center is not having enough coordination site left to do the chemistry. Okay, that is understood. What we are trying to achieve? We are trying to achieve a low coordination number for the metal center. By doing so, we'll have a number of vacant coordination sites on the metal center. Now, on those vacant coordination sites, you can do chemistry as you wish. Okay. In our domain, we take organic molecule. This is a cartoon diagram of an organic molecule, right? I'm trying to say here that 6 different centers are there. Okay. Let's say 1, 2, 3, 4, 5, and 6. Now, all these centers are looking almost similar or same exactly, right? The challenge that we as a community are trying to address simply is, how can you selectively do a reaction at any desired position? For example, at this position. How can you do that? Well, if any of you are familiar with this domain, you would know by now, at least over the last 2 decades or so, we have seen tremendous growth in the approaches, in the strategies by which this sort of selectivity can be achieved, and the reactivity is, of course, becoming quite exciting. So what we are looking for is a ligand metal complex which will participate in the activation of a desired position, and this metal will then be inserted and form bond between the carbon and metal. So in other words, it is going to be an organometallic complex that is going to be formed between this carbon center and that metal center. Now, how can you differentiate between this carbon center and that carbon center and that carbon center, or even these ones? You can do that by having many design of the so-called linker or whatever effect you want to bring in here. So the ligand metal is one part, organic substrate is another part, and this is another part, this linker. Okay, I'll discuss each of them in the subsequent slide. Now, this sort of approaches, if you want, you can look at the enzyme. Well, that is where we start in terms of getting some sort of similarity. You see, this is a cytochrome P450. This is a very, very famous enzyme. You have porphyrin ring, okay, and you have an iron center. In front of this iron center, iron porphyrin ring, there are zillions of, or not zillions, there are many metalloenzyme you can take. It's a similar arrangement. This sort of metal ligand is porphyrin here. And then this is the organic substrate, one of the organic substrate for cytochrome P450. What you see is right in front of this metal, this center is located. So therefore, this is the center which is going to get activated. The CH bond at this center is going to get activated. If you look at even these, or any other position which is over there, these are not going to be activated because it is not right close to the metal center. Okay, but you know how much price we pay or how much designing enzyme has to do to reach to this stage. Of course, we take it for granted, just like our life on Earth, we take it for granted, right? But it won't, as we know, a little bit deviation from anything, it's going to cost us dearly, like our health, everything, like mental peace and everything. But over here, what is really working out in favor of enzyme is there are zillions of effect, I would say, definitely. Weak interaction, electrostatic interaction, hydrogen bonding interaction, pi stacking interaction, London van der Waals forces, London dispersion forces, whatever you can perhaps think of from the physical chemistry perspective or from the physical organic perspective, all the forces put together, it ensures that this organic substrate will be placed right in front of this active site so precisely so that only one center can be activated. Right? So that is for enzyme. Enzyme can do it, right? Enzyme can do it for only one substrate or maybe another two, three, few substrates. But enzyme cannot do this for a variety of substrates. That's the big challenge, right? Enzyme perfected it for one substrate and one substrate only, right? Am I audible?
Yes, please go ahead.
Yeah, okay. Yeah. So organic chemists actually are challenged how to take this take-home message from enzyme and implement in synthetic setup. It's not going to be easy because for organic chemists, you need, or we have, different organic substrate. The moment you change the organic substrate, things are going to fall apart. The effects, that weak interactions or all the effect, the cavity effect, all the effect that we know is effective for enzyme is no longer going to be useful, right? So this is where the strategizing in the synthetic setup becomes most important. For example, you see this simple organic substrate, leucine. It's a very important amino acid. Every amino acids are important. Leucine is a very special one. You have this carbon center 1, 2, 3, and 4. 4 different carbon centers. Now, if you are asking me how to selectively do the reaction at these positions, okay? So these nearby positions, who are nearby to the heteroatom, these positions we will be calling the proximal position or nearby position. These positions, the highlighted one, I would call often the distal position, means it is far away, distant basically, far away from the functional group. Now, if you again look at the literature, so-called C1, C2, and C3, maybe you would be able to find out a way to do these reactions at those positions. But what you may not find, or actually will not find, is how to specifically functionalize this C4 or so-called delta position, alpha, beta, gamma, delta position. Now, if you take this substrate itself, of course, you can see that amine is there and carboxylic acid is there. It's a good ligand. You can say that, oh, it is a good ligand. Can I not use my metal to do the chemistry? Yes, you can add the metal, but it's not going to be work out to give you the desired functional life, because the mode of activation is not going to work out at this position. If you add any metal, in particular, we'll be using mainly the palladium, you will not get any functionalization at this delta position. So what we have done, we have taken this substrate or any analog of this substrate, which is a crystal structure one. It's not directly this one, it's an analog of this substrate, where we have taken this amine and added this pyridine carboxylic acid. Okay, pyridine carboxylic acid. This pyridine carboxylic acid, once it is added with this amine, now this is a good bidentate ligand. This ligand and this ligand. This nitrogen is this nitrogen. And this pyridine carboxylic acid nitrogen is coming from 2 picolinic acid that we have covalently attached. Okay. Now what we have a metal center and a bidentate ligand. Then this, due to the 6-member preferred activation as well as insertion, we see that metal is inserted at this carbon center. That means this carbon center. This is the crystal structure you can get. Again, this is not the exact substrate here, but it takes the message home that you can activate this terminal delta position. Okay. Once the metallation is done, if you are studying the organometallic chemistry, you can then plan your reaction the way perhaps you want. Not always you want many different things to be happening. Indeed, in this case, many different things are happening. It cannot be true all the time. You have to do significant amount of research. This is what it is about. So you find out the suitable reaction condition, you design, redesign, you plan your ligands, you plan your substrate. Basically, you keep on iteratively doing it. But the strategy remains very simple, that you want to closely associate the metal center with your desired carbon center. For that, you have to have a perfect designing. Once you are able to meet your ligand at your desired carbon center, once this organometallic intermediate is formed, you can do the reaction. In this case, we have taken aryl iodide. I did not write it here. Aryl iodide, you can get the arylation reaction in this position. If you are taking many other different reagents, of course, you can do many other reactions at this position. We have been doing quite a lot. I will not discuss all of those, but it works. Not all of them are also reported. Quite a few of them we have reported already. Again, what you need is a precise locating, okay, or positioning of the metal center within your organic molecule. Well, if you do not have a metal center in pure, like let's say metal-free organically organic way, there is no way to do these reactions. So if you have a question why we need metal, because without metal, forget it, move on. There is no way you are going to do a variety of things, wide variety of things. You may be lucky in 1 or 2 cases where metal-free things or some of the things can work out, specifically if it is a completely biased substrate. But most often, without metal, well, forget it. And this is particularly why we have seen, increasingly synthetic chemistry, so to speak, let's say organic chemistry, of course, organic and inorganic chemistry is intertwined. They are linked. The ideas of organic chemistry are limited with the thought of using metal. And that is where, again, the inorganic chemist can make a difference, can bring those things which perhaps cannot be possible without using metal. Judicious choice as well as design, of course, of metal ligand complexes is going to be fundamental part of organometallic reaction and enlarge the organic reaction, right? So this is what we have done. You have seen few over here, quite a few things works out. I am not going to get into way too much of details, but again, at the delta position, you see the reaction works. At the delta position, things are working out. Okay, but what I really wanted to take your attention to is the reaction condition. You see, you need silver salt as well as 100 degrees C. This is not going to be ideal. This is not going to be something you are going to like it. If specifically, if you are looking to do this reaction in industrial scale, you want to make these reactions in, let's say, kg scale. I mean, then 5 kg or 10 kg of the silver salt waste you will be getting. I mean, no industry is going to touch it. And the temperature is very high, right? How are you going to, reduce the cost if the temperature is such high? In other words, if you can do this reaction at room temperature, it is going to be much preferred in industry, much preferred, because per degree centigrade increment of temperature in industrial scale is going to cost you dearly. Okay, I'll come back to this point afterwards. As you may be knowing that we have been also working on the sp2 carbon hydrogen bond functionalization. Of course, it has to proceed with the activation. These reactions, I would say, are working out quite nicely. Of course, there are limitations, and that is where we as a research group and all of us, all of the scientific community, trying to see how can we contribute to make these transformations better and more useful. Okay, what we are taking? We are taking an organic molecule. You see, this is an organic molecule. It's a cartoon of organic molecule. with arene. In the previous slide, you have seen the aliphatic, right? Now, in this case, you see the aromatic molecule. Okay, and this is apparently the linker. Linker means between the arene ring and the template. Template is the ligand or directing group. T means template, or DG. DG means it's the same thing, or the ligand basically. T, DG, L is the same thing. Okay, depending on slide to slide, I might be varying. I should make it uniform. Anyway, so what you see is you take arene, you take any organic substrate, that means this is reflected in here. As long as you attached or you have attached this template ligand, this you see is a monodentate ligand. In the previous case, you have seen a bidentate ligand, 2-picolinic acid or 2-picolinamide. Here you take a monodentate ligand, like biphenyl pyrimidine. And then by virtue of the design and overall disposition, what you see that you do not really touch this position or that position. You selectively activate and functionalize this position. Okay, so that is what you see. Irrespective of the linker length and the type of linker, you see, type of linker. You can put different substituent as well. You can do the reaction at this position. See, the other position remains intact. Only I'm showing very little things here. But once again, I think you may be noticing that the reaction condition is far from ideal. Of course, there are many limitations. I'm touching upon two limitations here. One is the silver salt. You need 3 equivalent and very high temperature or relatively high temperature, right? Now, of course, the reactions are working. You see, this is an olefination, alkylation, acetoxylation, cyanation, you name it. Now, if you are again looking at the textbook, let's say bachelor, since I realize that many of you are in bachelor or in your masters, and so I think we studied in our textbook. You know, I do remember in my college days where we studied in the textbook saying that electrophilic aromatic substitution will be possible at the ortho and para position. Depending on the arene ring substituent, you may get the mixture of ortho and para product. At meta position, you are supposed to get only the nucleophilic type of reaction. Well, you look at the variety of reaction here. Do you think the meta position is biased by those statements that we studied maybe in our undergraduate, in our bachelor days? Probably not, and I would say definitely not. So this template over here, which will hold the metal at this position, this nitrogen will hold the metal and activate this position, will and definitely, you know, age in these cases, giving an opportunity to promote this reaction selectively at the meta position without touching ortho and para position. Of course, there are some selectivity issue. It's not like perfect. These are the best one. But again, this is something we are trying to overcome while discuss today. We would like to have further better yields and further better selectivity. And we would not like to have really the silver salt and very high temperature. Okay, moving on. We have been also designing the ligand. This is another ligand, you see. This is the nitrile-based ligand. This nitrogen will bind the metals. But this ligand, you have to attach with the organic substrate. Once you attach this ligand with organic substrate, what you see that this position is getting functionalized, or the para position, see, the para. So this so-called C4 position, C1, C2, C3, of course, remained intact, only the C4 position getting functionalized. So it is the ligand controlled reaction or functionalization. I agree that the yields and selectivity perhaps can be better. Perhaps the selectivity, again, these are the best ones. We always try to put the best fit forward. These are the best one in the original work. If you see, the selectivity in many cases will not be even this great. it. Once again, you need the silver salt and high temperature. I think we understand the reaction mechanism a fair bit, okay, by now. What we find that you have the ligand for metal center, in this case it is palladium, and you have template. Okay, this is the design template. All you have to really design it. I'm not getting into way too much of details, but anything you would like to change at this end or on it is not going to be taken positively by the overall functionalization. Any change you want to make is going to be costing you, both in terms of yield and selectivity. That means yield and selectivity is going to get down. So this is your organic substrate, and this is your template. This is the nitrile, this one, and the metal will bind right over here. You see the overall positioning? It's perfected so that this bond is going to get activated, right? Now, you remember the enzyme I was talking about? Just one of the examples, right? You can take any other example in the world you want, okay? But so this is precisely what looks similar to the enzyme, I would say. That enzyme substrate is placed right in front of the metal active site, which is over here, okay, in this vacant space. So this design is such that metal will be placed right over here and it will be activated. Okay, that's it. Once you are able to activate it and put the metal precisely at this position without touching these positions, those would require again fine tuning and the designing of the ligand. Okay, we have done tons of it, hundreds of it, and we have zeroed down on this template. Okay, once metallation is happening, you can basically take a textbook and try to see what may work out. Well, we have been trying to innovate in the reaction condition, and we find that indeed not everything is working, but good enough to survive, I guess. Good enough to work and have fun on this domain. Things are working quite nicely. And we get the functionalized product at the C4 or the para position selectively. One of the limitations certainly is, as I was explaining, in every cases we need silver salt. Silver salt, after reaction, the waste is going to be difficult to deal with. Okay, so silver salt comes into picture into the CH activation, although I did not show it more precisely because there is a silver palladium cluster apparently is involved in this computational study. At least in computationally, it has been proposed that it's a silver palladium cluster that is reaching to this position. Okay, anyway, and also for regeneration. So this is palladium 0 to palladium 2 oxidation. Okay, you need the silver salt. Usually silver nitrate, silver, silver carbonate, this sort of salt is used for this reaction. Okay, moving on. What we have been then doing over the last 6-7 years is to develop ligand or template or DG. Okay, here I call it DG. Okay, so over the years we have been designing this DG or template. In this case, if you take this template, you will activate this position. Actually, this is the one which we prefer at this point. It works better than anything else. Okay, so this template, which is a biphenyl pyrimidine-based template, which can hold the metal center precisely better than the cyano. It's a better sigma donor as well as pi acceptor. It will hold on to the metal more precisely. This is the one I would say the champion right now, not any others that is shown in here. But nonetheless, once you add this ligand with the organic substrate, you will get the activation at this position, at this C3 or so-called meta position. If you are attaching any of these ligand, you would activate this position or C4 or the para position. That's it. That's simple as that. Of course, to arrive at this ligand and continuous development is necessary. Hundreds of systems, if not thousands, we have been working on and trying to really come up with the one which is going to sustain and give you give you long-lasting impact on both in terms of the functionalization ability as well as ability to give the reaction under sustainable conditions. Okay, all these cases actually, one of the major limitations, you have been noticing that you need to introduce the ligand or template or directing group, okay, inside the or within the organic substrate. You take the organic substrate, you have to attach it and detach it. Similar to what you know as this protecting group strategy, protection, deprotection, right? So 3 steps for doing one reaction. I mean, none of us are happy with it, but there is no other alternative. You are talking about positional selectivity and many different reactions, versatility, and you are looking at production of molecules which has value. Could be agrochemical, could be pharmaceutical. At least it gives an opportunity to diversify simple molecule to get very, very complex ones. If there is no other approach, I think still it's okay. Still it is good enough. But inside out, we are not really happy. Okay, none of us are, because we want you to take the simple organic substrate without doing anything. You should get the selective product. Okay, or in a way, let's say again with the reference to the enzyme. Enzyme does not introduce the template or directing group with the organic molecule. It just places it perfectly. But for synthetic chemists like us, we needed to attach the template with the organic substrate. Well, this is a constant fight, how you do that. Okay, today I'll show you briefly one approach where we have taken the arene and we have constituted in situ method. Let me take you for a moment. So biphenylaldehyde as an organic substrate to start with. You take amine as a ligand or template directing group. Okay, so this NH2 and CHO, NH2 and CHO will in situ give you imine, and this nitrogen will hold your metal center. And if the designing of this ligand is perfect, then you will be able to activate a desired position. If that's not simple, I think so. So you take an aldehyde, you take an amine. Of course, it's a lot of designing that has gone into. I'm not getting into there, but you can see once you are focusing on a field for, let's say, 7-8 years, at least 7 years now, at least we are focusing and trying to develop. We have the understanding and of course the resources to reach the meat or to reach the need where we can take the amine substrate fully designed along with the ligand, combine this with in this aldehyde, despite having 5 carbon center here and 4 carbon center here. So total 9 centers you can get the reaction. If you look at 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different centers are possible for the desired, let's say, in this case, olefination reaction. But you see, it happens precisely over there. Again, for a variety of substrates. Again, enzyme, in all these cases, I'm not showing the detailed substrate scope, but it is true that the scope is pretty general. Of course, there are, again, no methodology, no strategy is foolproof. There are many limitations. I will not be able to discuss all those, but at least on the face of it, it looks like it's working quite wonderful. Okay, despite having 9 different carbon centers, only one center is getting functionalized, and that is that one. I think this is exciting. We thought it is exciting, and you can change also from aldehyde. You can take amine here, and you can take aldehyde here. Just the switch. It works. Again, I did not show you all the things, but you can refer to the work. So it works. So you can take an aldehyde, add an amine. You can take an amine and add an aldehyde. Again, we need to improve it further, but it works for quite a lot of cases. The thing that I was trying to draw your attention is it requires the silver salt and copper salt super stoichiometric amount. So you do the reaction, it looks like oxidant is taking care. Can we replace this with air, oxygen from air? Then you don't have to add this. Can we do this reaction at room temperature? So all these highlighted part, can we really do it? Okay, and that is where we have been thinking to do these reactions in a little bit different way. Now that we understand the reaction mechanism to some extent at least, what we find is, as I was telling, silver salt or copper salt is required at this stage as well as at this stage. The first stage as well as the last stage. Now, if we have a ligand palladium complex, this is the starting material, and you add ligand with a ligand palladium complex. If you take an organic molecule, okay, of course, you are going to get an organic molecule, palladium inserted intermediate. But if that ligand palladium complex can absorb light and can promote this activation step in a much facile manner, perhaps then we can do these reactions at room temperature. Again, the photoexcitation of the ligand palladium complex is going to be key. Subsequently, you can have your organic molecule coming in, interacting, inserting, eliminating, giving you palladium 0. So this part is, textbook, this part. This is done many times with many different systems. Organic molecule attaches with the ligand, with the metal, inserts, eliminate. So this is okay. What we are trying to influence is the first step as well as the last step. First step, ligand palladium complex should be using the light to make it facile or very mild. And the last step, oxidation of palladium 0 to palladium 2, need to be done without using silver salt. Both the first step and last step require silver salt, but by doing this way, we may be able to get rid of silver salt. Okay. Today, actually, I'm very happy to tell you that yes, indeed, we are able to do that. Here, a photocatalyst is required. Photoexcited intermediate will be formed. Okay. That photoexcited state can oxidize with the help of oxygen or superoxide in situ generated. This can be oxygen or superoxide, doesn't really matter. Overall, this palladium 0 can be oxidized to palladium 2. If you do not use photocatalyst, this oxygen or superoxide itself is not efficient. The potential wise, it is not matching to oxidize palladium 0 to palladium 2. So essentially, we are helping the last oxidation step perfectly to make these reactions happen. Okay, let's look at. So the thermal reaction, this is the thermal approach. Well, this work is not by us, but somebody else. To start with, they have reported the thermal reaction. I have discussed some of our work where we are doing thermal reaction. So they have shown, this is Professor Jinkwani, huge group from Scripps, one stalwart in this domain. So they were able to show that the need, just like those different functionalization that we have discussed at sp3 and sp2 position, which will require silver salt, okay, super stoichiometric amount and 100 degrees C. Now this thermal approach gives you product as you see in here. In all these cases, you see, there is a selectivity issue and severe selectivity issue. Okay, as I explained how the first step and the last step can be perhaps influenced by light. Now what we are seeing that in place of silver, we don't have to add anything. We can use air. You are doing the reaction in air, right? That's good enough. Here is good enough. And we can do these reactions at room temperature, where thermal approach would require 100 degrees C. But most importantly, the selectivity. Look at the selectivity. Thermal approaches were giving mixtures, but the photocatalytic approach are giving exclusive, that means only one product formation. Well, this is the brainchild of two of my co-workers. Simonto Guin is in the job market. He's a fantastic postdoc, former postdoc at this point, a fantastic researcher. If any of you are a recruiter and looking for a really, really fine chemist, I think you will not be disappointed to hire Simonto. Okay, so he's in the job market. Again, if anyone is listening, you can trust my word. I can vouch that he's one of the best perhaps we can have in our country. I mean, I can go on and tell that. Well, I wish him all the best. What we were able to show that this photocatalytic approach can give you an opportunity, okay, to do the reactions in a clean fashion. That's what I was telling. You need a photocatalyst, you see, fluorescent. This is the cheapest reagent you can perhaps get in terms of photocatalyst or anything perhaps. You need, as I was saying, you need a ligand for palladium. This is the ligand for palladium. These type of ligands have been used before, okay, and it works. You see, in all these cases, you get one product. Of course, some cases you see the para product, some cases meta product. These are the substrate controlled reactivity. Depending on the substrate, you get the product. But most importantly, you get one product. It's a substrate control, innate reactivity. One product. That is wonderful. I'll tell you how to get the other product or override the selectivity. The most critical substrates are the heterocycles. Anyone working in synthetic methodology, organic, inorganic chemistry would know functionalized heterocycle is a difficult task. It's a untamed horse, right? It comes from many reasons. One of the main domain or reason is specifically if you are using metal, ligand metal or heterocycle metal combination can be difficult to withstand and will end up giving you trouble. Okay? But quite exciting for this, the reaction condition is so mild, again, at room temperature, no more 110, 130, 90, 100 temperature. At room temperature, with very little of photocatalyst, you can do the product formation. Most importantly, the selectivity. The reaction condition is one thing. Of course, we would like to make it industrially viable slowly. Still, there are components we need to improve, but of course, we don't need silver salt anymore. We don't need high temperature, but the major focus or major importance of the work or this sort of work is that you can do this reaction very effortlessly by using simple setup. It's a CFL bulb, household bulb. This is the light source, this is the photocatalyst, and at room temperature. Essentially, you take a reaction vessel, you add everything, that's it. You let it go. You don't have to do anything. You just start it. That's it. And you get one product. I think we have every reason to be excited. Okay. Let me move on from there. We can get one product from these heterocycles. These are exciting days. We can also diversify this product formation to get the simplest looking natural product. Most importantly, we choose the natural product in such a way so that we can do this reaction in one step to demonstrate the capability of this transformation. One step, one natural product. I think I like it. Okay. I think you should also like it. Again, the natural products are very simple in these cases, but nonetheless, they are natural product. You start with phenol or anisole or, salicylic acid sort of derivatives or, catechol. You get one natural product in one step and the simplest possible reaction condition, I would say at this point, at least at this given point of time. There is nothing simpler than this. If you look at the literature, these complexes, many of them would require 2 to 4 steps. 3 to 4 steps, I think, would be the norm to synthesize it. You can further diversify or synthesize drug molecules. Well, this showcases further that the strategy is applicable for complex setup. So, and if you are in the domain of synthetic methodology development, you have to show that, unlike, let's say, nature's enzyme, which is working in one molecule, here it is working for a variety of molecules. You see, each of these molecules are different. Still, it works. Again, this is the challenge that synthetic chemists are facing. You have to do the reaction in many, many, many different molecules. Okay, and it works out quite well. Of course, there are problems. You know, I don't want to give an impression that all the problems we are trying to solve is solved. There are problems which will take decades to study and solve, but the promises. Well, of course, just the promise cannot be good enough. You have to deliver with respect to time as well. I think this is at this point both the delivery and the further future promises that it holds. I think we are pretty excited in that direction. Okay. So how can you explain this selectivity? Many of you are maybe from physical chemistry background, physical organic chemistry background. Of course, there are many ways to address this selectivity. Well, we are synthetic chemists. We try to look at it from aspects which we could understand or correlate or relate very easily. One of such parameters is this Fukui indices. It is not that difficult. It is in-house calculation we have done, simple calculation. Essentially, you take a substrate and you get, at the end, you get this Fukui indices. This is the nucleophilic parameter. So this is the center in this case, which is most nucleophilic. This is the center in this case, it is most nucleophilic. But the nitrobenzene you see, this is the position, meta position or C3 position is most nucleophilic. Okay, so the nucleophilic position is essentially getting functionalized. Okay, you can calculate, you can figure it out, but most importantly, other centers, even in cases where there are not much difference in two centers, we can differentiate the reactivity. Okay, I think that's the fun part, or that is part of the fun. If you do not want the substrate controlled reactivity, like your arene controlled reactivity, innate behavior of the arene is not controlling the reactivity, electronic or steric controlled reactivity. If you want to override it, all the biases that you have, maybe in an organic molecule, never you are dealing with benzene, always you have a substituent. So if you want to really overcome the innate reactivity or inherent reactivity, you can introduce directing group if your molecule allows. In these cases, by introducing simple directing group, acetanilide, NaCOMe, for example, you can get the ortho. Okay, that is simple. You can get the meta product if you are introducing those meta directing groups with the organic molecule. Again, the most important thing is the yields are better. Selectivity is much, 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 much better than the thermal reaction. Most of the cases. Okay. Essentially 30:1, people would say one product, because if you look at the NMR limit of detection, I think that's it. Okay. You cannot detect it in NMR. If you are introducing the para-directing group, I have discussed in the previous cases, 5-7 slides back, you can get the para product. So essentially, you are having an opportunity to control and do the functionalization. You have innate reactivity or the substrate control reactivity, and then you have the ligand control or the template directing group controlled reactivity. Yes, you need to, kind of control or optimize your photocatalyst. These are very cheap photocatalysts. Still at room temperature, still the bulb in our house, what we see, household bulb, simple bulb in in the kitchen, drawing room, bedroom, we use simple bulbs can do the chemistry. Okay. When we take a substrate where potentially enantioselective reaction can be done, it did not disappoint us, at least in this case. It gives moderate to good levels of yield and enantioselectivity with this photocatalyst. Now the photocatalyst has changed. Okay, photocatalyst has been changed. Okay, I'll briefly discuss another. I guess I have another 10-15 minutes. Is that correct? 10 minutes at least I have.
You have about 8 minutes.
Okay, fine. I'll finish with that. What we find that these ligand palladium complexes are the key. It's a trimeric complex. Why photochemical reactions are selected? Why the selectivity is not lost, unlike thermal reaction? And that is due to the fact that these reactions are slow and selective. Again, I'll come back in a moment. So the blue color here are the photo reaction. It's slow, always slow. We have done it for at least, I think, 50 different substrates. We have done total 150 substrates at least. But all the cases, photo reactions are much slower than the thermal reaction. And we have a series of ligand metal complex with sort of 2-hydroxypyridine. Always it gives this trimeric complex. So what is happening here? This trimeric crystal structure that you have seen in the last slide, it can be photoexcited, intersystem crossing. You get to TU1. Then you have an opportunity to have a barrierless transformation into the monomer. This part, if you are doing thermal, okay, you have to put this energy to reach here. Okay, that energy thermally I don't have to put, and also of course the total, and from here only for the photo reaction I have to put this much energy, only that much, which is good enough to do in the room temperature. For the thermal reaction, this whole profile you have to put, or whole 45.3 you have to put. That is making the difference. Okay, so the photochemical reactions are least energy demanding in these cases, the way the overall reaction works out. The pathway, this part is okay, you don't have to worry about that. But this part, only 17.7. If you are talking about thermal, you are going to take that much. Okay, that's the difference. This is again the same thing I'm saying in a different way. This is the thermal pathway in blue. You have to give this one as well as that one. So total 45.3 for the thermal. You can have triplet preserved throughout. That is going to cost you more often. And monomer is the one which is the one doing the chemistry. Trimer to the monomer picking up doing the chemistry. Okay, for the photo reaction, you reach here without paying any price. You reach here, as I show here in the last slide, you reach here without giving any price. You basically attain it by completely alternative mechanism or alternative pathway. Thermal pathway, there is straight, the highway. Okay, and highway is costing through its toll. Let's say there's a check and balance there. So this is why it is taking more energy. And more energy it takes, that means it has an opportunity to undergo the reaction in an indiscriminate fashion. So in addition to para, let's say, or meta, you have other possible product formation. Since you are doing thermal reaction and the energy in the system is quite high, you will end up getting mixture of products. But for photo reaction, the energy in the system is so minimal, only the most preferred pathway is the one which is going. The pathway or the mechanism is this one and the blue color one. But for the thermal one, of course, from here you are going there without going through this pathway. From here you are going. Okay, From here, you are going there. So the thermal pathway is completely different. Photochemical pathways are different, and it is giving only one product. Thermal pathway, once again, if you want to remember anything from this talk, I'd say thermal energy available in the system by heating it 110 degree, 90 degree. If you don't hit, reaction doesn't work, because the CH activation, you have to pay the price as well. Okay, so either the reaction doesn't work, or if it works, it gives you mixture of products. That's the thermal story. But for photochemical, story is written in a different way, at least based on our understanding and the initial presumption, and we think it is the way we were trying to portray. Of course, photocatalyst also comes into picture. If you have photocatalyst, photoexcited, and triplet to singlet energy, if you see it, this energy is available in the system. If you are not having the right photocatalyst, it can end up creating mess. Again, just like thermal or the temperature can create mess, the photocatalyst can create mess, meaning that other side product formation can increase. The minor product formation can increase, so the selectivity can be problematic. So that's why it is essential that you optimize the photocatalyst as well. Maybe I'll just take a quick minute, although this is very important slide. What we find that the detailed mechanistic studies, that if you take the substrates are controlling. If you have an electron deficient substrate, you have a rho negative value, then that means electrophilic aromatic substitution is going on. If you have an electron rich substrate, the rho value positive, that means an unsymmetrical transition state is going on. And in this domain, the neutral substrates gives you a symmetrical transition state and rho very low, very little kinetic isotope effect, very little kinetic isotope effect, or no kinetic isotope effect. And this is the reason where kinetic isotope effect is. This is the final disposition of the activation step. So in the arene cases, electron deficient arene, you have electrophilic palladiation. For unsymmetrical transition state, you have very little kinetic isotope effect. Unsymmetrical transition state gives you a rho value of positive 1.1332, and these are very little rho value symmetrical transition state. So depending on the substrate, your reaction mechanism will vary. That's it. I'm done. Scientific part, at least. I hope I'm able to briefly tell you that the nuances that involve the activation we can influence here, the oxidation we can influence here. Right? Since the first step and last step, we are influencing first step and the last step. Well, this makes it special for doing these reactions at room temperature without any oxidant. Of course, oxygen from air will be the oxidant, not the silver salt. Okay. With this, well, I think in every lab, it's the students. Right? Students and funding, that's what drives the activity. So I have been absolutely fortunate and delighted to have excellent students, perhaps the country can offer. I cannot thank them enough for their brilliance, hard work. My job becomes very simple, just to do nothing, I guess. Keep it simple for them, and do not come on their way. Let them flourish. I hope they enjoy. They will continue to enjoy. Yes, there are difficult times in every life, every walk of life, and we try to overcome those by understanding simple things. Thank you very much. I'll be happy to have your question. Thank you, the funding agency, and thank you, the organizers, for giving me this wonderful opportunity.
Yeah. Thank you, Professor Mighty. Now, I'll just keep the discussion open for the audience. So please post your questions on the YouTube channel that I can ask. I can convey that. Yeah, this is from Dr. Shantanopal from our institute. Is that light source is not responsible to do a organic photoreaction in the synthetic product simultaneously?
No, light source is required. The white light is good enough. We can take a particular wavelength light as well. Since simple light was working, we did not go for a particular wavelength light. But nowadays we have particular from the Cassil, we are buying the selective wavelength light. We can use that. Light source is simple household light is good enough. Thank you, Shantanu.
There is a query from Devendra Tiwari. What is the exact role of silver additives in CH functionalization reactions, or just act as a terminal oxidant?
Yeah, that is a very important and nuanced question. Well, at least in the literature, as it has been predicted or has been outlined, it has two roles, as I was discussing. The first role, it comes into the CH activation. It has been told that silver palladium cluster, even we have been also suggesting, silver palladium clusters is involved into this activation step. When you have palladium, only palladium versus silver plus palladium cluster involved in the activation step, it looks like silver palladium cluster activates the bond more efficiently, or you need less energy for that. Mainly, Ken Hauk and with us, Shunod's group, we have been working together. So we are proposing that it started with Ken Hauk. So we are proposing that that silver palladium cluster is involved for the thermal reaction. Okay, so CH activation step, or the first activation step, there is a role of silver palladium cluster that in situ forms. But so far there is no experimental direct proof. All these are computational. Okay, and computationally it has been shown that silver palladium cluster is a preferred intermediate compared to simple palladium intermediate. Again, I'm a synthetic chemist. I do listen to our great collaborators. I would like to believe that's the case. But in these cases, I think in the photo cases, we see that it's not necessary. Silver is not necessary. We can walk away. I mean, that's what we are able to see. Silver is not necessary. It's important for thermal reaction, but not required for photo reaction that we have been doing, or we started doing recently. Thank you.
Okay, good. So there is another query from Rajat Raju Maharana. In between is a basically fundamental question. In between aliphatic and aromatic system, where it is difficult to do CH activation reaction.
Yeah, that is, I would say, straightforward in a way. sp3 carbon hydrogen are very difficult, because the problem is, at least in aromatic, you have some sort of differentiation between ortho meta para. You have a substituent, you have some sort of positional selectivity. But let's say you are looking at octane, right? Simple aliphatic octane. Now, what is the difference between C3 and C4? Very little. Even C2 and C3, C4 and C5, it's very little. At least in arene, you have some pi electron cloud where you can interact with the metal. You can kind of latch on to. You can have the pi electron cloud interaction with the metal center, like donation, back donation, sigma to pi star, and that sort of some interaction you can induce for the arene. But for aliphatic, forget it. There is very little you can do. So that's why aliphatic becomes so tough. Yeah. Most often you will see that people are not dealing with the simple aliphatic substrate. They are taking little biased substrate. In this domain, or many of the domain in synthetic chemistry, biased substrate or more complex substrates are the easier one to react. It's perhaps contradicting many things that we look at, but it is true that more complex the substrate becomes, perhaps easier it is to do the reaction selectively. Simpler substrates are difficult, very, very difficult to do the things selectively. Complex means there are complexity or the electronic and steric bias. You can kind of try to modulate that or try to take that in your favor. Thank you.
Yeah, so there is another query, Bhairi Lakshminarayana. Is possible to put external template for specific selectivity?
Yes, indeed, that's a good one. Yes, it is possible. This is what we were trying to show, that you take an organic substrate, you attach or you interact. This is always, you don't have to attach covalently. That is where we want to reach. We are trying to reach. We are reaching there. You covalently need not always attach. Some sort of interaction, let's say electrostatic interaction, weak interaction, hydrogen bonding interaction, that is where the next story. Hopefully, maybe in a year, I'll be able to discuss with you all. So in some way, you interact your organic substrate. You take your organic substrate, you interact, right? Now, once you are able to interact this, and then you will be able to do the reaction. So the control of selectivity or selectivity control is coming from the design of the ligand. Yes, it is possible. That's what we have been doing for meta, para, ortho-meta, para, all of these cases, or C3, C4, as well as the aliphatic substrate, beta, gamma, and delta. Thanks.
Yeah, he has also another question. What is the scope of Metastage activation using nano catalysts?
Oh, well, that's a good question. One thing is we did not try. We have interest in trying, but of course, expertise, I think we can build up. But nano catalyst, the thing is we have to ensure that the ligand is attached with the nanomaterial. So that part, I'm not 100% sure of whether our ligand will be attached and the nano catalyst will be doing the reaction. If anyone had some clever designing aspect which would ensure that that is happening, I think this would be wonderful. I wish we would have been doing this earlier, but so far things are taking time. Yeah, I'll be happy to have someone who would be able to really push it forward. I think it could be done provided you have the right design. Thank you.
So there's a further question from Saurav Manna. Is base metal catalysts also do the same type of reaction?
I wish. We tried. We are trying. We will be trying. The thing is, what is happening, the ligand that we have designed here are specific for this sort of metal. Okay, palladium and rhodium are working so far. No other metals so far are working. So you can say that that's a limitation. Yes, it is. We have been trying quite a lot to improve the design of the ligand or find the right ligand which will be able to bring the base metal catalysis. So far, we failed miserably. Maybe we are not pushing enough. Maybe we have to pursue it more persistently. We'll do that. Hopefully, we'll do that. We have been trying a lot. Again, in short, we could not do it so far. We'll be doing. Yes, that's a good approach.
Final question, a very much similar question put by two people, Soumya Ranjan Mishra and Tanish Kumar Sahu. In photocatalytic reactions that you explained, what is the significance or significant role played by the light? Is that only by CFL light it happens, or any other light, particularly when you used 36-watt bulb? Does it matter reaction?
Yeah, yeah, that's a good question. Yeah, it works with every bulb. Okay, it doesn't really matter. See, the thing is, you for the reproducibility and the publication purpose, you want to have something which is, let's say, fresh from the market. You don't want to use it for a year. You just buy it and do it. But we see that things are good with almost any bulb. It is not dependent too much on the bulb. But well, it's so to speak, still it has some effect. But I would prefer you use a relatively good bulb, fresh bulb. Things works perfectly. Yeah, I mean, it works. That I know. We know it works. But there are sometimes the yield and selectivity varies depending on the light source a little bit, but still it's good enough. So if you want to get a good reaction, just get a CFL bulb and get the reaction done. Also, you can take the particular wavelength light. That also works.
Yeah. With this, now we'll conclude the questioning session. And then thank you, Professor Maiti, for presenting lucid way the current developments in CH activations that is undergoing in your laboratory, and also to take it into the future. What are the best other possible methodology that people can use in a different ways? Especially the questions are also very prerogative. I can just proactive, especially with meta-CH activation. Still, it is a very hot topic in the area of CH functionalization, CH activation. So thank you once again for your time to just give the lucid presentation about the from fundamentals to the advancements in CH activation. Thank you once again.
Thank you, Dr. Fidelity.
Yeah. Okay. So now
I will.
Yeah. Now we'll proceed to the final presentation of this session by Professor Ananta Kapdi. He is from Department of Chemistry, Institute of Chemical Technology at Bombay, this Mumbai. He did his PhD from UK in the University of York under the supervision of Professor Ian Fairlamb and Professor Richard Taylor. He did his postdoctoral work at Göttingen University in Germany with Alexander Humboldt Fellowship. He is currently UGC appointed Assistant Professor of Chemistry and Chief Central Training and Placement Coordinator at ICT Mumbai. And he was also associated with the ICT IOC Bhubaneswar in its initial functioning at Bhubaneswar. He has some recognitions. He got British Council UK Education Alumni Award finalist, Fellow of Royal Society of Chemistry London, as led us in the category. He recently just been elected there. And also he gave the invited professor position at University of Orleans, France, and CB Muraka Best Assistant Professor Award in 2019. Most importantly, his academic and research accomplishments with this associate editorship of RSC Advances, one of the of Royal Society of Chemistry. He is already fellow of Maharashtra Academy of Sciences, and he received that fellowship for scientists. And he also got the DST SERC Fast Track Fellowship for Young Scientists. And he has a good publications in various premier journals of chemistry like Anglo-Chemistry, Chemical Society of Review, Organic Letters, etc. With this, now I invite Dr. Ananta Kapdi to present his research work on case phosphines controlling metal electronics for the exploration of novel synthetic pathways. Dr. Kapdi, please. Please see the two slides. Yeah. Please check your mic once.
Please unmute.
Yes.
Yeah, now you can speak.
Yeah. Good morning, everyone. Thank you, Dr. Reddy, for kind introduction. I think it would have been always good to be in Bhubaneswar because Bhubaneswar as a city has a special place in my heart, and I've been there for 1.5 years as a part of the ICT IOC Bhubaneswar. I've also visited IIT Bhubaneswar and met all of the friends. So yeah, it's kind of a regret that we are not able to meet personally. But anyways, I think hopefully in the near future, we should be able to do that. I would like to thank the organizers for giving this opportunity to me. Whatever science we have been doing for the last 8 to 10 years. We have been interacting with various scientists, various companies, and the science has been developed over a period of time based on these interactions. And you'll see a flare of more fundamental science, mainly dealing with the electronic of metals, electronic of ligands that we use. But at the same time, some inclination towards trying to apply the science towards what companies require from us, either in India or abroad. So when you look at science, when you look at chemistry, I still remember that when I was working in doing my PhD in York, as well as then later on went on to do my postdoc in Germany. One of the things which I was always interested in, and one of the interaction which I had with Professor Robert Grubbs in 2005 when he had got the Nobel Prize. He had come to York for the Nobel Prize winning lecture. And during the interaction, I asked him a very, very specific question that when you develop a catalytic system or a catalyst, exactly what is the idea? Do you go on to make several catalysts and you target several species or several substrates? Or is it that you have one catalytic system which can take care of things? And that's what he said, that the idea should be that you do not try to make many. If possible, make sure that you understand the electronics and try to come out with one system which can target several problems which are associated with the variety of substrates that you're working in that field. So it got stuck in my mind that whenever I look at the chemistry which has been done in literature, certain ligands which have been used for controlling the electronics of the metal, either making them electron rich or trying to reduce the power of the metal. Phosphines and naturally even Nitrile like picarbines, but specifically phosphines have played a major role. Sigma donating phosphines, and the ones which are in front of you are some of the most applicable, some of the most useful phosphines. Buckwald ligands, for example, X-phos, S-phos have been immortalized. I think most of the processes from general cross-coupling to CH1 functionalization and even further, these ligands have played a very, very important role. Similarly, you have ligands such as Belaphos, you have the Fu ligands, and you have the Conphos and many more, which are known in literature. But one aspect which we should try to understand, and that is visible here, that whenever you have the phosphorus that is coordinated, the tri-coordinated phosphorus, the ligands, the substituents around them, or the groups which are coordinated to the phosphorus, they are commonly donating ligands. So this cyclohexyl, the aryl groups, they are generally going to donate.
Anand?
Yes.
Which slide you are on?
I'm on phosphines. I think it's the second
slide.
No,
your slides are not moving. Your slides are not moving.
Okay, just 1 second.
You are still on the first slide, if I am not.
Okay. Is it? I've closed it now. I'll just check if. Can it be seen now?
Yes. Maybe manually you do it or something.
But it's not coming.
Is it changing?
It's not coming at full screen.
Can you go for full screen and then change?
Yeah, I've gone for this full screen. I don't know what is the problem here.
One suggestion, Anand.
Yes.
What you can do, you share the screen, not the window. Sometimes it happens when you maximize, then it doesn't move. Okay.
Okay.
So if you share the whole screen, then I think it works. You may try that.
Okay. Now, is it seen now? Can you see this?
We can see it, but not full screen. That is perhaps all. Now full screen. Yes. Now
we can see. Yeah, it's moving.
Okay, great. Thanks. Sorry for this glitch. So I was just saying that when it comes to the
can you hide your this the stop sharing that pop up? Yeah.
So these ligands have been immortalized, and there have been a lot of applications of this ligand of these ligands. One of the main aspect is phosphorus is highly donating. So you have the lone pairs which are available for donation and can be easily donated to the metal. Depending on the metal, it can be highly electron rich, and you can then try to activate a variety of different bonds. So aryl halides have been one of the major target of these type of ligands, and aryl halide in the cross coupling, as well as you can see in the CH1 functionalization, wherever there is a possibility of using aryl halide, where CCl, CBr, or CI bonds are present, you can easily activate them using these donating phosphines. But one of the part which I'm going to talk about, something which we have been influenced, is whether we can have a caged phosphine. That means they are more constrained. There is a cage which is around that phosphine. The tri-coordinated phosphine either will be coordinated with the heteroatom, and then you have a cage system which will restrict the possibility of it, the way it coordinates to the metal. It will have a specific way of coordination. It will definitely show electron density or electron richness depending on what type of groups which are present around it. but it can also be fine-tuned to make it more pi accepting. So you can reduce the lone pair donation capacity of the phosphorus by interchanging this type of the coordination which is there, the groups which are present around that phosphine. So these are very important because 1980s onwards, Workaday has again immortalized this ligand system. The cage phosphines earlier were very less known, but Workaday ligand has been one of the pioneers of using these Sugma donating cage phosphines. So we have been fascinated with this, and what we see in literature, and that is something which I always tell the students, that whenever you are looking at problems which are there in literature, you cannot look at the current literature always. You'll have to go back 20, 30 years, and you see that there is one or few persistent problems which are continuing in literature in specific areas that have not been taken care of or that can be addressed using the chemistry that we are going to develop. At the same time, as I said, that we do work with companies a lot, and majorly when the companies give their inputs, there are certain problems which are associated with the companies, which probably the academic, academically we might not be, we might overlook those problems. So as I said, that aryl halide chemistry has been very well known, and 20, 30 years or maybe more has been explored very well. But when it comes to heteroaryl halide, that's where some questions have arisen. That even though there are these highly donating, very powerful ligand systems which have been utilized for addressing these questions, they have not been able to completely address the problems, and therefore the commercialization of certain processes or application of these ligands in commercial aspect has been still very limited. So we thought that we could probably start addressing one by one the question as and when they come in front of us. At the initial stage, we have always been fascinated by bioactive molecules, molecules of biological relevance. Nucleosides was one of the aspects or one of the structural motifs which came in front of us. And that was again through an interaction with a company, Rasayan and Incorporation from America. The question was very simple, that when it comes to a simple structural feature of any nucleoside, this is a uridine structure. So whenever the uridine structure, cytidines, you have guanosine or the adenosine, when you look at these molecules, so this is the adenine or adenosine with the sugar. So when you look at these structure features, they are going to be directly incorporated into the oligonucleotides, finally ending up into DNA or the RNA. And all the chemical biologists, either in India or abroad, and currently whatever we are seeing as a situation in front of us of pandemic, these molecules, which are nucleoside-based drugs as remdesivir, whether it's mRNA vaccines, or DNA vaccines which are coming up, they are the basic structural features of all these important molecules, which are commercially useful. So what we were not really aware of the fact that we will have a pandemic and this is going to happen, but definitely these are having a lot of important properties. One of the properties which has been extensively studied in academia specifically is to convert these simple molecules like uridine into what are called as fluorescent probes. And how would you do that? Is looking at the structural feature, you would understand that you have these two amide groups, which are generally, you can think about it as, they are electron withdrawing groups. So they are accepting, they can accept electron density or pull away the electron density. So they are good pullers, they can pull. And then you have these highly electron-rich heterocyclic ring systems, and furan is one of the most powerful donor system you can imagine, because they are pi-excessive heterocycles. So they will donate electron density into the so-called accepting group, which is the uridine. Similarly, if you go to cytidine, it changes, the scenario changes slightly because you have the lone pairs. Your nitrogen, the amino group, is a good donor. So it pushes electron density into this ring system. And your cytidine becomes slightly more donating as compared to your uridine. So accordingly, if you have a counter, then that counter should be more accepting. So you can have an electron withdrawing group which is present either on the aryl, or the whole aryl system can be more pulling. What it does is, with regards to this push-pull system, they can become highly fluorescent molecules. When they become fluorescent, they start absorbing in the visible range, which is 400 to 800 nanometers. And then they can be useful for detection of the viral DNA, what has been done currently, that you can incorporate this into the oligonucleotide, finally the DNA, and they can be injected into the various viruses or to get information about viral or bacterial cell. So there are several other molecules as well, but nucleoside-based molecules, you can imagine, can be absorbed more readily because they are the building blocks of the DNA itself. So when you have to mimic generally the cell, which is a viral cell or cancer cells, they can look at these molecules as only, and they would get easily absorbed into the cell. And finally, it would give out the information what you want. Similarly, another major point, these are the people who have worked extensively. Yitzhak Tov from San Diego has made some very, very useful contributions to this area. And these are the molecules which are very fluorescent, highly fluorescent, around 430 to 450 nanometers. Similarly, you can have this polycyclic, polyaromatic ring system like pyrene, and you can have conjugated systems like inserting these Chiral systems, or you can have alkynyl systems via Sonic-Geshra or Heck type of reactions. But the other point is, rather than just having fluorescent properties, these molecules also can act as very powerful antivirals or anti-cancer drugs. And we have already seen a major flurry of the antivirals which have come out have the core as nucleosides. As I mentioned earlier, that we have to always look at the problems which are associated with some chemistry in literature. And somewhere we have to understand how to tackle those problems over a period of time. So when you look at the structural features, either the uridine or the pyrimidine structural features or the purine structural features, in literature, chemistry has been done extensively on various subparts of these molecules. So if you look at specifically the purines, there are 3 sites where the chemistry has been done extensively. But some of the limitations which probably hinder the application of these molecules, either in the chemical biology or the biochemistry sector, because still people, when I came back to India and when these questions were in front of us, we started interacting with the current chemical biologists, some of our colleagues, and one of the reactions which was extensively used rather than what has been shown here is specifically the Stille reaction, which allows you to use tin type of compounds. Tin is very, very toxic. And you can also imagine that if there is large amount of these metals which are present in the solution, and when you are isolating the product, there might be a possibility of all these metals also getting stuck to the product, and that might cause major problems. So even for simple aryl insertion or for the incorporation of aryl groups onto these moieties, majorly Stille reactions were preferred over Suzuki or others. Even CH bond functionalization to a large extent have been neglected in this area, and something really people should try to look at and try to come out with more efficient techniques in this area. Scale-up limitations are definitely there because companies are going to ask these questions. Academically, it might be easier for us to isolate it using simple column chromatography. But general limitations which are there are catalyst concentration are literally substoichiometric, 10%, 10 mole % or higher. Palladium generally is going to be the preferred catalyst or the preferred metal for the catalytic systems. But there are various solvents which are also used, organic solvents. And somewhere all these points are to be considered if you have to develop catalytic system. There have been some reports in literature, specifically this one, which was a ligand, which is TPPTS. If you remember from the organometric point of view, TPPTS was used in the autorolin process. It's one of the main water-soluble ligands, which is used for rhodium coordination with the phosphine to make it water-soluble. So it has been used, but it has been again used with acetonitrile water system, and the yields have been suffering because this is the donation power of this phosphorus is not that much, but at the same time, there are certain complications with regards to the sulfonates which are present here. What we thought was to start off with this cage ligand, which is called a triazole phosphodiamantane or PTA. Our first tryst with this area was the collaboration which we had initiated with Professor Jose Serrano, where we developed the catalytic system where palladium can be coordinated with these 2 phosphines, the PTA ligands, and some of the science which I had initiated from PhD came to our our support, where you can have these pseudo halides, which are called as saccharinates, malaminidates, succinimidates, or thalamidates. So they can pull away the electron density to a certain extent. But the palladium will be +2 in oxidation state. And this is a very stable complex. You can crystallize it, you can get X-ray crystal structures, you can keep it in the, on the bench for quite some time, and it doesn't really degrade. So we started with this, and we started addressing some of the questions which were there already in front of us. And we were successful in a way to carry out the Suzuki coupling only in water as a solvent, although the temperature was something which we were not very happy with. Because the ultimate goal was not just to modify the nucleosides. The ultimate goal finally was to try and target late-stage modification of oligonucleotides, DNA or RNA. So we are very far from there. But one aspect was achieved, that you can carry out the reaction in water because the solubility of this complex was pretty decent, around 110 milligrams per ml. Not very efficient or not very impressive, but it's good enough to make sure that the palladium tries to remain more into the organic phase. Wherever the possibility was there, we tried to isolate the product without column, but it was seen that the palladium was still leaching into the final product. And that made us believe that this catalytic system is not the catalyst which will address all the questions, specifically for column-free isolation. So ICP-MS analysis showed that it was higher concentration of palladium which was present in the final product if we do it column-free. So we are stuck with some problems, but we were able to at least solve certain problems. Heck reaction also was carried out. Catalyst concentration can be reduced. But then certain other reactions which are more important, Songeshra, cyclization processes and all, they were not possible. So we were thinking that exactly what could be done. And this is where, we have to sit with the students. We have to start going back to our drawing board and try to understand that what can be done. First, to improve the solubility of this ligand, which can coordinate strongly with palladium, and the final palladium complex solubility into the solution, which would be solvent as water, can also be improved drastically. There was some precedence in literature. Fritz Kuhn from TUM, Technical University München, who had worked on N-nitrocyclic carbenes. Simple methyl imidazole, N-methyl imidazole, if you take, and you try to react with this so-called sultones. So you can have butane or propane sultones. You can have larger ring systems as well. But he just simply allowed one of the nitrogen atoms, which is the internal nitrogen atom with the lone pair, to attack onto these sultones. The sultone ring opens, and it was giving this cottonized N-nitrocyclic carbenes with the sulfonate ion. We thought, is it not possible that we can also apply the same chemistry, same science, and try to allow this PTA, which has some solubility, to be then converted into this zwitterionic PTABS, which is the butane sulfonate, butyl sulfonate, you can say. But what we are doing is, when you are doing this reaction, you can imagine that you are forming a quaternary ammonium center. This will play a very, very important role in the electronics, and I will discuss with you exactly how that helps understand the chemistry, usefulness in coordination of phosphorus to the metal, strong bonding, better solubility, and various other factors. Sulfonate is definitely going to be one of the major factors for having strong hydrogen bonding with water, and that will drag this ligand into the solution, making it more water soluble. On its own, the ligand, specifically the PTABS, has very good solubility, so we have definitely improved the solubility. Overall complex solubility has to be seen, but that is something which we'll look at a bit later. When it comes to the complexation, these are all water-soluble ligands, so that was a real tricky part, that crystallizing them out and understanding the crystal structures was a real big task. And that's where our collaboration with Professor Carla Schulzke from Germany paid dividends, because she is an excellent crystallographer, and she was able to crystallize this PTAPS, and we were able to confirm that, yes, the quaternary ammonium part is there, and you have the sulfonate. But interestingly, you also have these water molecules which are crystallizing, which suggests that there is a very much affinity of water to this ligand. It also suggests that you have to keep this ligand in a closed environment, because there is a possibility that it might get more water molecules around it, and it might try to, try to hydrolyze. The stability has been checked in solution on table, and we see that it's decent, but under nitrogen, it is very much stable even for several weeks. One of the main achievements with this ligand system was we certainly were able to do the reaction in water. Catalytic reactions still cannot be done at room temperature or lower temperature, but at 80 degrees, you are finally able to do the isolation of all 4 modified nucleosides without using column. So you can do a column-free protocol. These are the yields which are generally obtained via the column-free protocols. And the reason, you can imagine that although these molecules look very polar, but when you start putting these non-polar groups, aromatics, heteroaromatics, or polyaromatics, the molecules also start becoming more hydrophobic, and they will slowly start coming out. At the end of the reaction itself, you'll see that the compound is literally falling out of the reaction. So it made our life easy as well. But at the same time, the one question which was there, that whether the palladium, which was showing some leaching properties in the earlier catalytic system, is it better now with better solubility in water? And so the compounds which were isolated, when they were tested using ICP-MS, we definitely see much lower than PPB, rather very negligible amount of metal leaching, which suggests that either the non-coordinated palladium, which might be at the starting point itself, or maybe enough, that is the only part which might be leaching, but commonly it is so less that we can still be sure that your catalyst is major part, or 99% part, is still in the solution. So somewhere the ligand is playing a role. Solubility is one thing, but also something to do with electronics. And there again, I want to identify this quaternary ammonium part, which is going to be very important in defining the electronics of this ligand. We were able to further go ahead. We were able to finally do the recycling studies. We got up to around 8 recycles. Naturally, after that, you have the salting out effect, because you have the salt buildup, triethylamine hydrochloride salt buildup, and that somewhere is going to affect the final reaction conditions. But it takes at least 7 to 8 recycles where we see that the catalytic activity is more or less consistent, and after that, it starts reducing. When it comes to certain other reactions which had failed with the first generation catalyst, and this generation comes from, again, what we got influence when we saw certain people talking about generations. Grubbs catalyst, for example, the first generation, second generation. The first generation had limitations, but the Sonic-Gesha reaction now can be performed on these substrates very efficiently, in certain cases without the use of copper, giving the products, the Sonic-Gesha product, with very high yields. But this is specifically an example of cytidine. When it comes to uridine, this was very interesting that when we started the work with uridine, without even using copper, what we were seeing is, along with the product, which is a Sonic-Gesha product like this, we are also seeing some cyclization happening, something which was a fluorescent spot. We are not able to confirm exactly what it is earlier, but when we isolated that spot, which was very difficult to isolate because the polarity was very less, we looked into the literature, and what we understood was there is a possibility that your amide, which is here, because you have the alkyne group here, you have the amide part here. Under the conditions, even if you don't have copper, some part of palladium might coordinate with the alkyne, and your amide might start tautomerizing to the iminoalcohol form. If it does go into the iminoalcohol form, you have OH gets the lone pair and it attacks onto the alkyne. That's where your cyclization is taking place, and you get these molecules, which is a direct drug molecule. This is a Fe100, which is a HSV1 inhibitor. This is a blockbuster drug. So this was a very interesting process, that if we can combine Sonic-Gesha reaction, and rather than isolating the product, which is going to be having some impurity of this, can we completely cyclize it using what is called as a tandem process, where you add copper. Copper will coordinate strongly with the alkyne, and then allow this, this iminoalcohol to attack more efficiently. So your tautomerization is more or less complete. and then you allow the reaction to proceed forward to give you the product without isolating the intermediate. So that is something which we're very happy with, that we are getting much better results, much better yields of Fe100 or the analogs as compared to whatever has been written in literature or a two-step process. Similarly, we have been doing some tandem processes with the nucleosides, specifically the HEC and the Suzuki-Miyaura sequence, where you first carry out the HEC reaction. It is very interesting to see there is some chemoselectivity which is present here, because you can see the CI bond, which generally is associated to be more reactive. But you can also see that palladium generally can also insert into CBr with equal reactivity. However, when you have the PTA-based system, it exclusively initiates the reaction and it undergoes oxidative addition specifically to this bond. That's what we feel. CBr bond is completely untouched. What it does, it gives you the handle of forming this as an intermediate. And now you can specifically activate the CBr bond using a more electron-rich phosphine to activate the CBr and then allow the Suzuki coupling to happen tandem in the same pot. These molecules are highly fluorescent, and what we have been able to do with these molecules was synthesizing these molecules, comparing it with the one which Zach Tor has prepared, comparing the activity, mainly the photophysical activity. And what we see is whenever you have this conjugation and this more electron-rich heteroarenes which have been conjugated to the uridine, and that is a good thing because uridine is an acceptor while these are donors. And then you further conjugate, so now you have a separator. So you separate out the alkene with respect to the electron-rich, electron-rich heteroarene by a spacer. A spacer will be arene. There can always be a spacer of alkyne. Here we remove that alkene and we simply have the phenyl as a spacer. What we see is you have improvement in the absorbance as well as the emission properties of these molecules. If you see that in most cases, the emission values have gone up. But the interesting part is when you look at all the structural features, specifically this one, which we had prepared as compared to the one which is known in literature, the emission value has improved, but at the same time, it has shown some selectivity in what is the protein sensing area. So this is a collaboration which we had initiated with Professor Suvendu Bag from IIT Guwahati. And the idea was to take 2 or 3 proteins such as bovine serum albumin, which is very well known, very cheap, one of the most commonly applied or commonly studied serum albumins. You can also have HSA. Sorry, this is not BSA, that is HSA. So you can also have HSA, but this is slightly more expensive. And then we compared it with the alpha albumins. So there is a slight difference in the structural feature, mainly the cavities which are present in these proteins. So you have to do some modeling studies. And what we saw, specifically this molecule, was showing good sensing ability to the site 2. So it was trying to coordinate with the amino acid residues of the site 2 as compared to site 1. So it was more preferential coordination. And that would mean that it was showing better sensing properties as compared to, and even it was able to distinguish between albumin, which it was showing some binding studies. It was having some binding as compared to your BSA. So we have been able to apply our chemistry or the compounds which we have prepared outside the domain, although we are not experts in this area. But we are very happy to see that there is some application. We can fine-tune the electronics on these uridine as well as cytidine systems, and we are now looking at even the purines. This is what we have done with other molecules. We can put alkyne systems. We can have donor, donor part, which is going to enhance the fluorescent properties. And you can see that everywhere emission values have started growing. Even the absorbance value in certain cases has been very much appreciable as compared to what we have in the literature. But one interesting point, and these are the nice photographs, the students are excited when they see that there is color change, and there is specifically this one which I have to highlight, which is this D, which I'm talking about. This structural feature, which is called as acridizenium. This is acridizenium salt, again a cottonized nitrogen, and the PF6 ion, which is the neutralizing part. What it does is we commonly see this uridine to have hydrogen bonding interaction into the DNA. Whenever it goes for the oligonucleotide synthesis, it will coordinate, it will form the DNA superhelix by the 2 hydrogen bond interaction with the uridine structural feature. But then the question which we wanted to ask was, this is also what is called as a DNA intercalator. So it also has affinity to the DNA, to a DNA strand because of the electrostatic attraction which is there. You have the zwitterionic nature. What we see is when we try to see the solvatochromic effect of this compound as compared to others, you will generally see that these compounds will have higher fluorescent value in the buffer solution, which is highly polar, and slightly much lesser in case of dioxane, which is non-polar. But when it comes to this molecule, this showed a completely different view. The maximum emission value was seen in the buffer in the dioxane, while buffer was showing reduced value. Now, this also gives us an idea that we are switching the coordination mode of this molecule, that we might not see this probably to then coordinate to the DNA, and you might have more stronger intercalation of this structural feature with the DNA molecule. However, we have not tested it, and that is something which we are looking forward as one of the application of the molecules that we have synthesized. We are also pleased that when these questions were coming in front of us from the company, the interactions which we had with the companies, we were seeing that the companies, one of the molecule which has a lot of application, again, a DNA coordinator, how it does it will coordinate to the uridine. And this spacer, this linker, is going to be outside the DNA strand. And you can remove this treflamide protecting group, and you can coordinate it with various fluorescent structural features like biotin and many others. And that can become a fluorescent probe. So this is a very, very important molecule commercially, prepared generally on kilogram scale and very, very costly. But there are certain problems which are associated with the synthesis. It's a very specific, very easy Hecke type of coupling that we have to do. But one of the specific question which companies were, Safala Organic and Rasayan were asking us was, we have to be very careful with the sugar part of this molecule, that the sugar, which is a deoxyribose sugar, has a 5' position OH, which is protected by this dimethyl methoxytrityl group. Now, what is the significance of this trityl group is, before you take this molecule, which is DMT protected, and directly incorporate into either oligo and then finally, formation of the oligonucleotide strand and then go on to synthesize DNA. It is important that the DMT protection is done. Later on, this 3' position OH is being activated to form the phosphoramidite. And then that is incorporated into the oligonucleotide synthesizer. So you cleave this part then, you remove the DMT later on, and that molecule, which is the phosphoramidite, is inserted into the oligonucleotide synthesizer to give you finally the oligonucleotides which you want, in coordination with various types of other nucleosides which are phosphorylated. So this is a very important strategy. And many times what has been done in literature is you prepare the unprotected, what we have been doing till now, all these compounds, if you see, there is unprotection. There is no protection here which has been given. So these are unprotected nucleosides which we are working with. So what is always being done is when you have the OH group in the 5' position, which is available, you then carry out DMT protection of these so-called modified molecules. But this is a very poor yielding process because this is a very sensitive molecule. Generally, it is a DMT chloride. CCl bond is here. And your OH group, when in presence of pyridine, which abstracts the proton of the OH, is going to directly attack and give you this DMT protection. This is an acid labile group as well as a temperature sensitive group. So even if you have some traces of acid vapors which are there either in the rota or around, this can easily get cleaved, and you can literally see it on TLC itself that it has got cleaved. Another problem with nucleosides, which I have to mention, is this NC bond. The bond which is coordinating the base with the sugar. This is called as the glycosidic bond. This is a very labile bond. This again is temperature sensitive, also acid sensitive to a large extent. So the conditions under which you are performing has to be more basic and lower temperature. you cannot go for 100 degrees or higher because the sugar will totally char and you will not get finally the product what you want. Taking into consideration all these problems, we decided to test our system. And what we saw was we were able to get much better yields than whatever has been talked about in literature, as well as what was going on in the company itself. Company were working on substoichiometric amount around 10 or more mole % of palladium to get not more than 50% or 55% yield. We can drastically reduce the palladium content, but at the same time, you can get very high yields of the product. Rather than isolating it via column chromatography, you can do it this trituration method, where you take the compound in dichloromethane, and then you simply start adding a non-polar solvent to give you the product, which is very pure, very pure, analytically pure product. This is just something which is always done in the companies. So we were able to demonstrate in the laboratory that we can do it at 10 grams, but we have been able to scale up in the company as well up to 100 grams. And now we are looking at kilogram scale synthesis using our ligand system and the palladium complex. We were very much encouraged by this. And what we did was we further decided to explore the modification rather than using the unmodified or unprotected version of the nucleosides with the protected DMT protected versions directly. So this is, you can look at it as a more like a late stage modification because you already have a labile group which is present. So you have to make sure that the conditions are developed in such a way that it doesn't fall off. And we are able to then demonstrate in Heck reactions, so Suzuki-Miyaura, Swan-Geisler cyclization, and further, we are able to also demonstrate the same thing for the amidation process. And why specifically amidation? Because again, the question comes from the company that these molecules, specifically this one, has a lot of application commercially. So we are able to demonstrate that whatever problems associated in literature, as well as in the company processes, where the CO pressure were always above 100 psi. So we were able to reduce that to 40 psi. Liability of DMT protection has been taken care of because you are having enough amount of base. Everything is in the basic solution or have basic, more basicity as such for allowing the DMT to be intact. Catalyst loading has been drastically reduced, so 2 mole %, but generally it was more than 10 mole %. And the limited amines, so we have just been able to improve the substrate scope, but specifically to tell you that we have now even scaled up this molecule on gram scale. And this will also be one of the technologies which will be done on larger scale. I'm now going to have a switch because we are mainly in the, an area which is very useful biologically. A lot of applications are known, but it's not the mainstream area. And what after around 3-4 years earlier, we thought that we might be missing out on a much bigger question, which when we start looking at the heteroarenes. Now, heteroarenes are again very commercially very important, have a lot of importance because of the linkages into all these drug molecules and commercially useful molecules. So,
Dr. Abdi,
yes, please.
You have another 10 minutes time.
Sure. So we have been able to demonstrate, as compared to whatever was in literature from chloroheteroarenes and others, that we were able to carry out reaction more efficiently at lower temperatures than what has been done in literature. So we were, at least for the etherification reaction, we can do it only at 60 degrees rather than what was done earlier. So we can match up with Buchwald ligand very efficiently with the chloroheteroarenes. Similarly, we can do all other processes. So you can do the same Swan-Geisler cyclization or etherification followed by Swan-Geisler reaction as a double tandem. You can also do a triple tandem where you have etherification followed by Swan-Geisler and then cyclization to give these very, very fluorescent molecules. Now you're having the emissions which are around the 500 nanometers, which is the visible range. You can also prepare these drug molecules, XK469, which we already have shown. But the main part with the PTABS system, which we were really fascinated about, was the sulfur-containing compounds. Thiols are generally called as poisons. And what we are able to demonstrate is, with regards to thiol, we can easily coordinate these, we can easily use these compounds, substrates, for the formation of these molecules, these heteroaryl substituted molecules, very efficiently, much better than what has been reported in literature. In case of alkyl thiols, we are probably one of the best results that have been reported in literature till now. But the main challenge came when it comes to the amination reaction, and this is a very important reaction in industry, academia, everywhere. So what was the challenge was we have to carry out reaction, if possible, at room temperature, because all the other reactions for chloroetridines were happening much higher temperature of 100 degrees, 60 degrees, or 80 degrees. What our palladium PTA-based system was able to achieve was to carry out reaction at room temperature itself. And you can have variety of reactions, variety of compounds which can be prepared. But we specifically started targeting these commercially available molecules, which are already there in market. And now we are looking at these specific substrates for scale up, and probably Safala might also be interested in getting them commercialized. We have also been able to prepare this very important anti-diabetic drug, which is olagliptin. Now the challenge came that we are looking at palladium, which is very expensive, and it always comes as a question in front of us. So this is one question which came from another company where Uday was, he's a team leader and he is doing a company-sponsored PhD under me. Question was very simple: can we replace palladium with copper? Why? It's very evident. Palladium is $80 per gram. Copper is only $0.01 per gram. What was done efficiently, because he's an excellent process chemist, was to carry out this reaction as what we have seen earlier, but with replacing palladium with copper, simply at room temperature in water. Earlier it was TMF, but now we can do it in water, isolate the product without column, very high efficiency. All of them, we have literally reported even the HPLC yields, because companies have all these things. But we can even try to coordinate various other drug molecules. And recycling was so efficient that you can do recycling of the copper PTA-based system up to 12 recycles. Now the question comes exactly why it is happening like that. So if you look at the ligand system, the structural feature, this is the cottonized ammonium part, and that is generally pulling. It is like a nitro group. It is a puller. It does have an effect on all these lone pairs of nitrogen as well as the phosphorus. And DFT has confirmed that it loses, the phosphorus atom loses the electron density or the possibility of donation. And that can be seen from these values, as the phosphorus has a positive value as compared to the PTA phosphorus, which has a negative value, which has a possibility of donation. We also have calculated, done DFT studies, and we have also seen the Stallman property, what we can do with NiCO4 by replacing one of the CO with the phosphines. Generally, carbon monoxide has a value, IR value of 2154 centimeter inverse, but when it comes to nickel CO4, it goes down to around 2074. When it comes to electron, the pi accepting properties of ligands with respect to the metal, which is what we are talking about, the PTABS, what we see is the value is around, so it's around the CO4 itself, the carbon monoxide, which means that it is more of a puller, and it does not allow a strong back bonding characteristic to be induced into this C triple bond O on the other sides. While the donation property, if it increases, naturally the back bonding will improve further and further, because your nickel is going to donate back into the pi star of your CO. So PTABS, in that case, we have done some more properties as well. And one of the interesting part was the size. Looks like when you look at the structure of the PTABS, you have the alkyl sulfonate, which is dangling out. So we generally thought that it might play a role in the cone angle. What we see is the cone angle is very small. It's only 120 degrees. So this was not very well understood exactly why it is happening. But when we look at this part, how this ligand is going to pack itself around the metal. So when this DFT video was created, what we understood is the sulfonate probably is going to have some interaction with the cottonized ammonium of the other ligand, and it packs itself into this very compact structure. So maybe that explains the cone angle to be so small. In solution phase, we have tried to understand the mechanism, but it's very difficult because most of the systems are water soluble. But we have been able to do this ESI study, and what we see is palladium at least specifically for palladium, we see the possibility of reduction to it be taking place. Maybe palladium-2 itself is remaining in solution and catalyzing the reaction. So there are many doubts which are there, many questions which are there. But to understand, to confirm the pi-accepting properties, simply what we carried out was phosphorus lone pair, whatever were available, you can react it with selenium powder, and you can form phosphorus selenide. When phosphine selenide is prepared for sigma donating phosphines, you will have a J value of the phosphorus. If you see the phosphorus spectra and you see the satellite peaks of phosphorus coordinating with selenide, then you calculate a J value. And what you see is whenever the values are lower, you have generally the sigma donating phosphines. When they start increasing, the J value increases. You can start going closer to the pi accepting ligand system. And that's where our PTABS ligand comes. It is more pi accepting. For the copper system, it was possible that we can try to understand the mechanism by ESR, because copper-2, if we are using as a catalytic system, as a starting material or starting catalyst, and then coordinating with PTABS, and if we see that copper-2 might remain in the solution for catalyzing the reaction, a long shot as compared to what is generally the oxidative addition reaction or the cross-coupling mechanisms which are known in literature. So in such a case, what we should be seeing is we should not see the involvement of the unpaired electron, which is generally there in copper-2. But we do see some part of copper-2 which might be catalyzing. Now, this is again a debate, and we are still further understanding whether it is copper-2 and what is the coordination, whether the ligand is present on it, whether there is any other geometry which is present, whether acetates are fallen off. All these questions are still being answered. But what we have gone on to propose is this mechanism, which is kind of a third type of mechanism. Generally, we know that it is the Buchwald-Hartwig amination mechanism, which is well known for palladium chemistry. And from the copper chemistry, it is the classical Ullmann type of coupling, which is known to catalyze the reaction. This is the third type of mechanism which we are trying to promote. This is a copper-2 promoted SNAR, which we are saying as a coordination activation type SNAR. And how it does is it coordinates a copper-2 if it's present, which is more electron deficient, as a pi acceptor ligand has pulled away the electron density from the copper. It will rather chelate loosely to this nitrogen atom, activate this CCl bond, and the nucleophile can directly attack as a SNAR type of reaction. It doesn't require any activation energy. And that's why if you see most of the reaction as compared to literature have been carried out at room temperature or much lower temperature than what has been reported. So this is something which we are promoting. And for further understanding or getting some evidence onto this, we are now looking at this chemistry where this is more regioselective chemistry. What it does is if you have a regioselective question of this CCl bond versus the other CCl bond, there is some details in literature through this Jack's paper that the bond dissociation energies of the fourth position versus second position is slightly different. And in our case, wherever the mechanism is more coordination and activation, you can imagine the nucleophile to attack that preferential position, which is more activated and can get selectively the product, which is present, let's say for fourth position or the second position in such a case, where you have the fifth position, which is having higher BDs. While in case of those in the mechanism where copper is going to insert into the CCl bond, you might see loss of regioselectivity, preferentially in that position which is more activated, but still you might see some product in this case as well. That's exactly what we see. PTABS, if it's a pi acceptor ligand we are seeing, then you are getting very high selectivity of 93:5 for catalyzing specifically the fourth position activation as compared to the second position. While in other cases, the regioselectivity has been pretty much lost when it comes to the sigma donating ligands. We have tried that in various cases, and we have got crystal structures to prove our point what we have. We also have got NMRs to confirm that this is exactly what is happening. This was all these extra structures were done by Dr. Dandela in ICT Bhubaneswar. Really thankful to him. This is the latest result that we have been then demonstrating that if amination is carried out so efficiently on these molecules, can we look at these structures, which are very important drugs? And now, rather than using amines which are there freely available, can we use a solvent like DMF and activate it in situ to create this dimethylamine in solution and try to use it as a part of allowing these type of molecules to be synthesized. So this works efficiently with the PTA-based system at room temperature. It works like a dream. But you can also incorporate deuterated parts or the dimethylamino deuterated part into this, because now you can use deuterated DMF and you can prepare deuterated drugs which are having very high market. You can imagine one drug molecule, 100 milligrams in the commercial market costs $1,000. And we have already contacted some companies to see whether they are interested in the molecules that we have prepared. Similarly, what we have done earlier, mechanism remains kind of the same, but in the first step where we are trying to activate, what we see is we can confirm the mechanism where CO release is taking place, tertiary butanol formation is taking place, as well as when we try to use the dimethylamine or dimethylformamide and you replace it with diphenylformamide, you can also isolate the diphenylamine because it's a slightly more unreactive base. It is not as basic as the dimethylamine for lone pair attack. So you can isolate this, but to confirm that the mechanism more or less proceeds to this is the GC, which suggests that CO has been trapped. And this is where we see that the mechanism again follows what we see as the copper-2 promoted SNAR, where it's a coordination activation mechanism. Colors also more or less indicate that it is possibly a copper-2 because copper-1 is majorly colorless or mildly colored. So you are seeing a drastic color change from copper-2 as a copper acetate to whatever is happening at the end of the reaction. We are also very happy to tell you that this ligand has now been commercialized with STREM. This happened in 2020. We have already given them 150 grams of this molecule, and they generally pay whatever amount we are charging them. And this ligand has been like a dream for us. It has also gone into EROS. And we are hoping that it will do much more reactions. And that's what the question again comes back to what Professor Grubbs put in my mind, that one ligand system can do majorly all the chemistry what you want, and you can use a variety of metals, fine-tune the electronics, understand the electronics, and then come out with various different type of protocols. This is the final slide. I'm not going ahead. This mainly is the third generation, what we are looking at. We are now almost there to achieve the room temperature protocol. So room temperature protocols was finally achieved this year. We've just published this. And we have also gone on to use the catalyst, specifically this one, as well as this one. This we are talking about CERCAP because it's Serrano and Capri. And the third generation, which was there, we have seen that the oligonucleotide functionalization, which is a late stage functionalization, which has been reported in literature to give you 20% of the modified product. We are seeing that the initial results have already gone beyond 20% up to 27%. This collaboration, which were initiated in Spain with Professor Ramon, and we are hoping that within the next few months, we might be able to improve this much further. The final part is need for speed. Speed up the reaction, make it faster. Companies also want to use what is called as flow chemistry. We are very happy to say that one of the collaborators in UK, Stephen Hilton, has developed this ICA flow, and this is now available in the commercial market. So we got this free of cost from ICA for promotion purpose, for understanding, for demonstration as such. We have been able to do the reaction for the Suzuki coupling first. What we see is drastic reduction in time. We can reduce the temperature as well to a certain extent. And how it does is you have to keep in mind one thing for flow, that your solution, your reaction should be totally homogeneous. That means your solid should never fall out. So we had to twig it a bit, where rather than replacing water with ethanol water system, which means it's a completely homogeneous system, and you can reduce the time from 3 hours to 8 minutes for specifically uridine, and from 24 hours for cytidine to only 29 minutes for cytidine. Very fast. We can even reduce this time further. Overall solvent requirement for isolation, because this is now again isolation via removal of solvent, water is remaining, you get the product out, wash it, and you get the product without any column. You can do multi-gram scale in a continuous flow possibility. You can have 5 injections, 1 by 1. Overall 40 minutes, you can get multi-gram scale product. And you can combine easily photoreactors, electrochemical reactors, and many more. Finally, this is the final slide. I cannot be here. I cannot discuss my science until, as Devu said rightly, that these are the people who are wonderful people. They've worked so hard And this is our representation of that group. These people are not just my students, but the collaborators, the funding bodies, people who have supported us, companies who have interacted with us. And that has given us the confidence and the possibility of coming out with solutions on academic as well as industry scale. And I would like to thank all of you for your attention, and again thank the organizers for giving me this opportunity to discuss the science in front of you. Thank you.
Yeah, thank you, Dr. Kapdi. We have a couple of questions that I will take it up because we are running short of time. Samranjan Mishra, he put two questions. In column purification of the compound is due to high selectivity or the precipitation of the desired product?
Sorry, can you please repeat this?
Is the column purification of the compound is due to the high selectivity or the precipitation of the desired product?
Column free, you mean?
Yeah, free purification.
Yeah, column free, one of the part which you have to keep in mind is sometimes you might have certain byproducts which are there. So the type of solvent system which you use, and this is well known in companies, that how much amount of solvent you use, depending on that, the precipitation will take place. Preferential precipitation of the product versus the byproduct. Starting materials, generally, if it's completely consumed, you do not have to worry about it. But you have all these other materials like water-soluble materials which are there. They generally are washed out earlier. So there is some preferential precipitation technology which is there, but you need to know what type of solvents you use. Column, for that matter, the main problem with column is this is the easiest way of doing separation. But the amount of solvent which you use for column purification is so massive. And that's where we have to somewhere get away from this ideology. That was the main idea behind the column-free technology.
Yeah, he himself also asked again another question. Enlighten your shift from palladium to copper.
Yes.
What is the reason behind that?
Yeah, so the cost is definitely one of the major factors, because whenever we interact with companies, and even now Sapala has been very excited about the current results, what we have, the costing simply goes haywire with palladium. And wherever you have a possibility of replacing it with a 3D metal, and specifically copper is still earth abundant, and you can see the costing. That was one of the main focus since several years. I am very much fascinated with palladium because if you see my PhD as well, it has more palladium in it. But somewhere we took a decision that we might have to move out. And what we see is reactivity wise as well, because copper is smaller. And then you have this very, very compact phosphine coordination which is happening. You seem to have better, much more enhanced reactivity as compared to even palladium, which was not known. But seems like this bioacceptor chemistry is allowing these reactions to proceed much, much faster than palladium. So we are now looking at all these aspects to see whether we can come out with our analogy of why exactly palladium or copper, or why copper is probably more preferred and can slowly start replacing palladium. We are still very early in this idea, so we don't want to exaggerate it. But that's exactly the idea, that we want to probably replace palladium with copper slowly.
Yeah, the final question for the session, Devendra Tiwari is asking, ligand-free Suzuki coupling reactions with recyclable palladium catalyst, is it possible?
It is known. It is known. Just palladium on its own with a heterogeneous, let's say, coordination, that is known. But it has its own limitations. Rather, that is what we are also looking at, to be honest. Is it possible that we can heterogenize this palladium, this ligand, and still allow the coordination to happen to palladium? What will happen is then we have a better control, any solvent you use, and then you can simply remove the metal without any problem. So that is something which has some applicability, some in details which are there in literature. But yes, this is something which people should look at, something which we are also interested in looking.
Yeah, okay, that brings us to the end of this presentation. Dr. Kapadi, thank you for your nice presentation, especially taking academics to the industry and commercialization of the products, which has been one of the very important aspects in the research in chemistry. You could really establish and prove it and then demonstrated it. Thank you. Now, I take this now concluding the session. Once again, I thank all the three speakers of the day. And now back to our organizers, Dr. Akhilesh Singh and then Srikant Patra. I think Akhilesh, you had to unmute your mic.
Yes. Thank you. So let us thank to all the eminent speakers for their wonderful talk and three different flavors of chemistry we have just witnessed. And also let us thank Professor Paddy Reddy for nicely chairing the session and keeping us within time. And now one announcement is there. For 2 hours we will have take a lunch break. Around 2:45 we will assemble again, because next session starts around 3 p.m. Okay, so by 2:45 we will assemble again. Thank you.
Thank you very much. Would love to come and meet you all, guys.
Yeah, of course, sure, we are waiting.
Or maybe we can call you here, because I'm just hoping that the government probably gives us the go-ahead. But Maharashtra is slightly concerned about the development which are taking place abroad. So maybe we'll have to wait for more time. Hello, Dr. Patra. We meet face to face, but online.
Yeah. Yeah.
I met
So
Debu here. At least Debu I met here in Guwahati, but it's pretty tough.
let's see. So if we can do something physical in near future, so that we can have a good get together and lunch gathering.
Definitely.
Again, thank.
I'm also maybe suggesting, maybe is it possible that there could be some workshop done maybe with RSC? I was even talking to Dr. Dandela, because RSC is very supportive. They are willing to support as much as possible. Maybe if you can come out with some agenda, I can put you in touch with Rajesh, and maybe they can even provide funding for it.
Yes.
Yeah. Last time actually we were in touch with Rajesh, and we were going to have one. Dr. Patra took the initiative, and then all of us just contacted them also. But unfortunately, we could not have that meeting because of this pandemic, and also yeah, in near future definitely we will try to have such kind of gathering in person where we can meet, and RSC will definitely be in the loop.
Yes. Thank you very much again. Thank you very much.
Yeah.
Thank
Are
you
you visiting here? Are you visiting here, Anand?
I probably in April, because I'm the placement officer now.
Okay.
So I'm hoping that they send me an invite first of all. I cannot just barge into ICT Bhubaneswar, or I can always come to IIT and then tell them that I'm there.
Okay. Most welcome. Always, anytime you can come.
But April maybe I'll come for sure. That would be really nice. I'll definitely let you know.
Yeah.
Love to meet
We'll
you.
see you. Yeah.
Take care. Thank you.
Yeah, thank you.
Have a good day. Yeah.
Good day.
Okay, Sikam, then
okay, let's see. So can I just check my slide once? Because it was not working properly in the morning.
Yes, sure. You can.
Yeah, so let me try. Can you see it?
Yeah, we can see.
And it's moving?
Make it full screen and then start moving then. Are you moving the slides?
Yeah.
No.
I'm trying. Yeah. Is that?
It doesn't move. So the same. Yeah. Now it moves. Yeah.
Yeah, but then I have to go to like this, right?
No. Then the same thing you also apply. You share the screen, not the window.
Okay.
Share the screen and make it full screen.
Let me try once again.
Yeah. This bug is there in Microsoft We have tested couple of times, so slowly we just got this.
So now can you see it?
Yeah, we can see. You try to move the slides? Yeah, excellent.
Now it's moving, right?
Yeah.
Okay, good. So let me try one slide where I have some animation and let's see it's working. Yeah, I think it's working now. Yeah, thank you. Yeah, good. Great, thank you. And then have a nice lunch and then we'll see again at
It seems
3
you
o'clock.
will make my life easier because I could
Oh,
see
that's
Jablonski
good.
diagram. So yeah. Okay.
Okay.
See you then. Huh?
See you.
Yeah.
See you.
Okay then.
Hello? Hello?
Yeah, Dr. Patra. Good afternoon. Can you hear me?
Yeah, I can hear you.
Okay. So what time will start?
We'll start around, I think, at 3. Okay. So I think so. I'll just give a brief introduction about you. Then I'll just tell you, and you will just start actually.
Okay.
Let the speakers join. Oculus already is there, so the other two are join actually.
Because it is.
Let people join. God, yes.
Hi, Shrikant.
Yeah,
So,
hi.
Am I audible? The voice is clear?
Yeah, voice is clear. Okay, so I think let us just start this session as the speaker is already in online. So we are now at the concluding session or the technical session 3 of this eWorkshop RAIC 2022. So let me welcome the speaker as well as the chair of this session. And before start the session, actually, so let me give a brief introduction about this chair, Professor Vijay Krishna Kari. Actually, so Professor Kari now presently an associate professor of our department, School of Basic Science, IIT Bhubaneswar. He has done his master degree from Andhra University, Vizag, and PhD he has done from prestigious IIT Madras. And he is also CRNA's postdoctoral fellow from University Bordeaux, France. His research area is based on synthetic polymer chemistry, and he is publishing a good number of papers in very prestigious journals. So he is already having roughly 70 number of publications, 3 patents, and 3 book chapters he already have written actually. So he has already research guided or guided 6 PhD students and 3 are ongoing, and several number of MSc dissertation students actually. And he is having several fellowship also, like he is a visiting scientist under European Commission. Okay, at from May 2016 to July 2016, visiting scientist again under European Commission to Polymet at Spain from November 2013 to April 2014. CRNA's postdoctoral fellow from 2007 to 2009. He has also qualified, whatever national level exam like CSIR, GATE also. Then he is a recipient of Professor T.R. Seshadri Award in 1999 for outstanding academic performance in master degree, and Professor K. Ramachandra Rao Award in 1999 for outstanding academic performance in again at MSc. So he secured first rank in AUACT 1997, and his research group basically now active in development of different kind of synthetic ionic or synthetic homo and block copolymers, and he's trying to realize their self-assembly property and to apply in the drug delivery. So with this short introduction, let me hand over this session to chair, Professor Vijay.
Thank you, Dr. Shrikant, for a very elaborative introduction. Thank you so much. I welcome all the participants for the final session of this conference. And for this final session, the first talk we are having Professor Raju Gupta. Just I will give a brief introduction to Professor Raju Gupta. He has done his PhD from IIT Kanpur. After that, he did a postdoc from University of Kansas, USA, and then joined University of Delhi in 2003, became full professor in 2009. He has guided more than 16 PhD students, and more students are he's guiding right now. He successfully completed several funded projects. Okay, and he published all his work in very reputed international and national and international journals, and he's having more than 3,300 citations and having H-index of 32. It is a very a good number. And his research area basically like coordination chemistry. Is working on inorganic chemistry, supramolecular chemistry, and design materials. So mostly these 4 areas is his most interested focused research areas, and he's won several awards. Okay. I will be just reading out a few only out of different awards whatever he has received. One is like in 2016 he received a CRSI bronze medal, And 2015, he won a Science Flame Award from World Science Congress. He also won like the ACS membership award in 2009, Indo-US Fellowship in 2009, Young Scientist Project Award from DST in 2004, and so on and so forth. And he is a committee member in several committees like PAC, Inorganic and Physical SCRB, or SCRB Power, SCRB Star, SCRB Supra, and Inspire Fellowship programs from DST. So this is a very short introduction about Professor Rajiv Gupta, and I'm sure like all the audience, especially the students, will get motivated, and so we are waiting for your talk.
Thank you, Professor Kari, for a wonderful introduction. Let me also thank Professor Shrikant Patra and other members of the organizing committee for inviting me so that I could discuss some of the work which my research laboratory has been doing. I think most of us have been waiting for last 2 years. We had this, all the plans made in 2020. I remember that, I had booked my tickets, and then I was very excited because, all the IIT Bhubaneswar colleagues had invited many people, and I thought that, we'll be able to interact for at least 2 days or so. So nevertheless, today, at least we are able to see each other and discuss some of the work which was we were intended to do. Okay, I think I need permission to share my slides.
Dr. Shrikant, can you please look into that? Dr. Shrikant? Yeah.
Can you just
yeah, because I'm sharing, nothing is coming on the screen.
Because I cannot see anything, kind of permission or something.
Okay, let me just redo it.
Yes, sir.
Yeah, please. Yeah.
No, Shrikant, normally either you have to allow me to be a co-host, and then it will be sorted out.
Okay, just 1 minute.
So, Shrikant, from there itself, you just at the dot, just click it. If something is coming, just right click the dot.
3 dot, acha, dot, okay,
Yeah.
right click.
Does it ask any permission or anything?
No, actually there is nothing.
You
that's
allow
what
everything, and then I think he will be able to share.
Okay, let me do it one more time. Meeting option.
But other speakers also, no, they were sharing, and no permission was required since morning. Rajuda, you can.
Yeah.
Just one.
Let me share the whole screen. I think that may be one option.
Yeah. That was the issue with some people. When they shared whole screen, then it was coming nicely.
सर आप लोग मेरे बोला परमिशन मांग रहे थे कहाँ से करना है
Okay, is it visible now?
Yeah.
Yes, yeah, you can go to full screen.
Yes, I will do that. So, is it better?
Yeah.
Yes, perfect.
Okay, all right. So let me again thank Professor Kari for the wonderful introduction, and Professor Shrikant Patra, Professor Akhilesh Singh, and Professor Sujit Roy for giving me this, opportunity to come and discuss some work with you. So today I'm going to discuss about some part of the research which we are doing at the University of Delhi, and then the title of the presentation is Molecular Assemblies Offering Hydrogen Bonding Cavities. And I'm going to show applications as far as binding of different molecules are concerned, and then also towards some catalytic applications and photocatalytic applications. So at the University of Delhi, we are my research group. We are primarily a coordination chemistry research group, but then we do various type of chemistry. For example, it is primarily related to the coordination chemistry, but also supramolecular chemistry, bioinorganic chemistry. With interest in energy transfer, catalysis, photocatalysis, and sensors. So today I'm going to talk about three, examples using some of the system which we have synthesized in our laboratory. So the first example which I'm going to discuss is like, recognition and sensing. So I understand that, many students are also participating. So let me just elaborate this point and so that it is clear to everyone. So when we talk about recognition and sensing, so there are, when you search the literature, most of the time you see the sensors in which there is a binding site, and then there is a, the site which can give the output signal. And once the binding site recognizes a guest, and then the output signal can be used for generating some sort of output. It could be in the form of emission output, it could be in the form of absorption output, color change, or something like that. So I'm going to show some examples in which we are going to use some macrocyclic compounds. These are metal containing macrocyclic compounds, and I'm going to show that how we can use these macrocyclic compounds. We call it molecular assemblies for the recognition and sensing application. The second thing which I'm going to discuss is about catalysis. So catalysis, again, no introduction is required. So idea is that, how we can use our, molecular assemblies and explain them, show their role as far as catalysis is concerned. So you are aware about these are just, some schematics. So you are aware about, like, the for catalysis it's very important that the substrate is recognized by the enzymatic site or by the catalytic site in synthetic system. So schematically, I have explained that, the substrate comes, there is a binding site in which substrate is recognized, and after the recognition, the actual catalysis takes place, and then subsequently you will have the product. So I'm going to show that, how we can use our molecular assemblies for this purpose as well. The third example which I'm going to show is a more advanced one, and that is an example of photocatalysis. Now, why photocatalysis? Because remember that in future we have to shift ourselves to the sustainable, examples with the sustainable form of chemistry. So in this example, I'm going to show that how we can use light, which is coming from the sun. So solar light can be used for activating certain things, and then our macrocyclic compound, our molecular assemblies can actually activate this solar light and then generate free radicals. And these free radicals can be used for the oxidative purpose, for the decomposition of several hazardous organic pollutants. So I'm going to primarily, talk about these three examples. First, recognition and sensing. Second one is catalysis, and third one is photocatalysis. Now, what type of examples we are going to use, to demonstrate these applications? So these examples are metal-containing macrocycles and cage-like compounds. So, schematically, I have explained these three macrocyclic compounds. The reason we are interested about these type of assemblies is because we can adjust the molecular dimension of these assemblies. For example, depending on the selection of metal ion and the associated ligand, we can prepare a smaller macrocyclic compound, we can prepare larger molecular assemblies, we can actually put different type of functional groups inside the cavity. For example, hydrogen bonding containing groups we can introduce. We can also introduce variety of electronic and steric hindrance characteristic we can change. So these things are important, and that's what I'm going to show, that how we can utilize this type of criteria for preparing various type of molecular assemblies. When we talk about different type of molecular assemblies, the first thing which comes to our mind that what are the guiding principles? How do we arrive at different type of molecular assemblies, molecular compounds? So I'm taking some slides from the literature. For example, the first left-hand side, you can see this blue and red color shapes. So these are nothing but the donors and the acceptors. So you can understand that, for example, any metal ion will act as an acceptor, and any ligand will actually act as a donor, because ligand can donate its electron density. So if you can combine the right type of donor and acceptor, then you can actually arrive at variety of shapes. For example, you can prepare molecular squares, you can prepare rectangles, you can prepare triangles, polygons, and so on. So some examples are shown on your slides, for example, one can prepare by the selection of metal ion, by the selection of ligands. One can prepare triangles. One can also prepare variety of squares and rectangular compounds, as well as you can go for a more complicated selection of donor and acceptors, and one can actually think about preparing the cube, the tetrahedron, the trigonal bipyramidal structure, and so on. But then everything depends on the selection of the linker or the ligand and the metal ion, and then what type of geometrical parameters these linkers and the metal ion actually provide. So similarly, like we can go for the more complicated structures. For example, rather than simpler two-dimensional macrocyclic compound, we can go for the three-dimensional cage-like compound. So there are some examples. Again, these examples are from the literature. And then depending on the type of ligand and the metal ion, for example, the first example in A, you can see 24 ligands and 12 palladium ion. They can actually combine together to form a very large polyhedral assembly where the dimensions are in the nanometer. Similarly, you can also prepare a variety of polyhedral compound. You can see some of these examples here. For example, M6, L12, M12, L24, and so on. And the idea is that you can start from the simpler molecular compounds, and then you can simply go for increasing their complexity. So we can actually arrive at a variety of structures, variety of assemblies, including molecular cages. And then the interesting part about these cages is that you have a very good control about the interior space of these molecular assemblies. So that's the next slide which talks about is when we have the molecular cages, we have a confined space within the premises of that molecular cage. Now, how we are going to utilize that confined space? What can we do about it? So there's some, a lot of work is going on. For example, we can do the catalysis. We can do the sequential catalysis in which the interior space of a molecular assembly can actually dictate or decide or control the reactivity of this type of compounds. We can also, try to stabilize different type of intermediates. So the lower left-hand side drawing actually explains one such example in which this iminium salt has been stabilized inside the molecular cage, because these type of iminium compounds are very unstable, and then outside the cage it is not possible to actually stabilize them and then study them. Some other examples we can also, if we are able to prepare chiral compounds, chiral cages, we can also control the catalysis as far as initio selective catalysis is concerned. For example, out of two products, we can actually control either the R form or the S form of the product formation. And the last example is we can also talk about various photocatalytic applications, because I'll be talking about one example of this type. So I thought let me take one example from the literature, and you can see that quantum yield for the respective precursor have been discussed. And you can see this green precursor has a quantum life of, quantum yield of 0.15. The blue precursor has a quantum yield of 0.23. But then once you prepare a molecular cage, once you prepare molecular assembly, then you can actually significantly increase the quantum yield of the product, and then that actually helps in the generation of various reactive oxygen species. And these reactive oxygen species can be used for a variety of photocatalytic applications, including degradation of organic pollutants. What is our approach? Our approach is very simple. We are going to talk about, at least in this talk, I'm going to talk about various molecular assemblies. These are, we can construct them using different type of metal ion, different type of ligands, and you can schematically you can show in this slide. So these molecular assemblies, then we can always change the metal ion, we can always change the ligand, so that we can arrive at variety of molecular assemblies. But one thing is clear, that all these assemblies will offer a macrocyclic cavity. And this macrocyclic cavity, we can actually change the hydrophobic and the hydrophilic characteristic of these macrocyclic compounds. We can also use different type of linkers as the ligand. We can also use different type of metal ions. And so the first example, in this compound, the molecular assembly, it is going to provide a variety of arene functional groups. So these arene groups, we know that they can participate in pi-pi interaction, they can also participate in CH-pi interaction, and even weaker CHC interaction. So we can actually utilize this confined space for accommodation of a suitable substrate, and then that can actually be used for catalysis and recognition applications. We can also use, we can introduce hydrogen bonds inside the cavity. So this is the second example, which you can see in the middle of the screen, in which we can introduce hydrogen bonds, and then these hydrogen bonds have also been shown in various biological systems. For example, a large number of metalloproteins, a large number of metalloenzymes, that these hydrogen bonds actually participate in the substrate recognition, and I'll be showing 1 or 2 examples of this type as well. The last example is, a similar type of hydrogen bonds, but then these hydrogen bonds are little unconventional hydrogen bonds. For example, urea, which actually can provide multiple hydrogen bonds to the incoming substrate. So some of these examples I'll be discussing today in this presentation. And as far as the applications are concerned, I'm going to show about substrate recognition, substrate activation, catalysis, and then the last example is going to be photocatalysis using the visible light. Without taking much time, let me take you to the first example. So this example is about what type of palladium containing macrocyclic compounds which we can synthesize. Remember, the idea is to only synthesize macrocyclic compound, and for that purpose, a particular type of ligand has been selected. So let me briefly introduce the type of ligand. So it's a pyridine 2,6 dicarboxamide ligand, and you can see that this is the central pyridine group. So these are the 2 amide groups, and then they have the attached phenyl ring, and then this phenyl ring has been substituted by the diphenyl phosphine function group. So if you look into the this ligand, then you can immediately see that the phosphine is a very soft donor. And then we thought that if we take a ligand which is a soft donor and if we react it with a softer metal ion, for example palladium, then the palladium, rather than going to the pincer part of the cavity, it can actually coordinate with the phosphine, and indeed the same thing happens. When we take this ligand, the first one, which has the phosphine group at the meta position, it's a simple 1+1 self-assembly where the palladium chloride reacts with the this pyridine 2,6 dicarboxamide based phosphine based ligand, and it's a simple 1+1 self-assembly. And then you can see the crystal structure in which there's a small hydrogen bonding pocket. And as we anticipated, the palladium only reacts with the phosphine, so the pyridine 2,6 dicarboxamide based pincer cavity remains vacant. When we take the second ligand, in which the only difference is the phosphine group, the diphenyl phosphine group has been placed at the para position. So now what actually happens, because of the geometrical constraints, one ligand cannot hold one metal ion, and rather it goes for a 2+2 self-assembly. And then you can see that there are 2 ligands, and then there are 2 palladium ion, and then you can see a much larger macrocyclic cavity. And you can look into the dimension of the cavity. So the first macrocycle has a dimension of 4.9 versus 6.5 angstrom. The second macrocycle has a much larger dimension of 12.8 angstrom by 14.9 angstrom. So we have 2 macrocyclic compound. Now another thing which you have to remember that these macrocyclic compounds have been prepared with the idea that they will offer hydrogen bonds. And you can see this pyridine 2,6 dicarboxamide part remains uncoordinated. So that uncoordinated means that the metal does not bind to this pyridine and amide functional group, so they remain available. And you can see that they will provide a small hydrogen bonding pocket in the first macrocycle, and a much larger macrocyclic cavity lined with the hydrogen bonds in the second compound. You can see count how many hydrogen bonds. So the first macrocycle will have 2 hydrogen bonds, the second one will have a much larger cavity with 4 hydrogen bonds. So what we have, recognition of a variety of substrates. So what type of substrate we have selected? So you can see in this slide the color coding. So the The black color substrates are the one in which there is no recognition, there is no binding of these type of substrate within the macrocyclic cavity of these compounds. Then you can see the green color compound and the blue color compound. These are the one in which we see some binding within the macrocyclic compound. And the last example is this red color compound, which is the 2,4,6 trinitrophenol picric acid, and we can see that it shows a very large binding affinity for the this picric acid compared to other compounds. So what is the reason? When we try to compare these compounds together, we can actually find out certain parameters. But we can find out that out of various phenol or carboxylic acid or substituted nitro compound, these macrocyclic compounds have a very large affinity to recognize picric acid. After picric acid, then you can also see that the nitrophenols, for example, orthonitrophenol, metanitrophenol, paranitrophenol, 2,4-dinitrophenol, you can understand that they have some similarity with the picric acid, as well as aniline, for example, ortho, meta, and para-aniline, because they are also similar. So we can understand that the nitro group is an essential condition, as well as the OH group, because unless you have both these functional groups, you can see that various nitro-arene compounds, they do not show any binding. For example, you can see nitrobenzene, you can see dinitrobenzene, you can also see TNT. So that means the compound has a affinity to bind, or rather recognize a compound or a analyte which has a OH group and various NO2 groups. Obviously, after that, I'm sure you have studied during your BSc and MSc various type of binding, and then to understand the quantitative nature of binding, we can actually find out about their binding constant, and you can use both absorption and emission spectroscopy. So from absorption spectroscopy, we can find out the binding constant Kb, and from the emission spectroscopy, we can find out the Stern-Boltzmann constant, and then you can see very large KSV value for these compounds, particularly the larger macrocyclic, which is number 2. We can see the detection limit is very good detection limit, 70 nanomolar. And then you can also find out that from the Jobs plot, the stoichiometry is exactly 1:1. That means whether it is a large macrocycle or a smaller macrocycle, they are able to recognize one equivalent of picric acid. So that means the picric acid, we believe, goes inside the cavity of these macrocyclic compound. Some more studies to find out what actually happens. So we have done a lot of mass spectral studies, and you can actually find out that there is a very nice match of the isotopic pattern of the added compound with respect to the simulated pattern. So from there you can actually find out this compound that is the picric acid inside the cavity. But then we wanted to have some more finer details, and then we used molecular docking studies to understand that. So what actually happens, the two macrocyclic compound, in the first one, as the size of the macrocyclic cavity is very small, a molecule of picric acid cannot really go inside. So what actually happens, it only sits on part of the macrocyclic compound, and then the mode of interaction is primarily pi-pi interaction and NH-pi interaction, as well as CH-pi interaction. But when you look into the second compound, here you can see that the picric acid actually goes inside the cavity, and then the picric acid OH group interacts with the amidic NH groups, and then the nitro group interact with the other side of the the NH amidic NH function group. As well as there's a lot of pi-pi stacking between the arene ring of the picric acid with respect to the phosphine arene ring of this macrocyclic compound. So in case of a larger macrocycle, the picric acid actually goes inside, and that's why we see a very large binding affinity, very large Stern-Boltzmann constant, as well as a very decent binding limit of detection, which is 70 nanomolar. But in the case of first one, where the macrocyclic cavity is smaller because it's a 1+1 self-assembled compound, so the picric acid only sits on top of it and is stabilized by some pi-pi stacking and as well as NH-pi stacking. How do we know that we are correct in our assignment? We have done a lot of in situ FTIR spectral as well as NMR spectral studies. From there we can actually find out that a molecule of picric acid goes inside the cavity of the macrocyclic compound, the larger macrocyclic compound. The same, conclusion can also be drawn from the lifetime measurement, where we see a significant change in the lifetime values when we take the larger macrocyclic compound compared to the smaller one. Now, after when we realize that we can use this compound, which is very selective for the recognition of picric acid, we can actually use it for the transportation of picric acid from aqueous to non-aqueous layer. So these are, some of the plots you can see is a calibration plot, and you can see within a minute, the larger macrocyclic was able to transport 15.2 micromolar amount of picric acid from the aqueous layer to the non-aqueous layer. Compared to that, you can see the smaller macrocyclic is very inefficient. It can only transport 2.6 micromolar amount of picric acid from the aqueous to the non-aqueous. So we can actually use these type of compounds for transporting, some compound which the macrocyclic compound recognizes from the aqueous layer to the non-aqueous layer, and vice versa, depending on the condition of the reaction. So similarly, when we thought that can we, instead of picric acid, can we also recognize some other compounds, we thought, how about antibiotics? Because antibiotics also have a variety of functional groups. For example, they have the groups which can form hydrogen bonds, both hydrogen bond donors as well as acceptor. And some of the antibiotics also have, the nitro group, which can also make it electron deficient, so that the interaction with the electron-rich compound is much higher. And interestingly, in this case, we see the smaller macrocycle has very large affinity for the nitrofurantoin as well as nitrofurazone. And you can see that the binding for the nitrofurazone is much larger compared to nitrofurantoin. And then we have found out from the docking studies, from the spectral studies, that the detection limit almost touches 90 nanomolar, so that we can actually also recognize sense residual antibiotic from the contaminated water, from the the medical discharge, and these type of things are very important for various applications. Now I will show the second part of the talk, in which similar type of macrocyclic compounds have been used for promoting catalytic reactions. So what type of system we have taken? Again, similar phosphine containing compound which have been attached with the pyridine 2,6 dicarboxamide based system. So again, we can see that phosphine is a soft donor, and then we have reacted with a soft metal ion, for example mercury, and then it actually forms a 2+2 self-assembly. You can see here we have taken two different type of ligands. The first one is pyridine 2,6 dicarboxamide based ligand. The second one is isothalamide based ligand. And we see two different type of macrocyclic compound. The first one, in which the pincer cavity is very much in place, it actually shows the binding of water molecule very nicely, housed within the large macrocyclic cavity. The second one, although it shows, inclusion of DMSO, but then the hydrogen bonding is not very strong, because this cavity does not involve a pincer cavity or made up of pyridine 2,6 dicarboxamide groups. We have done. We have taken this system, these systems, for understanding a very simple reaction. It's a Noble-Zell condensation reaction. So in the Noble-Zell condensation reaction, what you do, you react an active methylene compound with some aldehyde, say benzaldehyde, and then it forms a carbon-carbon double bond compound. One can actually take a variety of active methylene compound, for example melanonitrile and other type of compound, and then we actually found out that out of various active methylene compound, these catalysts are only active to promote reaction with the melanonitrile, in which the hydrogen bonding was very poor. Let me explain slightly probably in this slide. So we have done a lot of studies in as far as in situ IR and NMR spectroscopy, and I have just shown here that any substrate or reagent, once it is bound inside a cavity, then it is not available for the catalysis. And in that case, what actually happens, the catalysis is very poor. But then the reagent which does not form hydrogen bond, or rather stronger hydrogen bond with the macrocyclic compound or the molecular assemblies, those reagents are available for catalysis, and then they participate in the catalysis, and we see a very large transformation. So a simple reaction can actually help you in understanding that what type of reaction, for example, melanonitrile does not participate in the hydrogen bonding, and then it is reagent is available, and this reagent actually participate in promoting the reaction. And how do we know? We have done a lot of, as I said, we have done a lot of in situ NMR, in situ IR spectral studies. From there, we can actually find out that which type of reagent is actually bound within the macrocyclic cavity and is are not able to perform the catalytic reaction, and the reagents which are not available because they are bound with the the NH groups, and they are because of that the local concentration decreases and they do not participate in the catalysis. Now we can go further with the same macrocyclic compound, although some more examples have been taken here. So you can see that in these example, the ligand is the one in which the phosphine group is at the para position, and they have been used for preparing the mercury-based molecular assemblies. And you can see it's a very large molecular assembly, and you can see the crystal structure of several compounds. I'm just showing a representative one, in which you can see a very large cavity in which two DMF molecules are bound within the cavity, hydrogen bonded to the amide groups. The second example, you can also see that the second example in which the water molecules are bound, although the cavity is slightly distorted in shape. So we have a symmetrical cavity, which is coming from the para functional group, and then we have a slightly asymmetric cavity whenever the functional group, that is the phosphine group, is placed at the meta position. So these two types of compound, we have used it for the dye adsorption. So why dye adsorption? Because remember that the hydrogen bonds which these macrocyclic compounds are going to offer, dyes also have various functional groups which can accept these hydrogen bond interaction, as well as a dye molecule can also be involved in various pi-pi stacking reactions. So we have used it for the dye adsorption. And you can see that the macrocyclic compound which offers a distorted cavity cannot bind any dye, for example, whether the methyl orange or the methyl red, because one is anionic dye, the other one is a neutral dye. You can see that there is no binding, there is no adsorption of a dye. But when you take this hello. So when you take this macrocyclic compound which offers a symmetrical cavity, that time you can see we have tested variety of dyes. For example, we have used malachite green, crystal violet, rhodamine B, rhodamine 6G, chlorophenol red, eosin yellow, methylene blue, Congo red, alizarin red, methyl red, and methyl orange. And you can see that it has this macrocyclic compound, the symmetrical one, has a very large affinity for Congo red, alizarin red, methyl red, and methyl orange. And we'll try to understand that what is the reason for that. So when we go in more details about the solid state binding, solid state adsorption, you can very easily see the macrocyclic compound which are white in or almost colorless in color. When you dip it in a solution of a dye, then the dye goes inside the cavity of this compound, and then you can also see the same thing from the polycrystalline compound, which changes color from the white to dark yellow. Similarly, methyl red, which is more reddish in color, and you can see that the compound changes from white to red. The crystals also acquire orangish color. Similarly, in other cases also, you can see that in all cases, the compound is able to absorb a dye within the cavity. And we have studied the dye uptake, and you can see the uptake efficiency is somewhere from 84 to 97%. And this uptake efficiency is actually related with that how much space is available within the macrocyclic cavity, whether the dye molecule is able to actually go inside the cavity or not. So these things we have related. And you can also see the rate constant. These are basically first order kinetics, and then you can see the rate constants are higher for the dye in which the macrocyclic compound is able to accommodate a dye molecule completely within its cavity. We can also use it for adsorption of a drug. Prontocell, that has a lot of similarity with some of the dye molecule. That's a very good antibacterial compound. We can actually also adsorb prontocell inside the cavity of this compound. We have done a lot of studies, both the solid state as well as the solution state, a lot of solid state and NMR to prove that these compounds are able to accommodate these dyes molecule within the cavity. Just so that you understand that what actually happens inside the cavity. So in any case, when there is a dye molecule goes inside the cavity, we see a much larger shift in the NH stretches of the compound, in which we can see the NH stretches move from the high energy to the low energy, because the dye molecule is forming hydrogen bond with these NH groups, and then based on that we can actually justify the all other spectral changes from the NMR spectroscopy, from the solid state NMR spectroscopy, from the molecular docking studies. So we have been able to generalize that any time a dye molecule goes inside the cavity and it actually forms hydrogen bond, as well as it is involved in the pi-pi stacking, in that case we are able to see these changes in the spectroscopic studies. The last example I'm going to discuss, I think I just have around 5-7 minutes time. I will just wind up taking this last example. This example is about photocatalysis. So let me just briefly introduce the type of system. So for these lanthanide based macrocyclic compound, we have used metal ligand. So my research group is quite famous for the synthesis of various metal ligand. These are metal containing compounds which can further function as the ligand. And we in past also we have used this metal ligand for material design. This is a very interesting example, a very recent example from the laboratory, in which a cobalt containing compound which offers a biphenyl carboxylic acid group. This can be used for the construction of a rectangular cavity. You can see that we have used for the synthesis of terbium macrocycle as well as for the europium macrocycle. These are the crystal structure of two compounds, and you can see that both the compounds are almost isostructural. Both of them offer a very large cavity of 17.3 angstrom multiplied by 18.5 angstrom, so very large rectangular cavity. And this cavity actually offers both hydrophobic as well as hydrophilic function growth. And you can immediately see that all these biphenyl groups are actually providing a wall of the macrocyclic cavity. So these are the primarily hydrophobic group, but at the same time the metal center and some of the the metal bound ligands or the solvent molecule, they actually provide the hydrophilic function group. And so we thought that this compound, that means these macrocyclic compound, they can be used for accommodating a variety of gas. And both these europium and terbium based macrocycles are very stable. They are stable almost up to 400 degrees centigrade, nothing happens to them. They are stable to various pH solutions. They are stable to water, solvents, so very stable compounds. So we used it for the adsorption and the photocatalysis, catalytic degradation of dyes. So this slide actually, summarizes the adsorption activity. So you can see that we have used a variety of dyes, for example, methyl red, methyl yellow, alizarin. We have also protonated methyl orange, because the methyl orange was not able to show much larger efficiency. So based on that, we can see that these macrocyclic compounds, they have a tendency to adsorb neutral dyes. When you go to the cationic dyes or dianic dyes, then the efficiency is very limited. Now what actually happens, you can, from this slide, you can get some details. For example, if you take methyl red, it is completely adsorbed, because after some time the oil becomes colorless. The methylene blue is not absorbed. You can see that there is no change in the absorption spectrum of methylene blue. The methyl orange is incompletely adsorbed. So what we understand that the methyl red is completely adsorbed, and you can see the compound which is originally green in color changes to red, and methyl orange is almost absorbed by 60% or so, and then compound changes its color from green to yellow. We have also found out the absorption rate constant, and you can see that for the methylene blue there is no adsorption. You can also see in the spectra, there is in the absorption spectrum there is no change. But in case of methyl red and methyl orange, the rate constants are related to the absorption efficiency, because methyl red is completely adsorbed. What actually happens once these dyes are used? So we have done a lot of modeling studies, and then from there we can actually conclude that in case of methyl red, the molecule actually goes inside the cavity and it actually forms a very nice inclusion compound within the macrocyclic cavity of this lanthanide macrocycle. In case of methyl orange, although the molecule goes inside the cavity, but then the hydrogen bonding as well as pi stacking is not that efficient. Methylene blue, I think I will discuss separately. It also goes inside the cavity, but then actually it is not adsorbed, it is actually degraded. So I will discuss after a couple of slides. Then we can use, we can use this compound for the separation of dyes. It's a very interesting, example my student has performed. For example, if you mix methyl red, methylene blue, and methyl orange, it forms a green solution, and you pack your lanthanide macrocycline inside the a pipette. Simply pack your compound with the help of a glass wool, and then you pass your compound, and systematically you can find, separate methylene blue, methyl orange, and methyl red in sequence. Addition of solvent molecule as well as use of some chemicals, for example, methanol, tetramethyl ammonium chloride, or NaOH. You can systematically separate all three dyes. You can also, separate it on a piece of paper. So if you keep your compound at the center and pour a mixture of dyes on it, and then you let it percolate, that means you let it elute, you can actually also separate all the dyes on a piece of paper. Now I was telling you about the last example, which is photocatalysis. So for that, we have to first find out what is the band gap. And one can actually use the help of a top plot to find out the band gaps in this compound. So the band gap for the europium, for the terbium compound comes out to be 2.38 electron volt. For the europium compound, it comes out to be 2.69 electron volt. One can also use these band gaps as well as the redox potential to find out the homo-lumo gap. And this homo-lumo gap is such that that once you flash light on these compounds, they can actually generate photoelectron. So using this concept, we have been able to completely degrade methylene blue. So if you take methylene blue and if you shine, the visible light, you can, within 220 minutes, you can actually completely degrade methylene blue. We have, used one terbium as a reference compound to make you understand about all sorts of degradation pathways, and you can see that the degradation is complete in some cases in 100 minutes time, in some cases in 200 minutes time. We have studied the first order rate kinetics, and then you can find out the rate constant for the terbium is very large. And then this is actually related with the band gap. Band gap for the terbium compound is 2.38, and that's why it's much more efficient compared to the europium compound. And then nothing happens to this system. So that means these macrocyclic compounds remain very stable. We can isolate them again. We can reuse them. We can recycle them. Nothing happens to these compounds. So very, very efficient. Now the question is, what happens to the methylene blue? So in this slide, you can see that 1H NMR spectrum as well as the carbon-13 NMR spectrum, and you can see large number of peaks for the methylene blue. So once the methylene blue is used in presence of catalyst, you can see after some time a very few peaks are remaining in the 1H NMR spectrum, and after 100 minutes the 1H NMR spectrum become completely silent. That means there are no peaks. The peak at this 3.5 is because of the water. Similarly, in the carbon NMR spectrum also, you can see the large number of peaks which are coming from the methylene blue, and then these peak eventually disappear. Finally, we see only in the carbon-13 NMR single peak, and this single peak was coming at 169 ppm, and this is nothing but the carbonate ion, sodium carbonate particularly. So what actually happens, the methylene blue is completely degraded to carbon dioxide, nitrogen gas, water, sulfur dioxide, and chlorine gas. We have estimated using gas chromatography. We also estimated using various other techniques. And then the carbon dioxide is the only one which reacts with water to form sodium carbonate. How do we know that what type of species are actually participating? So we have done scavenger studies. For example, there are specific scavengers for the superoxide radical. For example, benzoquinone, tertiary alcohol can be used for the hydroxyl radical. Sodium azide can be used for the singlet oxygen, and EDTA can be used for the holes. And we can actually find out that primarily we have superoxide and hydroxyl radical, and very minute amount of singlet oxide and host. And we also find out from the EPR spectrum that these reactive oxygen species, because they are EPR active, we can also see the from the time dependent EPR spectrum the same thing. We have studied the Arrhenius plot to understand what is the activation energy. So the activation energy comes out to be 15.3 kilojoule per mole. It's a very small energy, and it actually says that the pathway is primarily radical based. So the two major species are hydroxyl radical as well as the superoxide radical, and we have used chemical tools, the assays to find out the concentration of these two radicals. For example, coumarin reacts selectively with the hydroxyl radical. It forms 7-hydroxycoumarin, which is emission sensitive, which is fluorescence active, and from there we can actually find out the concentration of hydroxyl radical, which comes out to be 6 micromolar. It's a very large concentration. Similarly, this NBT can be used because it forms formation after reacting with the superoxide radical, so that actually gives rise to a concentration of 7.43 micromolar. So this is the overall mechanism in which you can see that what actually happens. So these are the lanthanide-based macrocyclic compounds. So when the sunlight is flashed on it, it actually results in the star separation. So that means there will be hole and electrons, photoelectrons, and these photoelectrons will be used for the activation of oxygen, and this oxygen will form various radicals, and this radical will actually generate. So what we have done, we have used this concept for the degradation of large number of compounds, large number of dyes. For example, we can completely degrade methylene blue, we can also degrade acridine orange, we can also degrade azure green, rhodamine green, toluidine blue, malachite green. So all these compounds can be completely degraded, and we only see the formation of gases and some water molecule in these cases. Last slide, because I think I'm about to complete. So this example is like, how far we can go. So we can actually not only degrade the dyes, we can also degrade some antipsychotic drugs. For example, there are some drugs which are used for treating the psychosis. It's a very dangerous disease, and these drugs are chlorpromazine, thoridazine, and trifluoroperazine. So these antipsychotic drugs can also be degraded completely. So after the degradation, we only see gases and water, nothing else. So it's a very interesting research, and we believe that all our studies support that it is encapsulation-led degradation, because their compounds are able to activate solar energy, and then the radicals are generated, and these radicals are able to degrade these compounds. Okay, so summary, I think I have said in the beginning that I have shown some multiple assemblies, very simple synthesis, not very complicated. I have also shown that how to introduce hydrogen bonds in these type of assemblies. Then I have shown the applications in the sensing and recognition, in the catalysis, although we do a lot of catalysis, but today I have just shown one example. But towards the later part of the talk, I have also shown example in the photocatalysis, which is very, very interesting in today's time. Our approach is very modular. We can actually change the ligand, we can change the metal, and based on that, we can actually arrive at a variety of assemblies. We also have a number of coordination polymers, and they are also, very excellent photocatalysts. Hopefully, next time I'll be able to discuss something with you. So let me acknowledge, because none of the work which I have shown is done by me. So I have a fantastic, group of co-workers. So these are the ones who have done the work, and funding is from various sources: SERB, DST, CSIR, and earlier UGC, and the University of Delhi. And finally, I thank all of you for your time and attention. I'll be happy to answer any question if anybody has.
Yeah, thank you, Professor, for a very nice talk. Now the floor is open for a discussion. Students, if you're having any doubts, as I mentioned, like you can type in the chat box in YouTube. Okay. Actually, one student, Supratik Ghosh, he asked, like, can we use asymmetric synthesis for chiral catalysis? But I don't know, like, the question is not very clear.
No, it's all right. I think I can explain. Okay. So, yeah. We have some coordination polymers or metal organic framework in which the cavities are chiral. And we have already published, so these things are available in the literature. So these chiral cavities can actually support either the binding of one type of enantiomers, and then once you have the binding affinity for one type of enantiomer, then you can actually do catalysis on one type of enantiomer. So we are able to take up a racemic mixture And out of the recipe mixture, we have one type of product as the final product.
So hope, so Pratik, you got your answer. So any other faculty from IT?
I can see Dr. Konar raising his hand.
Okay.
Hello, Professor Gupta. Very nice, interesting talk. So in the last part where you have explained those lanthanide-based metal complexes, initially I was thinking maybe you might explore the emission properties of those metal complexes, but you haven't shown any of those. So do you have any plan further, maybe using those ligands as an antenna to excite your lanthanides and get some emissions?
Yeah, so Apurva, if you remember, I can go back to the slide. Remember that those lanthanide-based system we have synthesized using metalloligand, and those metalloligands have cobalt in +3 oxidation state, so they are colored. So what actually happens once the light flashes on it, so they absorb. They show good absorption spectrum, but then as you can understand, the energy is used in the promoting electrons, so they don't show emission. But then in solid state, we have seen that some PL they show. But then, these are the very interesting compounds because the metalloligand actually act as the photosensitizer, and then the lanthanide, they are actually working as the reaction center or the catalytic center where the activation is taking place.
Yeah, that's good. I was thinking that superoxide or hydroxyl radical, what you are getting, maybe because of the long lifetime of those lanthanides, that's maybe helping to get those reactive oxygen species. Yeah, I think, yeah, you're right. The cobalt is there. I just
you have a very good, you have a very good point. In fact, unless we go for some detailed theoretical studies, it would be difficult because these compounds show extensive conjugation. So metalloligand is in electronic communication with the lanthanide metals. So we are also interested, but I think for that I need to collaborate with someone who can explore their photophysical properties in more details, particularly from a theoretical angle.
Right. Thank you.
Akhilesh? You have to unmute, Akhilesh.
Yeah. Oh, yeah. Am I audible now?
Yes.
So thank you, Professor Gupta. Very nice and elaborative talk and very nice slides, I would say. Colorful and nice slides. And here, one thing I would like to ask, very early stage of your talk, where you started with 1+1 and 2+2, where you were showing the molecular docking, and when 1+1 was there it doesn't go inside and it sits just above the surface or something like that.
Right.
Then lifetime you compared between 1+1 and 2+2, where it goes inside, and there you said that lifetime decreases.
It increases. It actually increases, and then this enhancement is larger for the larger macrocyclic compound.
Okay, it increases. Okay, fine. So what is the control factor for 1+1 and 2+2?
It is
having the same metal ion, same ligand and everything, but sometimes it forms 1+1 and sometimes 2+2. So what is the control factor there? So
if you if you remember that slide, the first ligand has a phosphine group at the meta position, the second has a phosphine group at the para position. So the time you have a phosphine group at the para position, it cannot bind a single metal ion because the groups are away from each other. In that case, it goes for +2 cell.
Okay, fine. Okay, I got it. Thank you.
Yeah. Any other questions? We can take one more question if anyone having. Okay, if not, once again, would like to thank Professor Rajiv Gupta for a very wonderful talk. It's like a feast to our eyes, your presentation, where you have spoke about recognition, sensing, catalysis, and photocatalysis, and the final work like photocatalysis, where you are degrading the dyes and very toxic drug molecules. Actually, this is a very important topic that one should address. nowadays we are using a lot of drug molecules, but how to degrade, that is very important topic that we have taken, having a lot of importance at the current scenario. And this we'd like to thank you from the organizers for taking your time out and having here. Thank you, sir.
So thank you very much, and thank you, Professor Kari, as well as other members in the department. I think it's wonderful to interact with all of you, and I look forward to one day come over there and meet all of you.
Definitely.
Thank you again.
Thank you. Good afternoon, dear participants. Now, the next talk we are having from Professor Apurva Lal Kunar, Associate Professor, ISER Bhopal. So I'll give very quick brief introduction about the speaker. Dr. Apurva Lal Kunar, he did his master's in 2006 from IIT Bombay. After that, he joined to Jakob University, Germany, and he graduated. He got his PhD in 2009. Eventually, he moved to University of Oxford, where he spent his time up to 2012 for doing his postdoctoral fellowship. During that time, he also got a very prestigious Human Frontier Science postdoctoral fellowship. Then he joined ISER Bhopal in 2012. Currently, he's associate professor there. He has having more than 80 publications, and he graduated 6 PhD students, around 25 master students, and he's having a big research group. His research areas includes chemical biology, nanobiotechnology, biophysics, physical organic chemistry, and that move around drug delivery systems. Okay, and Dr. Apur, we are waiting for your talk, please. The floor is yours. You can unmute, please unmute.
A minute. Yeah.
Thank
no
you.
problem. So thank you, Professor Kari, for the elaborate introduction. And also at the outset, I'd like to thank organizers, RAIC 2022, for giving this opportunity just to tell small work that we have done related to inorganic complexes. And mainly I'll be focusing on the biological application of those luminescent metal complexes. So before I go to the topic of the presentation, I'll just quickly tell about ISERs, because we have many students, participants also they are there. So ISER, they're new class of institution. We have around 7 of them, and I'm in Bhopal. And these ISER, they're built actually just to promote the basic sciences like physics, chemistry, biology, mathematics. In India, like IITs, we have this Institute for Technological Advancement Research and educating students on technology. So ISERs, they're mainly built to promote basic sciences and their research and educations. So this ISER Bhopal is only 13 years old. So this is still a teenager. And you can see some of the pictures I have taken or is taken from our colleagues. And it shows that this, of course, the infrastructure is really new, as it is only 13 years old, and we have all the infrastructure that you can think of with good facilities. You can see in the NMR facilities, library, and the lecture hall complexes. And we are doing really good in chemistry in terms of nature ranking, and in the Indian context also we are doing really good. So this is one slide I want to spend on the research what we are doing in our lab. So we call it bio-nanotechnology lab, where we make a lot of different molecules, nanoparticles, and then they are mainly colored, mainly in terms of like color, they are fluorescent in nature. And we wanted to use these fluorescent materials for different applications like supramolecular organization, understanding subcellular properties, making new materials, color-based materials. And here are some representative publications, but what I wanted to tell you today about, I said, metal complexes, which can have some application in the biological aspect. So before I go to the main research what we have done, for the students also I wanted to tell a little bit about the luminescence metal complexes. So I've categorized them in different classes. So this will be the layout of the presentation. So I wanted to tell about the luminescence inorganic probes, mainly quantum dots, lanthanide based probes that we have heard from Professor Gupta, ruthenium, iridium. So I'll just discuss a little bit about why they are luminescent and what is the origin of the luminescence properties of these inorganic probes. And then I'll go to the research topic, what I'm supposed to discuss today about the biological application of ruthenium-based complexes as a photosensitizer, and we'll see how the local DNA microviscosity that tune the photosensitization properties and how we can use these ruthenium-based metal complexes to have them as a DNA roadblock where you can stop the polymerization activity that happens in the biological systems. So just to tell you about these first luminescent inorganic probes, which is semiconductor quantum dots, which is becoming popular for last 30 years or so, where you can see here these semiconductor nanoparticles, you have a core. Core is generally semiconductor in nature. So that means they have a band gap, which is not like insulators or not like a conductors, but intermediate band gap, where the core is comprised of this kind of semiconductor materials, and this core is coated with higher band gap materials like ZNS, and then these nanoparticles can be coated with various organic or polymeric materials, and which can be functionalized further with different kind of biomolecules to have their application in biological, to understand biological processes. But very interestingly, these quantum dots, they have size dependent properties. So that means if you take these quantum dots, same materials, but if you vary the size, depending on the size, they have different kind of emission properties. And this is very unique for these quantum dots. So that means you don't have to make new materials, but the same materials, if you vary the size, it will have different kind of color, emissive color. So why they have different kind of emission color? Just to understand that, so if you take about these kind of nanoparticles, so they have different atoms. When you have many atoms, they form bands. So you can have a valence band and conduction band. And if you reduce the size further and further, then you can have discrete energy levels rather than bands. And when you decrease the size such that when you have the radius, which is very close to the Bohr radius, that time you can have these materials can act as a quantum confined system. And if you shine light on these nanocrystals, which having dimension very close to the Bohr radius, you can generate hole and electrons. So these hole and electrons, they are together called excitons. When they recombine, of course, you can get emissions out from these nanocrystals. And these nanocrystals can be thought about particle in a sphere model. So that means energy is inversely proportional to the radius square. So that means if you change the size of these nanoparticles, the energy gap between your states will change, and that will change the emission color of these nanomaterials. So there's a nice review came last year in Science on kind of synthesis as well as application of semiconductor quantum dots. If you are interested, you can go through this. Now, these are nanomaterials, but when you move from nanomaterials to molecules, then of course we'll think about that you can have systems which you can think about that you can have these electronic systems where you can have electronic levels like singlet state, excited singlet state, excited second states, and then you can have triplet states. So, and these diagram basically very much used to understand the photophysical properties of molecular system which are luminescent in nature or fluorescent in nature. So these are called Jablonski diagram. So I'll just show you kind of schematically how it happens. So you have this lowest energy state, you shine light, so you can have excitation, you can go to S1 state, or you can go to S2 state, then you can have vibrational relaxation, you can have internal conversion, and then you can have also like internal conversion and vibrational relaxation to have a non-radiative pathways. You can have inter-system crossing from singlet to triplet, and then from the triplet state you can have emission, which we call phosphorescence, or you can have from the same spin state, which you can call it fluorescence. But sometimes some metal complexes or inorganic based probe, sometimes we do not know where from they are emitting. Sometimes this can be combined of singlet as well as triplet. So that's how we call them luminescent materials typically. So here is one example of luminescent materials, as you have heard earlier about lanthanide based systems, but these lanthanide based systems also can be emissive in nature. But what happened, these lanthanide based systems, as you remember, these are actually having f orbitals, and so if you think about transition from one f to another f orbitals, they are actually they are forbidden transitions. So that means they don't absorb enough light. So that's why the molar extinction coefficient from these complexes they are very weak. So that means only in the range of say only 10th. And as they absorb very little, so you cannot excite them efficiently using light, and you need something called antenna. So here antenna, you can see here the coumarin molecule, which can absorb light and transfer the energy to the lanthanide center, and the lanthanide center can give emission. So this is schematically shown here. So you have an antenna connected with a kind of ligating sites where the lanthanide can complex. So this antenna can be excited using a light. Antenna can give emission if this is emissive in nature, but mainly what happens, this antenna transfer the energy to the lanthanides, and the lanthanides gives the emission, and which of course we can call it luminescence emission that you can see. I'll just show you typical emission spectra and the kind of excited state depopulation of these lanthanides. So these are typical emission spectra that you can see. They are very sharp. So you can see they have a characteristic peaks, and these are the different states where from they can emit. And also I should mention here, depending on what lanthanides you have a different kind of emission maxima. Okay, and they are very characteristic for the lanthanides. So looking at the emission maxima and the nature of the emission spectra, you can tell what kind of lanthanides you have. And interestingly, of course, they are very sharp, and of course you are spanning almost like 500 to 620 nanometer in case of terbium. For europium also you can see you are spanning quite a good range of visible range. So that means they can be also used to kind of get emission in the whole visible range. Very interestingly, as these lanthanides, they cannot absorb enough light, or this absorption is kind of not allowed, so that coming back from the excited state to the ground state is also not allowed. So that means they wanted to stay in the excited state for a little longer, and you can see the lifetime of these lanthanide based complexes, like for europium and terbium, you can see they are in the range of milliseconds. Okay, so they are really high compared to typical organic fluorophore. What we can see the lifetime is in the range of nanoseconds. So they are also interesting class of luminescent inorganic probes. Now let's move to the transition metal based complexes. And these transition metal based complexes, like what I wanted to tell you today about ruthenium and iridium, so they have d orbitals, and generally this d z square and x square minus y square, they feel the interaction of the approaching ligand much more compared to the other orbitals. So that means, when the ligand approach in our octahedral kind of orientation, then there will be some kind of splitting of your d orbitals. And of course, we have learned in our early education that you can have this T2G and EG kind of states, they will be splitting too. And of course, if you have a ligand, like in this case, ruthenium tris bipyridyl, so you can have also the pi and pi stirred orbitals that coming from the ligand. And what can happen, then you can have this metal to ligand charge transfer states, and which is generally many times the cause for the emission of these metal complexes. So here is the typical absorption spectra that you can see for ruthenium tris bipyridyl in acetonitrile. And here you can see these are the bands, typical bands that you can think of. So these are the coming mainly from intraligand transitions, and the lower energy, longer wavelength bands is coming from these MLCT states. Also, I should mention here So as you have seen this Jablonski diagram, you have this singlet state. It can go to singlet MLCT states, but these states can quickly goes from singlet MLCT state to triplet MLCT states, which takes around femtoseconds. And this is very efficient. So quantum yield of this intersystem crossing is almost unity. So when it goes to these triplet MLCT states, of course, now it's not a spin allowed transitions. So that means this transition from the triplet state to the ground state will be not favorable. So that's why they stay also in the excited state for quite long time, but not like lanthanides in the millisecond. They stay almost in several hundreds of nanoseconds. So that means these metal complexes can have visible absorption as well as long lifetime, and they can be suitable for lifetime imaging as well as the fluorescence imaging and biological applications. Also, I wanted to mention not all metal complexes can be luminescent in nature. So it depends on the crystal field strength. So depending on the crystal field strength, you can have a kind of orientation of these d orbitals and MLCT. They can switch their positions, and when this d orbital they are the low lying, that cases, of course, you see non-luminescent metal complexes like we can see in case of iron. But in other cases, in the other extreme, like where you can have osmium complexes, but MLCT state that is very low lying. So that means the energy gap between your singlet state and the MLCT state, they are very low. That cases, of course, you can have more non-radiative decay. So that means these complexes also will not be very much luminescent in nature. But in case of ruthenium, of course, your MLCT state is not that much low lying. You have sufficient energy gap around 2 electron volt. They are highly emissive in nature. So in this presentation, of course, I wanted to tell you more about ruthenium complexes. But before I go there, I just wanted to quickly mention one thing which is very important for students about the optical purity of the sample. Many times we make samples and sometimes we measure their UV visible absorption spectra. And if they are emission, if they are emissive, sometimes we can also measure their excitation spectrum. Okay, so here you can see this is a pure sample. You measure the excitation spectra, and the excitation spectra, they match well with your absorption spectra. Another case, you have impure sample, you measure the absorption spectra, and you also measure the excitation spectra. They don't overlap with each other. So in this case, it indicates this absorption and the emission, they might come from very different species. Okay, so if you have an emissive species and if you have an absorption, you just measure the excitation spectrum just to understand the optical purity of your sample. Now, as I said, I wanted to discuss more about ruthenium. So here is a justification why ruthenium, they're better than other metal complexes. So ruthenium-based metal complexes, they are becoming very popular as a potential drugs because platinum-based anti-cancer drugs have some issues related to some kind of toxicity and also the resistance to the various cancers. But in that respect, ruthenium complexes, they have shown remarkable anti-tumor activity with good photosensitization properties. Sometimes you can make them really low toxic, as well as so far there is no drug resistance reported for these ruthenium complexes. And of course, when we wanted to use these kind of complexes for application, biological application, you need to know about what kind of targets or where these metal complexes are going to target in the biological systems. So here is a membrane, so it can damage the membrane, which is the boundary of the cells. It can go to mitochondria, localize, and then you can generate reactive oxygen species, which can destroy different kind of mitochondrial metabolic pathways. It can react to other organelle like endoplasmic reticulum. It can induce the stress in the endoplasmic reticulum and ultimately goes to apoptosis. So there are several pathways. Like it can also attack the nucleus, it can generate ROS, it can damage DNA, which can again cause apoptosis. So there are several pathways that can operate for these kind of metal complexes where you can kill or damage cancer cells. So for our case, we have selected these complexes. Of course, these I didn't make these complexes, so this was made by Professor Srikanto Patra's group in IIT Bhubaneswar. And of course, we don't know how to make this. Srikanth is expert in making these complexes very well. So he made different derivative of these complexes. You can see we are having this X, we have pyridine, benzene, thiophene, and of course, with some prior understanding that these kind of metal complexes can have very good DNA binding if you can tune these ligand properties. Of course, we fortunately got some extra structure of these complexes, and these are typical absorption and emission spectra of these complexes. So this is one of them. So you can measure the absorption spectra, you can measure the excitation spectra, so that you can justify their optically pure. You can see emission spectra, which is really broad, and also is emitting around 620 nanometer, which is good for biological imaging as well. So first thing what we did after getting idea about the optical purity and the absorption emission properties, we wanted to see how these complexes they interact with the DNA. So what we have done a titration using circular dichromism. So we have taken the DNA, we have measured the electricity of the DNA, and then we have added the increasing concentration of one of the complexes. And you can see there is a change in the electricity when you are adding more and more DNA. That indicates there is interaction of these metal complexes with the DNA. And of course, you have some structural change because DNA is a double helix. When these metal complexes, they will bind with this DNA, then of course, there will be some structural change of the DNA. So initially, of course, your this ruthenium polypyridyl complexes, they are weakly emissive. But if you add DNA, of course, it becomes highly emissive. As you can see here, we start with the metal complexes, then we add increasing concentration of nanomolar concentration of DNA, and you can see there is a significant enhancement in the emission properties of these metal complexes. So these are the representative examples. Of course, we have tested for other complexes also. After getting this enhancement in the emission, we also wanted to see how the excited state lifetime. So that means we excite these metal complexes, they goes to MLCT states, and how long they can stay in the MLCT states. And of course, the lifetime of these metal complexes in aqueous solution is around 100 nanosecond. But when you add DNA in couple of complexes, we have shown here for C2 and C4, you can see there is a huge enhancement in the lifetime. So of course, you can think about this is slope. If the slope is very fast, that means they are decaying faster. So that means they are not staying in the excited state for long. But when you add DNA, it interact with the DNA. They goes to the excited state and they stays for longer time. And these lifetime they are 1500 nanoseconds. So that means you have around 10 to 15 times enhancement of the lifetime. And that is plotted here. So this is the average lifetime with the concentration of the DNA, and you can see the lifetime from around 83 or 100 nanosecond is going to around 1.5 microsecond, which is like 1500 nanoseconds. So there is a huge enhancement in the lifetime of these metal complexes when they're interacting with the DNA. Of course, you wanted to know how these metal complexes interact with the DNA. So we have taken ETBR, which is known intercalator for DNA, which is not very emissive, very poorly emissive in water. When you add double-stranded DNA, of course, the ETBR can emit strongly. That's what biologists use to stain their DNA. But what we thought, if we can use these metal complexes and displace these ETBR from the DNA, then we can see that how these complexes, they're interacting with the DNA. So when we have done that, so if you remember that when you are adding DNA, there is enhancement, but when you are adding ETBR in this, so this is like a reverse kind of titration. You add RPCs to the metals DNA, there is enhancement, and then you add ETBR, and then you can see there is a decrease in the intensity. That indicates those ruthenium complexes that was interacting with the DNA is getting displaced by another DNA intercalator called ETBR. We have also done the same experiment using lifetime. So you can see initially there is an enhanced lifetime, but when you add ETBR, there is a decrease in the lifetime, significant decrease, and almost you can get back to almost the same lifetime what we can get for free metal complexes in aqueous solution. After this, we wanted to know further how it's interacting. So we know that it can be displaced by one of the intercalator, but is that a major group binder or minor group binder? So for that, we have done further experiments. We have taken West dye, which is known as minor group binder, and also we have taken spermine, which is known as a major group binder. So in these cases, again, we have taken the lifetime and we added this competitor for the minor group and major group, and from the lifetime changes, it confirms that it's actually minor group binder. Okay, so it can be displaced by waste. So also, as they can bind with the DNA, we thought if we can use these metal complexes as a roadblock where DNA polymerase, they latch on this, and during replication of the cells or DNA replication, this polymerase makes more and more DNA, which is kind of one of the region where you can have this replication of the DNA. And when you have the new cells, you have to have the same type of DNA sequence, and it has to be very fast in case of cancer growth. So that means we thought as these metal complexes can bind with the DNA, so and they can act as a roadblock. So that means when the DNA polymerase will work making another replication, another copy of the DNA, their progress will be inhibited by these roadblocks. And we have done experiments using polymerase chain reactions. So because this polymerase activity is very important for the replication and cancer progression, so if we can stop the replications, we can again kill the cells. So what we have done polymerase chain reaction, PCR reactions, and in those PCR reaction, even different concentration of the metal complexes, we have kind of quantified the intensity of the band that is coming from this polymerase chain reaction, and we can see after certain concentration, we don't see the intensity of the band. So that means the polymerization process is getting inhibited. So that we have done for different polymerases, Taq polymerase, Q5 and POFU. These are the commercial polymerases. And one can have PCR machine, you can use these in presence of the metal complexes, and these are the quantification. So you can see in presence of the metal complexes, there is a significant reduction in the intensity. That means the polymerase activity is getting inhibited by these metal complexes. Okay, so these are actually iridium-based complexes we have done, but the principle is same like the ruthenium complexes. So then we wanted to know why there is enhancement in this fluorescent intensity and the lifetime. So we performed experiments. So we had some idea that when we are increasing the viscosity around the DNA, when the metal complex is binding to, it might cause the enhancement in the fluorescent intensity and the lifetime. So first we have checked the emission intensity of the metal complexes in different percentage of ethylene glycol, and we can see when we are increasing the concentration of ethylene glycol, which is increasing the viscosity of the solution, we can see a linear increase in the intensity. Same we have observed when we have done for DNA that you have seen. But also what we have done, we have taken the metal complexes and increased the percentage of the ethylene glycol. So that means it's increasing the viscosity of the solution, and we can see again the linear dependence of the average lifetime increase with the viscosity. So that means when these metal complexes, they're interacting with the DNA, there is a significant enhancement in the local microviscosity, which is causing the enhancement in the lifetime of this. So as we increase or enhance the lifetime by 10-fold, so we thought they can be very good photosensitizer, because in the excited state they are staying in the longer time. So that means you have without DNA, so they have a high non-degradative pathways and short average lifetime. But when they intercalates with the DNA, you have low non-degradative pathways and long average lifetime. So that means the metal complexes, they are staying in the excited state for quite long. So that means they have possibility to interact with the molecular oxygen that is dissolved in the solution, and that means this triplet oxygen can be converted to the singlet oxygen by the excited state lifetime of these metal complexes when they interact with the DNA. So that's what we have used. And of course, for the detection of the singlet oxygen, we have used this well-known cycloaddition reaction that we learned in our school, that ring in the middle is kind of reactive, because it's kind of give a product which is even stage aromatic. So this is the endoperoxide formation for anthracene. But as we are using these metal complexes in aqueous solution, we cannot use normal anthracene. We have used water-soluble derivative of anthracene, and we have used this singlet oxygen that will be generated from these metal complexes upon DNA binding, and you can see endoperoxide generation. And these process you can follow by the loss of this chromophoric unit that is coming from the anthracene. So this is the typical anthracene emission. But moment these anthracene interact with singlet oxygen from the endoperoxide, chromophore is lost, and then of course you'll see a significant decrease in the emission intensity without much change in the intensity that is coming from the metal complexes. So this indicates that these metal complexes, when they interact with the DNA, they can generate singlet oxygen efficiently. Of course, we have quantified the yield of the singlet oxygen generation. We have done experiments in different kind of isotopic conditions just to understand the efficiency of the singlet oxygen generations. Later, after getting idea that they are generating singlet oxygen because of their enhanced excited state lifetime, we wanted to understand the photocleavage efficiency of these metal complexes, the DNA photocleavage efficiency. So what we have done, we have taken plasmid DNA, and of course these are the DNA gel that you see. These are the supercoiled DNA. These are the nicked supercoiled DNA, and these are the different time. So this is complex 1, complex 2, complex 3, complex 4, and the 0 to 0.5. These are the time in hours. So that means these are the irradiation time. So these we are using light to irradiate these metal complexes when they're interacting with the DNA. So you can see for the first lane, when we are interacting for 2 hours, you don't see much changes from supercoiled to nick. Okay, the second lane. But when you have used the metal complexes, you look at this 1 hour and 2 hour, you see a significant reduction in the intensity in 2 hours and 1 hour. And in case of third and fourth, you can see there is almost no band that you see in 1 hour. So that means complex third and fourth, they are very efficient to kind of formation of nick in the DNA. So that means the cleavage of the DNA, and because of that, you form the supercoiled to the nick DNA. So that means we can efficiently cleave the DNA using the singlet oxygen that we can generate from these metal complexes. And we have done also in presence and absence of light, just to understand the effect of light, because the excited state lifetime, that is important. So of course, in absence of light, you don't see it, but in presence of light, again, you can see the formation of this nick DNA. So this is also kind of quantified with different concentration of the metal complexes, and you can see these are color code for different complexes with different concentration. So which indicates, again, in presence of light, DNA can be cleaved because of the interaction of the metal complexes and the DNA. After this, wanted to go further just to inhibit the bacterial growth, and so this is under dark, you don't see much effect. But when you do in presence of light, in different concentration of the metal complexes, you can see there is an inhibition of the bacterial growth, which we have monitored around 600 nanometer, which give a scattering. And this is one way to monitor the bacterial growth at 600 nanometer. So when you have monitored at 600 nanometer in different concentration in presence of light, we can see significant reduction in the bacterial growth. This we have also monitored by SEM. So you can see these structures here for the bacteria. So they are like, you can think about kind of three-dimensional structure. So these are the typical E. coli bacteria that you can see. So we have checked in presence of light without any metal complexes, they can still retain their structure. But when you use the metal complexes in presence of light, you can see these bacteria, they are getting degraded. And some of them, you can see the membrane is getting distorted here in the image at the right hand side here. Okay, so this we have not only checked in E. coli, but we have checked in S. aureus, other bacteria also, typhi, Facilius. Okay, and wherever, and in all cases, what we see in the dark and light, there is a significant reduction in the optical density, indicating there is an inhibition of this bacterial growth. Doesn't matter it's a gram-positive or gram-negative bacteria. We have further checked this under fluorescent microscope. Of course, bacteria, they are much smaller, in around 1 micrometer. So getting good resolution is always difficult with the bacteria compared to mammalian cells. But you can see these bacteria, they are stained with popidium iodide, which can interact with, and you can see these nice fluorescence images that you can get from these bacteria. So this is no light, no metal complexes. But when you have used light, no metal complexes, you can still see the morphology that is kind of intact on these bacteria. But when you have used light and metal complexes, you can see there is a significant distortion and the damage of the bacterial membranes, as well as some of the bacteria. You can see only what you see is the debris that is coming from this bacteria. Okay, so that means we can efficiently kill bacteria, which is proved by SEM as well as these fluorescent microscopic measures. So later, what we wanted to see what happened in mammalian cells. So we have taken two different cells. One is melanoma cancer cells, B16F10. Another is HEK293, which is normal cells. And you can see they are not that much toxic. So that means you need really, really high concentration, around 75 micromolar for these. For cancer cells, you need around 12 micromolar. This is the IC50 values. That means this is the 50% of the inhibition that happens at 12 micromolar for this cell line, and for HEK you need around 75 micromolar. So they are not that much cytotoxic, but they are little toxic to the cancer cells. So why is that? We have also done live cell imaging. So these are the cells from melanoma cancer cell B16F10. When you have incubated with the metal complexes, you can see all those metal complexes, they are getting accumulated in the middle, which is actually the nucleus of the cells. Okay, so that means these metal complexes can penetrate the nucleus and gets localized in the nucleus and can interact with the DNA. So this also we have quantified for again B16F10, and you can see that line profile indicates that they are in the center of the nucleus, center of the cell. This we have when we have done for another cell line, which is normal cell line. We don't see the intensity that's getting accumulated in the nucleus, but they are kind of outside of the outside the nucleus. So that means it's also getting localized inside the cells, and in cancer cell they're getting localized in the nucleus. Okay, so I think that's all I have. So this is the summary of the presentation. So we have developed these ruthenium polypyridyl complexes. We can enhance the lifetime by the DNA intercalation. When their lifetime is getting enhanced, they are generating singlet oxygen, and singlet oxygen can kill again bacteria as well as the normal cells. Okay, so finally, I'd like to thank Professor Shikanta Patra for giving the opportunity, as well as the fruitful collaboration we had over the years with all this exciting chemistry that we do with these metal complexes. So this work was done by Paltan Laha, a student of Professor Shikanta Patra, and a couple of my students, Falguni Chandra and Prasant, both of them graduated. Paltan, I suppose he's submitting his thesis soon. So this is my this is the funding agency who supported our work, Imprint, ACRB, and ISR Bhopal and IIT Bhubaneswar. This is the current lab members I have. Generally, they do all the hard work, and I present the work. And thank you very much for your kind attention. I'll be happy to take any question you have. Thank you.
Thank you, Dr. Apur, for a very nice talk. Now the floor is open for discussion. Actually, one student, Arnab Mondal, I think, he raised a question, and he asked like, after ruthenium complex, when it is binding with the DNA, why there is enhancement of emission intensity?
Yeah. So as I have mentioned earlier, so one thing is very important. So these metal complexes, sometimes when you have this ligand, which can be little flexible, when you have a flexibility and the interaction with the solvent, they can have a non-radiative pathways. But when they feel local microviscosity, which is much more viscous compared to water, what happens? These groups, they cannot rotate that much. Okay, so if they cannot rotate that much, what will happen? The non-radiative pathways, that will not be that much significant. Okay, if the non-radiative pathways, they are not that much significant. If you see the structure of these molecules here, so you have this pyridine, phenyl, or thiophene. So this group can rotate and then can have more non-radiative pathways. I don't know, you can see it, I think still is moving in the YouTube, but so if you remember the structure of those metal complexes, we have some extension of this polypyridyl backbone, where we have this pyridine, benzene, and thiophene, which can rotate Okay, and if you can stop the rotation by increasing the viscosity locally or by intercalation with the DNA, what will happen? Then you can reduce the non-additive pathways, and there is a enhancement in the intensity. Okay, that you can see in the lifetime as well. Is that okay, Anirban? Arnab?
Like, yeah, Arnab, he cannot respond, but I think okay.
Dr. Kari, I have a question.
Yeah, please go ahead.
Yeah, thank you, Professor Koner, for a very nice talk, and it looks like you have expanded your area into a variety of fields. I enjoyed your lecture. I have a couple of I probably am confused. So now your ruthenium complexes that you shown in place of utilizing with polymerase. Do you think your ruthenium complex bind to double-stranded DNA or single-stranded DNA?
It binds to double-stranded DNA.
How then, when you are doing polymerase chain reaction, your first stage is to unfolding the DNA. So how do you make sure that your ruthenium is still bound there and making a roadblock?
So in the first step of this polymerization is like you have a double-stranded DNA, and then you are unwinding this, and then your primer is binding to this, and your polymerase is acting, right? Yeah. But suppose your metal complexes, they are binding to the double-stranded DNA, then possibly what will happen, the unbinding process plus the binding of the primer, that will not be also that much efficient, because you are already kind of wrapping your DNA with these metal complexes. Maybe their structural distortion is also there, as we have seen from the CD spectrum. So what I suppose, so these are done actually in the polymerase chain reaction. These are not done in cellular system where you can, but basically what I can think of, that you have a double-stranded DNA, they unwinds, and then your primers bind, and then you can have a polymerase activity, right? So if your DNA binds,
No, that is why I when I saw your DNA gel, that's why that's raised the alarm in my brain. You saw that when you're increasing the concentration of your complexes, and you see nothing. So there could be two possibilities, and that's the suggestion. We may look at it later on. One possibility is that your complex is actually affecting the polymerase, and that's why the polymerase is nowhere able to do the job.
Yeah, we have checked that inhibition of the polymerase. So we have increased the different percentage. So what DNA band you are seeing, this is actually for the product. Okay, this is not for the DNA. So this is for the product. And also what we have done, we have incubated the polymerase with different concentration of the metal complexes, and then we have used that polymerase again to use it further for the polymerase activity, but we haven't seen any inhibition of the polymerase activity. So we feel that there is no interaction of the metal complexes with the polymerase.
Okay, yeah, that's okay. We can discuss that thing later on, but just check it out. And one more question also I have. I saw your propydium iodide, the labeling, live cell imaging. Yeah. So when you do propydium iodide bound to the E. coli, are they live or dead? The cells are.
So these actually we wanted to keep them not alive, because when they move fast, then sometimes very difficult to image them. Hello? Can you hear me?
Yeah, I can hear you. Yeah.
Yeah. So we wanted to make them not alive, because sometimes they grow fast, sometimes they move. So we wanted to also kind of keep them like, I think these are treated with sodium azide also, so that they don't move faster. So these are kind of, you can think about kind of dormant E. coli, so they are not live and growing. Okay, because imaging live bacteria is very difficult. That's what we have realized. And then of course, these are actually done in between two cover slips, and then of course they are treated with sodium azide, so that at least the metabolic activity is little reduced.
Okay. Yeah, propydium iodide can fluoresce on its own. I mean, when it goes inside the cell, and only it can goes inside the cell if your complex is harming the membrane actually of the E. coli, because propionamide can actually fluoresce when it binds to DNA.
That's what you see, but in the background, you can see in these slides, the background, they're not giving that much emission, right? So that means definitely there is interaction.
That's why, that's why, because then that must be the cells are actually alive, and that is in the absence of the your complex. But anyway, it's a very fantastic, work. You've done a good amount of job, and it's very interesting. So thank you for your presentation, and I appreciate it. Thanks a lot.
Thanks, Rana. And Dr. Apurva, can you take 2 more questions, because our students, they're having. Arnab Panda, he asked, like, the ruthenium complex, are they stable in blood pH? Can we make like target specific one? So that is a question from
we haven't done anything in bloods. But of course, we have done different pH dependent studies where it indicates that pH doesn't have much effect. Of course, if you go to very extremely high pH, there might be some effect, but in physiological system, you don't need to go to pH more than 8. So we are good with actually pH 8 and pH 4. pH 4 to 8, there is no problem. And if you want to make them targeted, of course, we can think about attaching some antibody, or we can conjugate these metal complexes with specific antibody that can be selective towards specific cancers, like some kind of growth factor receptor that is there, gets overexpressed in different cancer cells. So maybe if we can target using some antibodies conjugated with these metal complexes, yes, we can make some targeted delivery. Yes.
Yeah, Anurab, hope you got the answer. Yes, they are stable in blood pH, and you can. Okay. And one last question from Subham Kumar Panda, our PhD scholar from IIT Bhubaneswar. He asked, like, he appreciated that very nice presentation, and he says, like, what kind of ligands can be used to prepare this ruthenium of lanthanum complexes? Sorry, to improve the luminescence of lanthanum complexes.
Yeah, so generally should be highly absorbing. Like you can see that example with coumarin, naphthalene, anthracene, even pyridine, those kind of antenna where they can have very high molar extinction coefficient. That means they can absorb a lot of light. Can be good antenna, okay, and can transfer efficiently the energy to the lanthanides.
And there is one last question from Sartaj. He says, like, if these ruthenium complexes get functional issue with carbon quantum dots, so can we expect some interesting applications in these type of DNA binding?
So it depends. Carbon quantum dots, you have a lot of different functional group. If I remember, you have hydroxyl carboxylic acid group. You can functionalize, but I cannot guarantee that upon functionalization, it will still retain the DNA binding activity. Probably what I guess, you might put a linker between the carbon dots functional group and the metal complexes. So if you can suitably functionalize with suitable linker, but the metal complexes, they'll be little outside and able to bind with the DNA. I think you can do that. I don't see any problem with DNA binding, but you have to have a linker between your carbon dots and metal complexes.
Sartaj, hope you got your answer. So with that, like, okay, we are running short of time. So with that, we'll stop this question answer session. And once again, we thank Dr. Apurva Koner for his very nice talk. Okay, and actually, you have taken me like 4 or 5 years back, like where we also have done similar kind of work by using some polymers, ionic polymers, and we studied how this interaction will be by using all these kind of studies. Very nice and interesting work that you have presented. Once again, we thank you for your time, for giving a very nice lecture. Thank you so much.
Thank you. Thank you very much. Yeah. Thank you.
With that, we'll move on to last talk for this session. For this, we are having Dr. Akhilesh Kumar Singh from IIT Bhubaneswar. He is our own faculty. I'll give very quick brief introduction. Dr. Akhilesh, he did his MSc from BHU Varanasi in 2001. After that, he joined in IIT Kanpur for PhD, where he graduated in 2007. After that, he did his postdoc in Germany as well as France from 2007, 8, and 9. Then he joined IIT Bhubaneswar in 2010. He's working in chemosensor, preparing different kind of magnetic materials. He's also working in MRI contrast agent, developing a new reagent for MRI contrasting agents. And his research group also working on ionic liquids, using different kind of ionic liquids in lithium-ion batteries, so on and so forth. He guided 3 PhD students successfully, and I think 6 PhD students are working with him. He's having more than 30 publications in very reputed international journals. And this short discussion, I invite Dr. Akhilesh to give his presentation. Thank you.
Thank you, Dr. Kari. Very nice introduction. And I would like to thank the organizing team to this RAIC 2022, and a special thank to the convener of RAIC 2022, Dr. Shikant Patra, who has given me opportunity to discuss my research findings on this forum. So just provide me some time to share my slide. So my slide is visible now?
Yes, yes.
Yeah. Thank you. Somewhere mic is on, because of that I'm getting echo. Could you please put off the mic? Yeah. So today I'm going to talk about molecular probes for magnetic resonance and fluorescence imaging. Okay. So before starting, I will give a brief overview what kind of research work our group is involved. So we work in 3-4 areas. So first area is ligand directed self assembly. Here we try to make some polytopic ligands, and with that polytopic ligands, metal complexes we isolate so that it will be self-directed. I mean, ligand will be directing to form the N cross N grid kind of complexes, 2 cross 2, 3 cross 3, or 2 into 2 cross 2, or 2 into 3 cross 3, something like that. It will be just totally directed by ligand, and it will form a self-assembly. Once we get the self-assembly, then we try to do its coordination chemistry, like its redox properties, its electronic properties, and then magnetic properties, and all the spectroscopic characterization like EPR, Mossbauer, and other things we study. And that is the one part of research. Second part, we do taking the same coordination compounds. Basically, I'm a coordination chemist, so I use the coordination compound for different purposes. And second part is MRI contrast agents. So here we design the macrocyclic ligands, and those macrocyclic ligands we design in such a manner that they are metal complexes. They will be soluble in water, and once they are isolated in pure form, so they are used as a contrast agent, MRI contrast agent. So here basically 2 kinds of contrast agent we are right now just focusing on: T1 based contrast agent and also the Padhasarat based contrast agent. So T2 we are not paying attention to. So this part I will be talking about in my talk today, and also further the third part of my research in my laboratory is going on, that is the ionic liquids as electrolyte additive in lithium-ion battery. So here basically we design the task specific ionic liquids, and those ionic liquids we use as the electrolyte additive to lithium-ion batteries, and we try to improve the like performance of battery. And one thing here I will say that fossil fuels, they are very limited in means a quantity. So after some time, there is a need of alternative source of energy. So here we thought that this is the thrust area of energy. So very recently we have started using the ionic liquids for this as an electrolyte additive, and so that it can improve the battery performance in terms of Coulombic efficiency, also its the cycling performance, and then all these things are based on solid electrolyte interface formation during the cycling of the battery charge discharge cycle, and that's how its life is little bit enhanced. And also these ionic liquids play a very crucial role, making it safer because they are non-flammable in nature, these ionic liquids. So if you put there, as compared to organic electrolyte, these are safer in terms of flammability. The fourth part, that is the fluorogenic and chromogenic chemosensors. Here basically we design the molecular probes, and with that molecular probe we try to sense some specific kind of metal ions, or not only metal ions, like those analytes, different analytes I should say, and those analytes could be environmentally active, biologically active analyte, and also some like biogenic amines, small molecules like water, those moieties we try to sense that one. Okay, so now moving to my first part of the talk, which I will be talking about MRI and contrast agents. So first thing, that why one should work on MRI contrast agent, because MRI is a very safer technique. The advantage of MRI is that it is non-invasive. So unlike many other techniques which are uses ionizing radiation, so there cell death and other problems are there which is not possible in MRI. So here basically on what principle it works, the molecular interaction of water molecules with macromolecular structure like proteins, cell membranes and other things these are the responsible for contrasting the image here. And MRI image are required mainly depending upon the inherent differences in water proton density, and thus they just modify the T1 relaxation of the water proton, and that's how they just give the contrast. So contrast, what is contrast? That also we have to understand here, that the contrast is the difference in luminance that makes object distinguishable. That means less darker to more darker, or less brighter to more brighter, and that's how two images are distinguishable, and that help in my medical diagnosis. Okay, so three types of contrast agents are available: T1 based, T2 based, and Paracelsus based contrast agent. But today I will pay attention only to Paracelsus based contrast agent. These kinds of contrast agents are relatively very new, because earlier T1 and T2 based contrast agent for a long time they are being used, and the problem there was the leaching of the metal ion, and lot of companies were being sued in USA because of this leaching, and after a long time their effect is just observed in the body, and lot of like patients, they sued the company that because of those contrast agents I have such kind of problem. So these Paracelsus contrast agents, relatively those are safer, and here also they are the less time consuming. So here we will just first see that what are the cis contrast agents. They are the promising alternative to traditional T1 or T2 relaxation agents, and also this is very much responsive towards change in pH and temperature. So all of us, we know that any tumor tumor cell, if you take it, so extracellular tumor pH is always acidic in nature. However, the pH of healthy tissue is slightly alkaline. So if it can respond to pH, then always it will be very much beneficial, and this can differentiate between the image of healthy cell and damaged cell. And this is selective, because when you use the pre-saturation radio frequency, then only it turns on, and otherwise on general normal radio frequency, the image is just off. Because of that, normal image will be just obtained. And it is very time and cost effective. Why time effective? I am saying that normal T1 and T2 based contrast agent, if you take it, then pre-injection and post-injection scan is necessary. But here, at the same time, just whenever you are using the radio frequency, then only you get the enhanced image. Otherwise, you just get the normal image. So immediately you can distinguish between two images. So now the little bit principle about the contrast works. Here basically there are two pools of protons here. So as I said that here everything happens with the water protons. Okay, so these protons, two pools of protons are, one is from the exchangeable protons present in the contrast agent, and second one will be the water proton. So what will happen that there will be exchange of these ligand proton which are the exchangeable with water, and then based on that you get all the signals. So first you illuminate this one, okay, with a radio frequency, you pre-saturate this one, and once you pre-saturate, then their intensity goes down, and when it goes down, that means you have pre-saturated. That means what? The down spin and up spin, both number population becomes equal, then that stops, like its signal is just diminished. And after that what happens that those electrons, sorry, those spins starts exchanging with the normal pool of the water protons, and that's how this process keeps continuing, and because of that you get better and better enhancement. So this CEST percentage, how much percentage CEST enhancement will be there, that depends on this formula. So here one can easily see that all those things, these factors like number of exchangeable protons, concentration of contrast agent, exchangeable rate constant, and then this mz by m0 value, and all those things affects the percentage CEST effect, that means CEST intensity. Only one condition is there, that whenever you are having such kind of system, so delta omega, which is nothing but the difference between the bulk water proton signal and then your exchangeable proton signal, like NH or something is there. So this one, if you have the delta W, that means difference between the chemical shift of this NH and bulk water, so that is delta W must be greater or equal to exchangeable rate constant, exchange rate constant. So how you can improve the CEST percentage, that means CEST intensity? So for that you can just larger the concentration of CEST agent, because this is in numerator, so increase the concentration of CEST agent, then your CEST percentage will be more, and also more and more number of exchangeable protons are there, then that will be better, and large value of K exchange. But this K exchange, this criteria must be fulfilled, that delta omega must be greater than K exchange, and large value of T1 and low relaxivity. So this is the difference here. You can notice here that unlike T1 contrast agent, where the relaxivity, ultimate aim is what? To increase the relaxivity, or in turn you can say that to decrease the T1 relaxation time. But here it is just opposite. So what kind of system we have utilized for that? So this, the macrocyclic ligand. And why we take macrocyclic ligand? Because I said that we take it for to avoid any leaching problem, and also stability will be more once the complex forms with that, and then that compound will be very, very stable, and metal ion won't come out of the ligand cavity. So we prepared two complexes, cobalt and nickel, and these compounds were paramagnetic in nature by their magnetic measurement, room temperature magnetic measurement. We could find that. So now the next job was to find out the exchangeable protons are there or not. So for that we did the NMR spectroscopy of these ligands, complexes. That means these are the paramagnetically shifted NMR spectra, and first in DMSO D6 and after that in D2, that means aprotic and protic solvent, and that clearly shows that some exchangeable protons are there which are missing when we are going from DMSO to D2O. So on that basis, first we identified, and we can see that one is at say 80 ppm, another one is approximately around 70 ppm. So here it is written that cobalt complex 63 and 68 ppm exchangeable protons are there. So for them the CEST spectra was recorded, and after that now I am going to discuss that CEST effect for cobalt complex. Basically here cobalt complex, you can see that that was the better para-CEST effect. This gave the 30% CEST intensity as compared to nickel complex, which gave only 6% CEST intensity. So this cobalt compound outperformed. This was much better as compared to. Then, as I said, that they are very, very much responsive towards pH. So pH dependent CEST activity also we measured, and that we could find that at higher pH the CEST activity was higher as compared to lower. But physiological pH around this around 7, if we see, that was also quite a bit like 20% kind of CEST activity we saw, which is the very good CEST intensity. And also what we found that percentage CEST activity, when we increase the concentration of that cobalt complex, it was higher and higher, and which is in line with the whatever equation just now I have shown. And also here you see that around pH, so the same thing here manifested at approximately 7.8 pH, it was higher. So now just for the application purpose, we thought that why not to check in different media. So 4 different media we chose, and one is the Herpes buffer, second rabbit serum, and fetal bovine serum, and also the agarose gel. In all 4 media, we could find very good CEST effect. Approximately, you can see that in Herpes buffer 30%, rabbit serum 28%, fetal bovine serum 25%, and agarose gel 23%. So it is very good CEST activity. So one might ask that why the CEST activity is decreasing from one media to another media. So that is because the decrease in CEST effect can be attributed to increase in longitudinal rate constant of the amide protons when we go from Herpes buffer to rabbit serum to FBS and agarose gel. Because of that, this is little bit decreasing. But after decrease also, it is quite a bit sensitive towards the end. It shows the excellent CEST activity. So there, whether we check that whether this effect means this condition delta omega must be greater or equal to exchange rate constant. For that, we just measured this one mz by m0 value versus 1 upon omega 1 square, and then from there we determined the rate constant, and that was exactly in line with this equation. And also for the application purpose, we thought of checking the MTT assay, that how much our compound is tolerant by the normal system. So MTT assay, we did it, and there it was found that 75 millimolar kind of concentration, if it is there, then it is tolerable. So it is not very toxic molecule. Next is the stability in different conditions. Also, we checked it. Why? Because the normally if you inject inside the human being means a body, then what happens? There are a lot of different ions are there. Okay, like zinc 2+ ion, sodium chloride, and other things, and a lot of anions are also there. And also the pH might vary, acidic or basic or something. So those parameters we took into consideration. And in acidic condition, and in presence of zinc ion, and also in presence of anions, and we measured the its stability. And stability, while measuring, we did not forget to use the sodium chloride and this trimethylsilyl 1-propansulfonic acid and all the sodium salt, everything we added, so that we can mimic at least the near by to the real system. And what we could find that up to 72 hours, in acidic condition, only little bit dissociation was observed, 6%, which is very nominal. And in presence of anions and cations, up to 72 hours, there was no dissociation. So our compound were very tolerant and also very stable. So it's biocompatibility and T1 phantom image also we just wanted to measure. Why? Because how much in vitro, like in vivo activity, we could not check it. So we thought of taking the phantom image in NMR tubes, and in this kind of condition, varying the percentage concentration of that 1 millimolar, 3 millimolar, 5 millimolar, and all different concentration of paracest compound. And then what we found that when we take up to 10 millimolar, like from 1 millimolar to 10 millimolar, contrast was increased monotonically. Okay, so MTT assay also tells that this is very much tolerant and not very toxic, and also in vitro activity it shows excellent behavior. But in vivo activity we could not do because of the lack of infrastructure. So in order to summarize that work, here I can say that in all 4 medium we got very excellent CEST effect, and also cobalt complex was better CEST effect as compared to nickel complex, and in phantom image it shows the excellent contrast behavior, and it was pH dependent, which was the prerequisite, because I said that in tumor cell pH variation that plays a very crucial role, pH and temperature. So here at pH also around physiological pH it shows excellent behavior. So I am now moving to the next part of my talk, which will be covering the optical imaging with fluorogenic and chromogenic probes. So now question arises that what is the need of sensor? So sensor, actually these are used for different analytes, and those analytes are very much useful and involved in different kinds of application. Like first one, let us talk about clinical diagnosis. So they are ATP, ADP, DNA, RNA. These analytes are very much useful, and like for acid rain eutrophication, CN-, Cl-, NO3, phosphate, and all these are very much crucial. Like for chemical warfare agent, that explosive, TNT, and phosgenes, these are very crucial. So imaging or just sensing very much selectively this kind of things with a low cost method and quick response, that is very compulsory and necessary. So these are the different like health hazards and solvent contamination, like water. I said that small molecules, so these are present as a contamination in many solvents. So if you have an excellent sensor and quick sensor which is cost effective also, that is always a better suitable choice. So for that, we just design some chemosensors. So those chemosensors, first we have to understand that what are these consists of. Chemosensors are of two types. One could be colorimetric and another will be fluorimetric. So colorimetric chemosensor, that means it just varies its color and wavelength, based on like in presence of analyte, immediately it changes its color, and that's how from naked eye you can monitor. And fluorometric chemosensors are those which changes its fluorescence intensity either from off to on, or maybe enhancement in the fluorescence, and they can be measured by emission spectroscopy. So what happens that one signaling unit is there, and this signaling unit actually is connected to link to some binding unit, and they are targeted, and light comes and then binds it. When it binds, and that message through linker, it reaches to the signaling unit, and signaling unit has some fluorophore or chromophore, and that is manifested or that is observed as a response either by color change or maybe change in the fluorescence intensity. So what are the advantage of these sensors? They are easy to use. They are very less expensive and very sensitive, and their response time is very fast. Like immediately you can add it and immediately color change or fluorescence change, and something you can just monitor by your naked eye. Real-time analysis happens quick, on the spot analysis you can do, and very low detection limit in terms means in the range of nanomolar or maybe picomolar or micromolar. These kinds of detection limit they have, and they are having the variable receptors. So all these things, everything like this one, Dr. Kohner just now he talked about the Jablonski diagrams. He already simplified my life, so this I am not going to talk about here. That means very simply I can tell that it absorbs light. Any fluorophore absorbs light and it goes to excited state, and from there maybe by vibrational relaxation comes to lower excited state of singlet, and from there if it comes to ground state, then it is the fluorescence. Otherwise it might go to by intersystem crossing to next triplet state, and from triplet state when it comes to ground state, that is the phosphorescence. So fluorescence and phosphorescence combined way, they are known as luminescent materials. So these luminescent property will be exploited as a sensor. So next I will talk about little bit mechanism. So conventional mechanisms for these fluorescence or this kind of chemosensor, those are the intramolecular charge transfer, ICT, metal to ligand charge transfer or ligand to metal charge transfer, photo-induced electron transfer, Foster resonance energy transfer, excimer exciplase formation. These are the very conventional kind of mechanism, long lasting, means for a long time they are in use. Relatively new or emerging mechanisms are there, which are the aggregation induced emission, CN isomerization, chelation enhanced fluorescence, and then excited state intramolecular proton transfer. So all these kinds of systems we have used where one or another mechanism is involved, which we will be talking one after another. So fluorescence mechanism, here I have just summarized all the new emerging mechanisms. So ESF IPT, what it is that excited state, once it absorbs the light, it goes to excited state, and in excited state it does the intramolecular charge transfer and intramolecular proton transfer, and because of that it changes its form from enol to keto or keto to enol, and then from there it now undergoes the radiative path, by radiative pathway it emits, and that is the fluorescence is just recorded. Second one is that TICT. TICT actually it is a link between donor and acceptor moieties are there in that receptor. So receptor means chemosensor altogether. So donor acceptor molecules are interlinked. When they absorb light, it goes to excited state, that is the local excited state, and there the charge transfer and intramolecular, like twisted intramolecular charge transfer, its name as it suggests that there is a twisting along the single bond, twisting and charge transfer that takes together, and in twisting what happens, little bit energy dissipation and it goes towards the non-radiative pathway, and then energy is decreased, and from here when it comes to ground state, that leads to fluorescence, and that is called twisted intramolecular charge transfer. Another one is aggregation induced emission. So aggregation induced emission, what it is, it has lot of kind of rotors, and these rotors are freely rotating. Then when you put the suitable solvent in that condition, what happens that there is aggregation, and because of that one molecule is stacked over other, and because of that what happens that this rotation about single bond, those stop. So restriction of intermolecular rotation leads to aggregation, leads to fluorescence enhancement, and that is called aggregation induced emission enhancement. Next one is ICT mechanism. Here you see that unexcited fluorophore is there and free receptor. When the analyte comes and binds, and after that what happens, that intermolecular charge transfer takes place, and that compound becomes the fluorescent, and then it starts showing the emission. Next one is PET. So PET, what? Here it is basically unexcited fluorophore and free receptor. If you see their energetics, so what is that? It's HOMO of the free receptor is a little bit higher than the HOMO of the unexcited fluorophore. So whatever the in LUMO, if electrons are there, then what happens that this electron can come here easily. Because of that, whatever electron has gone up in the excited state, that cannot come to the ground state because already it has 2 electrons now. So once it binds with the analyte, what happens? There is a reorganization of energy, and then this HOMO level comes down for the receptor, and it is lower than the excited fluorophore, and because of that what happens that now from this to that electron transfer cannot be possible because it is lower in energy. So from the excited state, now this electron can easily move to the HOMO, and because of that you see the fluorescence, and that is PET. What is next? The Foster resonance energy transfer. So here happens that 2 moieties are there. So this is the donor and acceptor. So donor absorbs at this moiety, actually donor fluorescence that emits, and that light, emitted light, is absorbed by the acceptor. And as these two are overlapped, so because of that what happens, there is an energy transfer from donor to acceptor, and because of that you get the emission. Next one mechanism which is also very, very important, that is the CN isomerization. It's lots of effect you can see in the organic molecules, small molecules, like where you can see that when C double bond N is there, here cis and trans kind of geometry could be possible. So but once it binds to some analyte, and after that this cis trans, that like around C double bond N, that rotation cannot be possible, and because of that this isomerization is stopped. Once it is stopped, any kind of rotational motion or any kind of motion that gets frozen, then what happens, that non-radiative path, means decay path, that is stopped, and because of that radiative path becomes active, and then it becomes fluorescence active. So here you can see some examples have been given that this is the molecule where the CN isomerization could be possible, but as soon as by some organic transformation, if you can do such kind of things, then this is non-fluorescent, but this becomes highly fluorescent because of the CN isomerization is stopped. Similarly here also the same thing, 3 molecules have been shown, and in all 3 molecules same phenomena is happening, that CN isomerization is stopped, and that's how that leads to strong fluorescence. So now coming to the actual system, what we have designed, some of the system we will be discussing here. So first one, it is the coumarin based chemosensor. So this is the receptor unit, and this is the binding unit, and this receptor, actually fluorophore unit, is also taking part in binding. And what happens that this ligand, this is selectively binds the aluminium from a pool of different analyte which has been given here, all the different ions, and selectively it binds to aluminum only, and it turns on fluorescence it shows, and that energetics we studied by DFT calculation. And what we realized that this is the intramolecular charge transfer, and PET is taking place here, because when aluminum binds, then this is the free ligand energetics, and this is your aluminum HL complex. So when it binds, then this HOMO goes down, and then from here it cannot transfer the electron here. Because of that, what happens that from here it starts showing the intramolecular charge transfer. And also you can see the aluminum HL complex here. Here the charge is just completely smeared over all the molecules, and here charge transfer has taken place from this side. That means the phenol moiety here, whatever is there, from phenol to this side, coumarin side, charge transfer has taken place. So intramolecular charge transfer is taking place, and because of that this becomes active. And its detection limit was measured at 6.7 micromolar. Now next system, we utilize the pyrene-based fluorophore here, and pyrene-based this molecular probe, it selectively senses only the copper 2 complexes, and it forms first the metal organic macrocycle. Here 6 copper units are just means copper 6 and ligand 6 kind of unit is isolated, that forms this kind of metal organic macrocyclic, and this is only selective towards the copper. Other metal ion if you give, then there is no enhancement in the fluorescence. That means this is turn on fluorescence for copper only, and lifetime measurement we did it, and we realized that after forming the copper, that means strong binding for the copper is available. Its lifetime it increased from 0.855 to 3.252 nanosecond. Even though it is not very much higher, but still we thought that as it is not very cytotoxic, so let us check it. It's a bioimaging in Verocell, and that gave the claim that you see that copper 2 plus and HL, both ligand and copper 2, when it is available, and in Verocell it was very much fluorescent. So coming to the next system, where some signaling unit here we were time limit. That's what I
Yeah, Dr. Singh, can you just try your slides one more time? Let me just check.
Yeah, now it is connected. I had to, YouTube is connected. I think Dr. Akhilesh, now you can continue your presentation.
Okay. Thank you. So starting where I left it, so I was discussing about this fluorophore. Pyrene-based fluorophore was used for this chemosensor, and this could selectively sense the copper 2+ with the detection limit 0.66 micromolar. And also its average lifetime was found that when it binds to the copper 2+, its lifetime enhanced from 0.855 nanosecond to 3.252 nanosecond. Yeah, I understand that this lifetime is not very much for the fluorescence imaging, but still, as its cytotoxicity, we checked it and the cell viability was quite a bit good. I mean, 50% up to that 30 or 35 micromolar compound was tolerated. So we thought of just checking its confocal microscopy and bioimaging we did in Vero cells, and that could get excellent result that when ligand and copper 2+ both were injected in the cell, and that was very much visible under the UV light. So here, second system with the different signaling unit we tried, and here two different fluorophore we used in this pyridine-pyrazole kind of system, and surprisingly what happened that this was so much fluorescent, but still it did not give any good result because it was not selective in nature. So we again checked with the pyrene-based chemosensor, and that gave good selectivity towards copper 2+. But yeah, it shows the sequential sensing as well, that not only that this molecule senses copper 2+, but once it finds the copper 2+ complex, and then that complex became sensor for sulfide ion, and the region probably that with the sulfide ion, and also it was reversible. So reversibility, how we checked it, we took the ligand and then put the metal ion that means this copper 2+, and then it became fluorescence active, and then we put the sulfide, immediately fluorescence off got quenched, and when additional amount of metal ion, that means copper 2, was added, again fluorescence become active, and the reason probably being that copper 2 has much affinity towards the sulfide ion, and copper 2 sulfide got formed and ligand became bare. So because of that, fluorescence quenched and ligand was bare, and at that point when again copper 2+ was added and fluorescence was again re-achieved. Next one, so with the same system, chromogenic sensing we observed for the iron, and here the important part is that system senses not only iron but only the particular oxidation state of iron. Particular oxidation state means only iron 3+, not iron 2+. So what happens that you check that system, add the iron 3+, immediately it changes its color from colorless to brown, yellowish brown, and then again that complex now senses the fluoride ion, add little bit fluoride, and immediately again becomes colorless, and again it is the reversible in nature. Again you add it iron 3+, again becomes active. That means this like reversible nature of iron 3+ sensing and fluoride minus sensing was observed with this system. Now, just to check that why it was selective only for iron 3+, whether it senses iron 2+ or not, we just added iron 2+ and there was no color change. But what we did it that to oxidize iron 2+ to iron 3+, we added a small amount of H2O2 and also alternatively ferric ammonium nitrate we added, and both are the oxidizing agents. So immediately iron 2+ got oxidized to iron 3+, and as soon as iron 3+ analyte was there in the solution, immediately our molecular probe senses that and immediately turns the solution color from colorless to yellowish brown. So here is the summary of that work, that take this one, this molecular probe and put iron 3+ chromogenically, it senses iron 3+ and again put fluoride ion to that iron 3+ and this ligand complex, and then it becomes colorless. So this is the turn on, and again for fluoride it is turn off. but fluorescence quenching, that one was achieved by copper 2 plus, it senses fluorogenically, and then this copper 2 plus and molecular probe complex again senses the sulfide ion and it forms this one. So next system, we just did it on the basis of TICT fluorescence. So twisted intramolecular charge transfer was observed in this system. What we achieved that to this system, put aluminum 3 plus, it shows the turn on fluorescence behavior, but that fluorescence behavior was just quenched when you put it P2O7 4 minus. P2O7, that means the diphosphate was sensed by this aluminum H2L complex, and then again put aluminum 3 plus to that, and then again it becomes active. So this reversible nature of sensing of aluminum, then followed by diphosphate, and then again it becomes reversible, that was achieved, and sequential detection of PPI and aluminum 3 plus was achieved. To make it the system to real application, what we did it that this strip of filter paper strip was soaked in H2L, and then we put little bit aluminum solution to that, and immediately it becomes fluorescence active, which was observed in 365 nanometer UV light. So now this sensing of biological phosphates were achieved, like P2O7, I said the diphosphate, the same observation was achieved for ADP or ATP. So these biological ions were sensed very much by this aluminum H2L system. And this is the logic gate. Here it has been given that in what the aluminum 3 plus and then H2L, it is active. As soon as you give the diphosphate, immediately it becomes inactive. That means fluorescence turns off. Next one, how to confirm that TICT mechanism is involved in this. So for that, the signature of TICT is temperature dependent fluorescence study, and also you increase the polarity of the medium. And then both experiments suggest that when you increase the temperature, then what happens? Increasing the temperature, viscosity decreases, and then what happens? That twisting of the unit along the single bond, that becomes more and more when viscosity decreases, and because of that, what happens? That energy is dissipated by non-radiative pathway, and because of that, fluorescence intensity decreases. And when you add the polar solvent, when polarity is increased, then what happens? That is the charge transfer is taking place in polar solvent, that becomes more facile, and because of that, what happens? It's shifted towards the higher wavelength. Here you can see that these bands were around 450, so that decreases, and then this shift was just towards the red shift. Now, real-time sensor and sequential sensor on similar principle, iron 3 plus, aluminum 3 plus, copper 2 plus, and biological phosphates. These two were achieved by this kind of system, pyrimidine-based system, and here it was observed that for copper 2 plus, purple coloration was achieved. So chromogenic sensor for copper 2 plus, but fluorogenic sensor for iron 3 plus and aluminum 3 plus at very low pH, it was achieved. Here you can see that for H2L, it is very low, and as soon as you add the iron 3 plus and aluminum 3 plus, the intensity becomes high. That means it is showing the turn on fluorescence for iron 3 plus and aluminum 3 plus. And for copper 2 plus, as I said, that it is showing the color change, purple coloration, and that's how it is working as a sensor. And then to those complexes, so iron 3 plus and aluminum complexes, when you add the diphosphate, immediately that quenches the fluorescence intensity, and that's how sequential sensing of these anions were achieved. So the same thing was done for this one. Paper strip was taken, and then you take the molecular probe and then add iron 3 plus and aluminum 3 plus, that starts fluorescing. So this paper strip can be easily used for on-spot sensing of iron 3 plus and aluminum 3 plus. And energetics also tells that, you see that from this H2L and aluminum complex and iron 3 complex, in both cases, energy goes for HOMO, that goes down, and because of that, this PET is much more facile and it works as turn-on fluorescence sensor. So here in this work, what we showed that zinc cadmium is such kind of metal which is non-redox, which shows non-redox behavior. That means it doesn't get oxidized or doesn't get reduced. So sensing of these by electrochemical method, that is not possible. Same is true with the spectroscopic technique. Because of being D10 system, that cannot be studied by spectroscopic method. So for sensing zinc and cadmium, this kind of sensor becomes very, very important tool. And it was observed with this molecule DDTQ, and this senses cadmium and zinc both. And later on, by using copper 2+ and by quenching the fluorescence, we could differentiate between zinc and cadmium both. And this energetics by DFT studies, we could prove that this PET and CHEF mechanisms are involved in this turn-on fluorescence. Now, for this zinc and cadmium complexes, lifetime studies were also done, and for both complexes, you can see that the lifetime were enhanced as compared to the free molecular probe. And then detection limit was also in nanomolar range, 154 nanomolar and 126 nanomolar. So it was quite stiff because it was non-toxic in nature. IC50 value was 60 micromolar, and then in Verocell we could just do the confocal microscopy to prove its possible applications. Now, as I said that for some small molecules also we were looking for sensors. So water was the prime target, because water, humidity, these sensors are very, very relevant, very, very important, and they are very much useful for, like, at present era COVID-19, security purpose, rainfall detection, wearable devices, pharmaceutical, packaging, food processing, textile industry, leakage detection, and in all those applications, water sensor becomes very, very important. So we made one molecular probe which senses water very effectively, and in very limit of detection limit, if you see, that is the 0.27%, 0.24% for all medium. In different medium it was checked, and it was less than 0.5%. That means very small amount if water is there in this medium as the contaminant, immediately that will be sensed by this molecule. And the principle involved here for this sensing behavior or fluorescence on behavior, that was the aggregation induced emission. And the signature of aggregation induced emission is such that if you take that molecule as such outside, that is not fluorescent, but in solid state if you illuminate with UV light, immediately it starts fluorescing. So in solid state it shows very great fluorescence, and for that DFT studies also we did it to understand its mechanism, exactly what is going on. And then what in different medium, like different polar to non-polar medium, we just tried whether the water is sensed or not. In all four medium, you can see that excellent when we increase the percentage of water, in incremental amount of water was added, and then it starts from non-fluorescent to fluorescent green kind of complexes. And in dioxane, methanol, THF, in acetone, all medium it worked very well. But now we started searching for some application of this water sensor. Then what we could find, that take a strip paper and then coated with the sensor, that means you soak in the sensor and then start writing with something which by water, because it senses water. So with a strip, just you write, say H2O, it was written, and then in UV light it started glowing. And then how you can erase it? So just you heat it up by hot air gun, and then water will be evaporated. Once water is evaporated, immediately you see that writing is vanished. And then again, that was reversible in nature. Again and again, you can just write it. You write again something, then it appears in UV light, and then again you heat it, and that was just reversibly. Couple of times it was tried, and it worked fantastic. So in couple of cycles, it always shows the inkless kind of. So you can say its application as inkless writing, it can be always shown. And also for security purpose, many a times people just coding, decoding, they do it, like some kind of paper can be sent somewhere where nothing is written, very secret information, and only the person involved in that person knows that. Just you have to put little bit water or sprinkle some water and then see in the UV light that becomes active. So that kind of thing also can be just done with that. Okay, so these are the some application. Next application, moving to some amine sensing, which are the biogenic products, and one of the biogenic product 1,3-diaminopropane that was sensed by this molecular probe. So this molecular probe senses very selectively only diaminopropane, and ethyl amine also little bit was sensed, but that intensity was not up to the mark. So only the diaminopropane was sensed by this molecule, and this response was so quick. You can see that immediately after adding to the molecular probe, if you add diaminopropane, within 3 to 4 minutes, immediately it reaches to the maximum fluorescence intensity. So very quick response. And also energetics tells that you see that here the homolomo energy gap was increased. In the molecular probe, it was 4.2085, but immediately after adding the diaminopropane, the homolomo energy gap increased, and that shows that it is more stable system because the homolomo energy gap is more, so it cannot be oxidized or reduced or any other thing. So this is comparatively more stable than this one. So product formed was a bit stable in nature, and that was seen here. Here it has been shown that in different medium, if you do that, so it was observed that DMSO and water, that shows the excellent like fluorescence enhancement, and because of that this titration was done in water and DMSO, and from here detection limit was determined, and detection limit tells that it is in micromolar range, 4.35 micromolar, and here it was 1.51 micromolar. So you can just sense that 1,3-diaminopropane in micromolar concentration. So here now what is happening, we started exploring the reaction mechanism, that what is going on with the diaminopropane with the molecular probe. So molecular probe reacts with 1,3-diaminopropane, and these was the 3 possible products what we could think of. That one was that 2:1, so one diaminopropane and 2 such molecule, then C-base condensation, because it breaks from here and after that it gives this product, and this product was one of the option, and another option could be there that 1:1 this kind of condensation, and it gives second product. And first product, how it is forming, that once it forms this kind of product and this undergoes cyclization and it gives this. So predicted structure we could predict based on the spectroscopy that it is this one. Okay, how? I am just telling that you do the ESI mass spectra for after addition of diaminopropane, then it was obtained in positive mode 312, and the molecular mass for these 2 units, both units are 311 kind of. So 311, it could be this or this one. Okay, in positive mode it will be giving at 312. So but how to prove that this is the desired structure, that means predicted structure, whatever is forming product form is this one. For that we studied the NMR spectroscopy, or we did the NMR titration, taking the molecular probe, and incremental amount of DAP was added. After adding the DAP, what we observed that this this kind of this NH proton peak which was observed near this one, so this got vanished after addition of DAP. So how it can get vanished? If this is the molecular mass for these 2 molecules, if it forms this one, still this NH peak would have been observed, but here we are not getting, so that clearly suggests that maybe it is undergoing the cyclization, and this cyclization, how it can go, because the 6-membered cyclic ring that might be much more stable as compared to this one, and because of this is the favored product, and because of this it is showing the fluorescence. So finally, to summarize the second part of the talk, that we developed the sensors for environmental friendly and relevant inorganic cations and anions, and also small molecules like water and biogenic amines. For that also we developed the sensor, and biological and inorganic phosphates like ATP, ADP, and diphosphates, and those things for the sensor for those analytes we developed. So finally coming to the acknowledgement that all these works have been done by my two past students, PhD students, this Syed Mukhtar Hussain and Rabi. These two have done Rabi has done the first part of work, and second part of work has been done by Mukhtar, Sagarika and Subham. So they are doing wonderful work. And finally, without funding research work, it is very, very difficult to pursue. So IIT Bhubaneswar for infrastructure, SERB, UGC, DAE and DST, and also I thank my collaborators for this one. And finally, I would like to end my talk with a quote that if you take a suitable system in the right light at the right time, turns everything extraordinary. Thank you very much. And I will be happy to take any question from the audience.
Thank you, Dr. Akhilesh, for a very nice talk. Now the talk is open for discussion. Students, if you're having any doubts, you can send message. So in between, like other faculty members, if you're having any questions.
Probably they are tired now.
So maybe Akhilesh, I can ask one.
Yes, please.
Yes.
Very nice talk. Very nice talk. So all these sensing application I really enjoyed. So related to that water sensor that you have.
Yeah.
So why is it so specific in water? Because the molecule doesn't look like very hydrophobic. So you have some polar part also. But in all these different solvent, why this is so sensitive to water?
Sensitive to water means I was telling you that in water what is happening, aggregation is happening, because in water maybe it is trying to, like, that is not very suitable solvent. In other solvents it might be soluble, and in putting just water, aggregation of one molecule over another, or maybe exciplex formation that starts taking place, and because of that it starts fluorescing, fluorescence intensity goes higher.
Because the percentage was very low, it's around 0.2, 0.5, right? So in that percentage, of course, the polarity of the medium is not changing very significantly. So that means your system is very sensitive to polarity.
Yeah, very sensitive to polarity. Yeah, of course. And mainly aggregation, and that was the signature. I could show that in solid state, it fluoresces. Like if you take it in open air, that color is yellowish kind of. And if you put in UV light in solid state, immediately it starts glowing very beautiful fluorescent green color. So that is the signature of aggregation induced emission.
In solid state, are they also sensitive to moisture?
In solid state, that we have not checked it yet, humidity or maybe the water, but yeah, only we checked it in UV light, putting in UV light, and then it started glowing. And in solution state, in different medium from polar to non-polar, everywhere we have checked that is quite sensitive towards water.
Good, great talk. Thank you.
Thank you. Thank you, Barry.
Any other queries? Okay. If not, we thank Dr. Akhilesh for a very nice and wonderful talk. Thank you. And I'll hand over it to Dr. Patra.
Thank you, Dr. Kari.
Yeah, so thank you, Dr. Kari, for organizing this session very nicely. And we are really sorry for the happening, actually, mishappening during the talk. Actually, it was really unfortunate. We tried our level best, but anything, so we cannot predict anything.
It's okay, those are technical glitches. You can't do anything. That's fine.
So I must thank all the speakers and also the chair for this symposium or for this workshop. So far we have done. So now I request our colleague, Dr. Rana, to give a concluding remark about the workshop, whatever we are conducting today. So Dr. Rana, please take it.
Yeah, thank you Hello, Dr. Patra. I hope you all can hear me. Just confirm that you can hear me so that I can start.
Yeah.
Yes, we can.
Okay, thank you. Thank you. So I would begin with a quote. You know, the beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. It's not my quote. In fact, it's given by Carl Sagan. So good evening, everyone. It is my pleasure and privilege that the convener of RAIC 2022 gave me this opportunity to deliver the vote of thanks on behalf of the organizing committee and the faculty colleagues of the School of Basic Sciences. Thank you, Professor Patra. I myself, being a chemical biologist, thoroughly enjoyed the proceedings of this virtual conference spanned over 1.5 days. To the best of my knowledge, such an activity is the first one to be organized in chemistry and biosciences at School of Basic Sciences since its inception. Thank you again to all my colleagues. Thus, on behalf of everyone and on my personal behalf, I profoundly thank all the speakers who spared their precious time and delivered excellent lectures at the frontiers of inorganic chemistry in general. It was a fantastic showcase of chemistry of transition metals, ranging from its reactivity to ligand tuning for coordination complex to modulating both the physical and electronic properties for synthetic and biological applications. I again thank all the speakers for sharing the knowledge with all the student participants. I have no doubt that it must have been a great learning exercise for all the participating students, and I'm sure that the renowned speakers must have inspired many of them to take their future academic journey in the broad area of chemistry and at the interface of chemistry and biology. Success of any program is largely dependent on its audience. Thus, I would like to thank all the participants for making RAIC 2022 a successful event. My best wishes to all of you. I would also like to thank all the coordinators and session chairs for effective and timely management of this session. Thank you all. Conducting any kind of event is not possible without the help and support of the staffs and administration. On behalf of all concerned, I express my sincere gratitude to the entire administration, including head of the School of Basic Sciences, Dean R&D, and of course the Director IIT Bhubaneswar for their kind support, guidance, and encouragement. At last, it would not have been possible to conduct the RAIC 2022 without the funding support extended by SERB New Delhi. Thus, on behalf of the convener, Professor Patra, and the entire organizing team, I sincerely thank SERB for the generosity. We all at the SBS hope that we'll be able to tap your resources in your future for conducting an interdisciplinary in-person scientific gathering at IIT Bhubaneswar. For all the students who participated wholeheartedly, I would like to conclude with the following quote again by Carl Sagan. You know, chlorine is a deadly poisonous gas employed on European battlefield in World War I. Sodium is a corrosive metal which burns upon contact with water. Together, that makes a placid and unpoisonous material, what we call table salt. Why each of these substances has the properties it does is a subject called chemistry. With that, I thank you all again, and my best wishes to all of you. Thank you all. And now I'm done. I put pass on the mic to our convener, Professor Patra. Please take over.
Yeah. So thank you, Professor Rana, for your nice conclusive talk. And you have nicely summarized actually whatever since last 1.5 days we are trying to do. We hope all the participants and all of us enjoyed this one. And again, we are hoping that we are able to organize another scientific workshop or another scientific events soon, and that could be in person. So with that hope, so let me just conclude the session and let me what I should say, close the session for this RAIC 2022, and looking forward to see you all soon. Okay, in another scientific event in the near future. So thank you all, and with this,
and special thanks to all the speakers.
Yeah, so it is definitely. Yeah, so it is definitely. So let me again thank all the speakers for accepting our invitation from their busy schedule they made. Okay, so we hope we will again get their support whenever we need their help. Okay, thank you.
Virtual clapping.
Yeah.
Yeah, thank you.
Chalo, thanks a lot. I'm logging off now. Okay.
Okay then. Bye-bye.
Yeah. Bye.
Thanks.
Nice talk, Achilles.
Thank you. Okay, bye-bye.
Yeah, bye.